Hi there, I'm David Dye and welcome to the Mathematics for Machine Learning specialization. Before we get stuck in, let's set the scene. Machine learning is a set of powerful mathematical tools that enable us to represent, interpret and control the complex world around us. However, even just the word mathematics makes some people feel uneasy and unwelcome to explore the topic. The purpose of this specialization is to take you on a tour through the basic maths underlying these methods, focusing in particular on building your intuition rather than worrying too much about the details. Thanks to the amazing machine learning community, it's actually possible to apply many powerful machine learning methods without understanding very much about the underpinning mathematics by using open source libraries. This is great, but problems can arise, and without some sense of the language and meaning of the relevant maths, you can struggle to work out what's gone wrong or how to fix it. The ideal outcome of this specialization is that it will give you the confidence and motivation to immediately dive into one of the hundreds of brilliant applied machine learning courses already available online and not be intimidated by the matrix notation or the calculus. We want to open up machine learning to as many people as possible and not just leave all the fun to computer scientists. This first course offers an introduction to linear algebra, which is essentially a set of notational conventions and handy operations that allow you to manipulate large systems of equations conveniently. Over the next 5 modules, we'll be focusing on building your intuition about vectors and transformations through the use of quizzes and interactive widgets, as well as occasionally asking you to fill in the gaps in some Python coding examples. In the final module, Dr. Sam Cooper will bring it all together by showing you how linear algebra is at the heart of Google's famous Pagerank algorithm, which is used for deciding the order of web pages in search results. Hopefully, if you find this course useful, you'll stick around for our follow-on course, where Sam and I will introduce you to multivariate calculus. Then, in our other course, Dr. Mark Deisenroth will introduce principal component analysis. So, welcome. We really hope that the course will be productive and useful for you, but also quite a lot of fun, and I look forward to hearing from you in the forums. In this video, we're going to look a bit more at the types of problems we might want to solve and expose what linear algebra is and how it might help us to solve them. The first problem I might think of is one of price discovery. Say I go shopping on 2 occasions and I buy apples and bananas. And the first time I buy 2 apples and 3 bananas and they cost €8. And the second time I buy, say, 10 apples and 1 banana, and the cost is €13. And the A's and the B's here are the price of a single apple and a single banana. And what I'm going to have to do is solve these what are called simultaneous equations in order to discover the price of individual apples and bananas. Now, in the general case of lots of different types of items and lots of shopping trips, then finding out the prices might be quite hard. It might be quite difficult to solve all of these equations by hand. So we might want a computer algorithm to do it for us in the general case. Now, this is an example of a linear algebra problem. I have some constant linear coefficients here, these numbers, 2, 10, 3, 1, that relate the input variables a and b to the output 8 and 13. And that is, if I think about a vector AB that describes the prices of apples and bananas, then this gets translated into a cost if I know how many of them I want to buy, and the cost happens to be 8 on the first trip and €13 on the second trip. And I can write this down as a matrix problem where the 2, 3 is my first trip and the 10, 1 is my second trip. And then these are then matrices, that's a matrix then, and these are vectors. And what we're going to do over the course of modules 1 to 3 is build up looking at these different types of mathematical objects and understanding what they are and how to work with them, these vectors and these matrices. And then we'll come back and figure out how to solve this problem in the general case. Another type of problem we might be interested in is fitting an equation to some data. In fact, with neural networks and machine learning, we want the computer in effect not only to fit the equation, but to figure out what equation to use. That's a highly inexact description, really, of what's going on, but it gives the right sort of flavour. But let's say we have some data like this histogram here. This looks like a population with an average and some variation here, some width. Another type of problem we might want to solve, as well as the apples and bananas problem, is how to find the optimum value of the parameters in the equation describing this line, the ones that fit the data in the histogram best. That might be really handy. Then using that equation, we'd have an easy portable description of the population we could carry around without needing all the original data, which would free us, for example, from privacy concerns. Now we could plot how good the fit was in terms of the parameters, and that's what we'll look at in the next video. In this video, we've set up two problems in this first module on linear algebra. First, the problem of apples and bananas, of solving simultaneous equations. And secondly, the optimization problem of fitting some data with an equation with some fitting parameters. And these problems we'll go on to look at and motivate our work right through the course on linear algebra and its partner of multivariate calculus. So the first thing we need to do in this course on linear algebra is to get a handle on vectors, which will turn out to be really useful for us in solving those linear algebra problems. That is, the ones that are linear in their coefficients, such as most fitting parameters. We're going to first step back and look in some detail at the sorts of things we're trying to do with data and why those vectors you first learned about in high school are even relevant. And this will hopefully make all the work with vectors a lot more intuitive. Let's go back to that simpler problem from the last video, the histogram distribution of heights of people in the population. You know, there aren't many people above about 2 meters, say, and there aren't really very many people below 1.5 meters. Say we wanted to try fitting that distribution with an equation describing the variation of heights in the population. And let's say that equation has just two parameters, one describing the center of the distribution here, and we'll call that mu, and one describing how wide it is, which we'll call sigma. So we could fit it with some curve that had two parameters, mu and sigma. And I would use an equation like this. I'd call it f of x, some function of x, where x is the height, is equal to 1 over sigma root 2 pi times the exponential of minus x minus mu squared divided by 2 sigma squared. So this equation only has two parameters, sigma here and mu, and it looks like this. And it has an area here of 1 because there's only 100% of people in the population as a whole. Now don't worry too much about the form of the equation. This is called the normal or Gaussian distribution, and it's got a center at mu and a width of sigma. And it's normalized so that its area is 1. Now, how do we go about fitting this distribution? That is, finding mu and sigma, or the best possible mu and sigma, that fits the data as well as is possible. Imagine that we had guessed that the width was wider than it really is, but keeping the area at 1. So if we guessed that it was a fatter and probably a bit shorter distribution, something like that, say. So this one has something like that. This one has a wider sigma, but it's got the same mu. It'd be too high at the edges here and too low in the middle. So then we could add up the differences between all of our measurements and all of our estimates. We've got all of these places where we underestimate here and all of these places where we overestimate here. And we could add up those differences, or in fact the squares of them, to get a measure of the goodness or badness of the fit. And we'll look in detail at how we do that once we've done all the vectors work and once we've done actually all the calculus work. Then we could plot how that goodness varied as we changed the fitting parameters sigma and mu. And we get a plot like this. So if we had our correct value, our best possible value for mu here, and our best possible value for the width sigma here, we could then plot for a given value of mu and sigma what the difference was. So if we were at the right value, we'd get a value of goodness where the sums of the squares of the differences was 0. And if mu was too far over, if we had misestimated mu and we'd got the distribution shifted over i.e. the width was right, but we had some wrong value of mu there, then we get some value of all the sums of the squares of the differences of our goodness being some value here that was higher. And it might be the same if we went over the other side and we had some value there. And if we were too wide, we'd get something there, or too thin, we'd get something that was too thin like that. Something like that, say. So we'd get some other value of goodness. And we could imagine plotting out all of the values of where we had the same value of goodness or badness for different values of mu and sigma. And we could then do that for some other value of badness, and we might get a contour that looked like this, and another contour that looked like this, and so on and so forth. Now, say we don't want to compute the value of this goodness parameter for every possible mu and sigma. We just want to do it a few times and then find our way to the best possible fit of all. So say we started off here with some guess that was too big a mu and too small a width. We thought people were taller than they really are and that they were tighter packed in their heights than they really are. Well, what we could do is we could say, well, if I do a little move in mu and sigma, then does it get better or worse? And if it gets better, well, we'll keep moving in that direction. So we could imagine making a vector of a change in mu and a change in sigma. And we could have our original mu and sigma there, and we could have a new value u prime, sigma prime, and ask if that gives us a better answer, if it's better there, or if mu prime, sigma prime took us over here, if we were better or worse there, something like that. Now actually, if we could find what the steepest way down the hill was, then we could go down this set of contours, this sort of landscape here, towards the minimum point, towards the point where we get the best possible fit. And what we're doing here, these are vectors. These are little moves around space. They're not moves around a physical space, they're moves around a parameter space, but it's the same thing. So if we understand vectors and we understand how to get down hills, that sort of curviness of this value of goodness, that's calculus, then once we've got calculus and vectors, we'll be able to solve this sort of problem. So we can see that vectors don't have to be just geometric objects in the physical world of space. They can describe directions along any sorts of axes. So we can think of vectors as just being lists. If we thought of the space of all possible cars, for example, so here's a car, there's its back, there's its window, there's the front, something like that. There's a car, there's the window. We could write down in a vector all of the things about the car. We could write down its cost in euros, we could write down its emissions performance in grams of CO2 per 100 kilometers, we could write down its NOx performance, how much it polluted our city and killed people due to air pollution. We could write down its Euro NCAP star rating, how good it was in a crash. We could write down its top speed and write those all down in a list that was a vector. That'd be more of a computer science view of vectors, whereas the spatial view is more familiar from physics. In my field, metallurgy, I could think of any alloy as being described by a vector that describes all of the possible components, all the compositions of that alloy. Einstein, when he conceived relativity, conceived of time as just being another dimension. So space-time is a four-dimensional space, 3 dimensions of meters, and 1 of time in seconds. And he wrote those down as a vector of space-time, of x, y, z, and time, which he called space-time. When we put it like that, it's not so crazy to think of the space of all the fitting parameters of a function, and then of vectors as being things that take us around that space. And what we're trying to do then is find the location in that space where the badness is minimized, the goodness is maximized, and the function fits the data best. If the badness surface here was like a contour map of a landscape, we're trying to find the bottom of the hill, the lowest possible point in the landscape. So to do this well, we'll want to understand how to work with vectors and then how to do calculus on those vectors in order to find gradients in these contour maps and minima and all those sorts of things. Then we'll be able to go and do optimizations, enabling us to go and work with data and do machine learning and data science. So in this video, we've revisited the problem of fitting a function to some data, in this case the distribution of heights in the population. What we've seen is that the function we fit, whatever it is, has some parameters, and we can plot how the quality of the fit, the goodness of the fit, varies as we vary those parameters. Moves around these fitting parameter space are then just vectors in that space of fitting parameters. And therefore we want to look at and revisit vector maths in order to be able to build on that and then do calculus and then do machine learning. So we have these things called vectors, like this guy here. What we want to do first is get an idea of what makes a vector a vector. What we'll do in this video is explore the operations we can do with vectors, the sort of things that we can do with them that define what they are and the sort of spaces they can apply to. So a vector we can think of as an object that moves us about space, like this guy here. This could be a physical space or a space of data. At school you probably thought of a vector as something that moved you around a physical space, but in computer and data science we generalise that idea to think of a vector as maybe just a list of attributes of an object. So we might think of a house, say. So here's a house. And this might have a number of attributes. We could say it was 120 square meters in floor area. It might have 2 bedrooms, say. It might have 1 bathroom. That would be sort of sensible. And it might be worth 150,000 euros, say. And I could write that down as the vector 120 square meters, 2 bedrooms, 1 bathroom, and 150,000 euros. And this, that is, while in physics we think of this as being a thing that moves us about space, in data science we'd think of this vector as being a thing that describes the object of a house. So we've generalised the idea of moving about space to include the description of the attributes of an object. Now, a vector is just something that obeys 2 rules. Firstly, addition, and secondly, multiplication by a scalar number. We'll do this first, thinking of a vector as just a geometric object starting at the origin. So something like this. So we'll get a vector R there. Vector addition is then when we just take another vector. So let's take another vector like this guy here. Let's call him S. And where we put S on the end of R. So then that's S. And therefore, if we put S on the end of R, we get a sum that's R, then going along S. We'll call that guy R plus S. Now, we could do this the other way around. We could do S and then R, and that would be S plus R. So you go along S and along that way. And that would be S plus R there, S plus R. And we see that they actually give us the same thing, the same answer. So R plus S is equal to S plus R. So it doesn't matter which way round we do the addition. So the other thing we want to be able to do is scalar multiplication, that is to scale vectors by a number. So a number A, say, making it twice as long or half as long, something like that. So we'd say that, say, 3R was doing R 3 times, so that would be 3R there, where A was 3. Or we could do a half R, which would be something like that. The only tricky bit is what we mean by a minus number, and by minus R we'd mean going back the other way by a whole R. So we take R, we go back the other way, the same distance there. That would be minus R. So in this framework, minus means go back the other way. At this point, it's convenient to define a coordinate system. So let's define space by 2 vectors. Let's call the first one that takes us left, right, and is of unit length, length 1. Let's call that a vector I. We'll have another vector here that goes up, down, a vector j that's also of unit length of length 1. And then we'd say, just use our vector addition rules. If we wanted a vector r here, something like this, that was 3 2's, by which we mean we go 3 i's, 1 I, 2 I, 3 i's, and then 2 j's. So we go 3 i's plus 2 j's, and that gives us a vector r here, just from our vector sum. And what we mean in the 3 2 is do 3 i's added together, or a scalar multiple of 3 i's, and then do a scalar multiple of 3 j's as a vector sum. And that's what we mean by a coordinate system and defining R as being 3 2. So then if I have another vector S, let's say S is equal to minus 1 i's and 2 j's. That is, it takes us back 1 I and up 2 j's, so that's S. Then R plus S would be that. We just put S on the end of R. And then R plus S is going to be, therefore, that total vector. That's going to be R plus S. And we can just add up the components, right? So R is 3 i's, and S takes us back 1. So it's 3 plus minus 1 gives us 2 i's. And in the J's, R takes us up 2, and S takes us up another 2. So that's a total of 4 J's. So we can just add up the components when we're doing vector addition. So we can see that because we're doing this component by component, then vector addition must be what's called associative. Formally, what this means is that if we have 3 vectors, R, S, and another one, T, it doesn't matter whether we add R plus S and then add T, or whether we add R to S plus T. It doesn't matter where we put the bracket. We can do this addition and then that one, or we can do this addition and then that one. So a consequence of it not mattering what order we had, so S plus R is equal to R plus S, we can also see that therefore it doesn't matter what order we do the additions in if we've got 3, and that's called associativity. That's associative. That's formally that definition. And vector addition, we can see when we're adding it up like this, will be associative. So I've just got rid of the S's and so on, so we can talk about another issue, which is in a coordinate system, what do we mean by multiplication by a scalar? So if we want to take a multiplication by a scalar, say 2, then we define this to mean that 2R would be equal to 2 times the components of R. So 2 times 3 for i's and 2 times 2 for the j's, because we've got 2 there multiplied by 2, and that will give us 6, 4. So 2R would be doing R and then doing another R, so that would be 2R, which would be the vector 6, 4. Go along 3 i's, 4, 5, 6 i's, and up 4 j's. Now, you need to think about another question, which is minus R. So R is this, minus R is then that, which will be minus 3 minus 2. That will be minus R. So then we see sort of obviously, kind of, that R plus minus R is equal to 3 plus minus 3 on the i's and 2 plus minus 2 on the j's, which is equal to 0, 0. So if we do R and then add minus R, we end up back at the origin, duh. Therefore, we've defined what we mean by vector subtraction here. Vector subtraction is just addition of minus 1 times whatever I'm doing, putting after the minus sign. So if we think of another vector S, we had S was minus 1, 2 before, right? Minus 1i plus 2j's. So then R minus S would be this. So that's minus S there is equal to go along 1 on the i's and minus 2 on the j's. So R minus S, add up the components, R minus S, let's switch to an addition. So R minus S is this vector here, that's R minus S. If we add up the components of that, it's 3 i's plus 1, 3 plus 1 on the i's, and 2 plus minus 2 on the j's. So that gives us the vector 4, 0. So if we do R is go along 3, and minus S is go along 1, we've got a total of 4. And if R is go up 2, and minus S is go down 2, we've ended up going up, down 0 in total. So then we've not only done addition by components, we've done now what we mean by vector subtraction as well, as being addition of a negative 1 multiple of the thing that we're doing the minus by. And that's vector subtraction and addition by components. So let's come back to the house example for a moment. So we said we had a house, that's my house, that was 120 square meters, 2 bedrooms, 1 bathroom, and 150,000 euros. So if I put the units in, that's square meters, that's its number of beds, that's its number of baths, and that's its thousands of euros that it's worth. So 2 houses now is equal to the vector addition of those things is equal to 2, and the way we're defining vector addition, times 120 to 150, which would be equal to 240, 4, 2, 300. So we'd say that in this scheme, the way we're defining it, then 2 houses would be 240 square metres, that makes sense. 4 bedrooms, 2 bathrooms, and worth 300,000 euros if I bought 2 houses identically next to each other. And that would be a scalar multiple or an addition of one house to another. Yeah, one house plus one house. And we could keep on doing that with 3 houses or differently shaped houses or whatever it was, or negative houses. The way we've defined vectors, that will still apply to these objects of houses. So that's vectors. We've defined 2 fundamental operations that vectors satisfy. That is addition, so like r plus s here, and multiplication by a scalar, so like 2r here and minus s here. And we've explored the properties that those imply, like associativity of addition and subtraction, what subtraction really means of vectors, r plus minus s being r minus s. And we've noticed that it can be useful to define a coordinate system in which to do our addition and scaling, so like R3, 2 here, using these fundamental basis vectors, these things that define the space, I and j, which we call the basis vectors, or the things that define the coordinate system. We've also seen that although perhaps it's easiest to think of vector operations geometrically, we don't have to do it in a real space. We can do it with vectors that are data science lists of different types of things, like the attributes of a house. So that's vectors. That's all the fundamental operations. So in this first module of our course on linear algebra, we first looked at the problem of data, that our world has so much of it, and that if we could figure out how to analyse and use it, we could really solve problems in the world. And we've looked at where these courses fit in terms of helping us access the world of machine learning and data science. Then we've moved on to look at some example problems, the problem of solving some simultaneous equations, for example, to discover the price of things in the apples and bananas problem, or the problem of fitting a model equation with some fitting parameters we want to optimise against some data. We've then said that both of these problems are going to involve vectors and possibly some calculus. So we've started off our journey with vectors and with defining vector addition and scalar multiplication. In the next module, we'll go further to look at some more operations with vectors and define what we mean by a vector space and the coordinate system of a vector space, or its basis. In this module, what we're looking at is the sorts of things we can do with vectors. First, we can look at their modulus or magnitude. We can look at a way to combine vectors together to get a number called the dot product, which will take us on to find the scalar and vector projections. That will then take us on to looking at the vectors that we use to define the space, the basis vectors, and at linear independence and linear combinations. And that will wrap up module 2. This is hopefully going to be a good work. We'll get all set with some nice problems and exercises to try this stuff out. This is the main module on vectors. After this, in the next modules, we'll move on to matrices. So, we've got stuff to do. Let's get started with the next video on the modulus and the dot product. So, we've looked at the 2 main vector operations of addition and scaling by a number. And those are all the things we really need to be able to do to define what we mean by a vector, the mathematical properties that a vector has. Now we can move on to define 2 things, the length of a vector, also called its size, and the dot product of a vector, also called its inner scalar or projection product. The dot product is this huge and amazing concept in linear algebra with huge numbers of implications, and we'll only be able to touch on a few parts here, but enjoy, it's one of the most beautiful parts of linear algebra. So when we defined a vector initially, say this guy r here, we did it without reference to any coordinate system. In fact, as a geometric object, this thing r just has 2 properties, its length and its direction, that it's pointing that way. So irrespective of the coordinate system we decided to use, we want to know how to calculate these 2 properties of length and direction. If the coordinate system was constructed out of 2 unit vectors that were orthogonal to each other, like I here and j here in 2D, then we can say that r is equal to a times I plus b times j. And when I say unit about I and j, I mean they're of length 1, which people will often denote by putting a little hat over them like this. Then from Pythagoras, we can say that the length of r is given by the hypotenuse. So what I mean by that is, if we draw a little triangle here, then we've got this length here is ai's, and so if we write the length being, well, with these two little vertical lines, it's just of length a, because I is of length 1, right? And this side here is bj's, and that's of length b. So this side here is from Pythagoras is just a squared plus b squared, all square rooted, and that's the size of r. So we can write down r, quite often people will do this, write r down like this, just ignoring the I and j and writing it as a column vector. So r is equal to ab. And the size of r, we write down as being the square root of a squared plus b squared. Now we've done this for two spatial directions defined by unit vectors I and j that are at right angles to each other. But this definition of the size of a vector is more general than that. It doesn't matter if the different components of the vector are dimensions in space, like here, or even things of different physical units like length and time and price. We still define the size of a vector through the sums of the squares of its components. The next thing we're going to do is to define the dot product, one way among several of multiplying, if you like, two vectors together. If we have two vectors r and s here, r here has components ri, rj, so r in the I direction, r in the j direction, and s has components si and sj, then we define r dotted with s to be given by multiplying the I components together, so that's ri times si, and adding the j components together, so that's rj times sj. That is, the dot product is just a number, a scalar number, like 3, given by multiplying the components of the vector together in turn and adding those up. So in this case, that would be 3 and 2 for the RIRJ, and minus 1 and 2 for S. So if we do that, then we get a sum that R dot S is equal to minus 3 plus 4, which gives us 1. So R dot S, in this case, is just 1. Now, we need to prove some properties of the dot product. First, it's commutative. So, commutative. And what commutative means is that R dot S is equal to S dot R. It doesn't matter which way round we do it. And it doesn't matter because when we put these numbers in here, if we interchange those, the R's and S's, we get the same thing when we multiply minus 1 by 3. It's the same as 3 times minus 1. So it doesn't matter which way round we do the dot product, S dot R is equal to R dot S, which means it's commutative. The second property we want to prove is that the dot product is distributive over addition, by which I mean that if I've got a third vector here now, t, that R dotted with S plus t is equal to R dotted with S plus R dotted with t. I can multiply it out in that kind of way. This probably feels kind of mundane or obvious, but let's prove it in the general case. So let's say I've got some n-dimensional vector R, components R1, R2, all the way up to Rn. And S is the same, has components S1, S2, all the way up to Sn. And T has components T1, T2, all the way up to Tn. Then let's multiply it out. So if we take the left-hand side, R dotted with S plus T, that's going to be equal to R1 times S1 plus T1, if we take the components. And then R2, component R2, times components S2 plus T2. and then all the dimensions in between, and then finally Rn times Sn plus Tn. And then what we can do is we can then separate that out. So we've got, multiply that out. So we've got R1 S1 plus R1 T1 plus R2 S2 plus R2 T2 plus all the ones in between Rn Sn plus Rn Tn. And then we can collect them together because we've got the R1 S1 terms, R2 S2 all the way to Rn Sn, and that's of course just equal to R dotted with S. And if we collect the RT terms together, we've got R1 T1, R2 T2, all the ones in between, and Rn Tn, and that's just R dotted with T. So we've demonstrated that this is in fact true, that you can pull out plus signs and dots in this way, which is called being distributive over addition. The third thing we want to look at is what's called associativity. So that is, if we take a vector, a dot product, and we've got R dotted with some multiple of S, where A is just a number, it's just a scalar number. So we're multiplying S by a scalar, and what we're going to say is that that is equal to A times R dotted with S. And that means that it's associative over scalar multiplication. And we can prove that quite easily just in the 2D case. So if we say we've got R1 times A S1 plus R2 times A S2, that's the left-hand side just for a two-dimensional vector. Then we can pull the A out, right? So we can take the A out of both of these. And so then we've got R1 S1 plus R2 S2. And that's just R dot S, A times R dot S. So this is in fact true. And so we've got our three properties that the dot product is commutative. We can interchange it. It's distributive over addition, which is this expression. And it's associative over scalar multiplication. We can just pull out scalar numbers out. As an aside, sometimes you'll see people in physics and engineering write vectors in bold and numbers or scalars in normal font. Or they'll underline their vectors to easily distinguish them from things that are just scalars. Whereas in maths and computer science, people don't tend to do that. It's just a notation difference between different communities, and it's not anything fundamental to worry about. The last thing we need to do before we can move on is draw out the link between the dot product and the length or modulus of a vector. If I take a vector and dot it with itself, so R dotted with R, what I get is just the sums of the squares of its components. So I get, R1 times R1 plus R2 times R2, and all the others if there are all the others. So I get R1 squared plus R2 squared. Now that's quite interesting because that means if I take the dot product of a vector with itself, I get the square of its size, of its modulus. So that is, that equals R1 plus R2 squared square rooted all squared. So that's mod R squared. So if we want to get the size of a vector, we can do that just by dotting the vector with itself and taking the square root. And that's really kind of neat and really, hopefully, quite satisfying. Let's take the cosine rule from algebra, which you'll remember probably vaguely from school. And that said, if we had a triangle with sides A, B, and C, then what the cosine rule said was that C squared was equal to A squared plus B squared minus 2AB times the cos of the angle between A and B, cos that angle theta there. Now, we can translate that into our vector notation. If we called this vector R here, and we called this vector S here, then this vector would be minus S plus R. So that vector would be R minus S plus R. So we could say that C squared was the modulus of R minus S squared, and that would be equal to the modulus, the size of R squared, plus the size of S squared, minus 2 mod R mod S cos theta. Now, here's the cool bit. We can multiply this out using our dot product, because we know that the size of r minus s squared is equal to r minus s dotted with itself. Now, that's just that. And we can multiply that out, and then we'll compare it to this right-hand side here. So r minus s dotted with r minus s, well, that's going to be, if we need to figure out how to multiply that out, that's going to be equal to r dotted with r, and then take the next one, minus s dotted with r, minus s dotted with r again, if we take that minus s and that r, minus s dotted with r again, and then minus s dotted with minus s. So that is, we've got the modulus of r squared here, and we dot r with itself, minus twice s dotted with r, and then minus s dotted with minus s, well, that's going to be the size of minus s squared, which is just the size of s squared. And then we can compare that to the right-hand side, and when we do that comparison, compare that to the right-hand side, the minus r squareds are going to cancel, the r squareds even, the s squareds are going to cancel, and so we get a result, which is that minus twice s dotted with r is equal to minus twice modulus of r, modulus of s, cos theta. That is, and then we can lose the minus sign, right? The minus signs will cancel out, just multiply through by minus 1. So, and then the 2's we can cancel out again. So we can say that the dot product r dot s, just to put it in a more familiar form, is equal to mod r mod s cos theta. So what we found here is that the dot product really does something quite profound. It takes the size of the two vectors, if these were both unit length vectors, those would be 1, and multiplies by cos of the angle between them. It tells us something about the extent to which the two vectors go in the same direction. Because if cos theta, if theta was 0, then cos theta would be 1, and r dot s would just be the size of the two vectors multiplied together. If the two vectors, on the other hand, were at 90 degrees to each other, if they were, r was like this, and s was like this, and the angle between them, theta, was equal to 90 degrees, cos theta, cos of 90, is 0, and then r dot s is going to be, we can immediately see, r dot s is going to be some size of r, some size of s, times 0. So if the two vectors are pointing at 90 degrees to each other, if they're what's called orthogonal to each other, then the dot product is going to give me 0. If they're both pointed in the same direction, say s was like that, and the angle between them is 0, cos of 0 is equal to 1. And then r dot s is equal to the mod r times mod s, just the multiplication of the two sizes together. Last fun one here, is that r and s are in opposite directions. So let's say s was now going this way, and the angle between them was 180 degrees. Cos of 180 degrees is equal to minus 1. So then r dot s would be equal to minus the size of r times the size of s. And so what the dot product here really does with this cos, it tells us when we get the minus sign out that they're going in opposite directions. So there's some property here in the dot product that we've derived by looking at the cosine rule that we've derived here. When the dot product's 0, they're at 90 degrees to each other, they're orthogonal. When they're going the same way, we get a positive answer. When they're going more or less in opposite directions, we get a negative answer for the dot product. Now, there's one last thing to talk about in this segment, which is called projection. And for that, we'll need to draw a triangle. So if I've got a vector r and another vector s, Now, if I take a little right-handed triangle, drop a little right-handed triangle down here, where this angle's 90 degrees, then I can do the following. If I can say that, if this angle here is theta, that cos theta is equal to, from SOHCAHTOA, is equal to the adjacent length here over the hypotenuse there. Adjacent over the hypotenuse. That is, and this hypotenuse is the size of S. So that's the adjacent over the size of S there. Now, if I compare that to the definition of the dot product, I can say that R dotted with, we'll have fun with colours, dotted with S is equal to mod R, size of R, times the size of S times cos theta. Cos theta. But the size of S times cos theta, if I put S up here, I just need to put my theta in there. Cos theta is just that adjacent side. So that's just that adjacent side here in the triangle. The adjacent side here is just kind of the shadow. If I had light coming down from here, it's the shadow of S on R, that length there. It's kind of a shadow cast if I had a light at 90 degrees to R shining down on S. And that's called the projection. So what the dot product gives us is it gives us the projection here of S onto R times the size of R. One thing to notice here is that if S was perpendicular to R, if S was pointing this way, it would have no shadow. That is, if cos theta was 90 degrees, that shadow would be naught. The cos theta would be naught here, and I get no projection. The other thing the dot product gives us is it gives us the size of R times some idea about the projection of S onto R, the shadow of S onto R. So if I divide the dot product R dot S by the length of R, just bring the R down here, I get mod S cos theta. I get that adjacent side. I get a number which is called, because R dot S is a number and the size of R is a number, and that's called the scalar projection. And that's why the dot product is also called the projection product, because it takes the projection of one vector onto another. We just have to divide by the length of R. And if R happened to be a unit vector, or one of the vectors we use to define the space of length 1, then that would be of length 1, and R dot S would just be the scalar projection of S onto that R, that vector defining the axes or whatever it was. Now, if I want to remember to encode something about R, which way R was going, into the dot product or into the product, I could define something called the vector projection. And that's defined to be R dot S over mod R dotted with itself, so R dot R mod R squared. So that's R dot S over R dot R, if you like, because mod R squared is equal to R dot R. And we multiply that by the vector R itself. So that's dot product's just a number, these sizes are just a number, and R itself is a vector. So what we've done here is we've taken the scalar projection R dot S over R, this guy, that's how much S goes along R, and we've multiplied it by R divided by its length. So we've multiplied it by a vector going the direction of R, but that's been normalized to have a length 1. So that vector projection is a number times a unit vector that goes in the direction of R. So if R, say, was some number of lengths, the vector, that would be R divided by its size, say, if that was a unit length vector I've just drawn there. And the vector projection would be that number s dot r, that adjacent side, times a vector going in the unit length of r. So that's, if you like, the scalar projection also encoded with something about the direction of r, just a unit vector going in the direction of r. So we've defined a scalar projection here, and we've defined a vector projection there. So, good job. This was really the core video for this week. We've done some real work here. We've found the size of a vector, and we've defined the dot or projection product. We've then found out some mathematical operations we can do with the dot product. That it's distributive over vector addition and associative with scalar multiplication, and that it's commutative. We've then found that it finds the angle between two vectors, the extent to which they go in the same direction. And then it finds the projection of one vector onto another. That's kind of how one vector will collapse onto another, which is what we'll explore in the next two videos. So, good work. Now's a good time to pause and try some examples that put all this together and give it all a workout and a bit of a try before we move on. Now, so far, we haven't really talked about the coordinate system of our vector space, the coordinates in which all of our vectors exist. But it turns out that in doing this thing of projecting, of taking the dot product, we're projecting our vector onto one which we might use as part of a new definition of the coordinate system. So in this video, we'll look at what we mean by a coordinate system, and then we'll do a few cases of changing from one coordinate system to another. So, remember that a vector, like this guy r here, is just an object that takes us from the origin to some point in space, which could be some physical space, or it could be some space of data, like bedrooms and thousands of euros for the house, or something like that. What we haven't talked about so far, really, is the coordinate system that we use to describe space. So, we could use a coordinate system defined by these two vectors here. I'm going to give them names. We called them I and j before. I'm going to give them names E1 and E2. I'm going to define them to be of unit length, so I'm going to give them a little hat, meaning they're of unit length. And I'm going to define them to be the vectors 1, 0 and 0, 1. And if I had more dimensions in my space, I could have E3 hat, E4 hat, E5 hat, E a million hat, whatever. Here the instruction then is that R is going to be equal to doing a vector sum of 2 E1s or 3 E1s and then some number of E2. So we'll call it doing 3 E1s hats plus 4 E2 hats. And so we'll write it down as a little list, 3, 4. So R is the 3, 4 here is the instruction to do 3 E1 hats plus 4 E2 hats. But if you think about it, my choice of E1 hat and E2 hat here is kind of arbitrary. It depends entirely on the way I set up the coordinate system. There's no reason I couldn't have set up some coordinate system at some angle to that. Or even use vectors to find the axes that weren't even at 90 degrees to each other and were of different lengths. I could still have described R as being some sum of some vectors I used to define the space. So I could have, say, another set of vectors B, and I'll call B1 here in the vector 2, 1, and I could have another vector here, B2, as the vector minus 2, 4. And I've defined it in terms of the coordinates E, and I could then describe R in terms of you're using those vectors B1 and B2. It's just the numbers in R would be different. So we call the vectors we use to define the space, these guys E or these guys B, we call them basis vectors. So the numbers I've used to define R only have any meaning when I know about the basis vectors. So R referred to these basis vectors E is 3, 4. But R referred to the basis vectors B also exists. We just don't know what the numbers are yet. So this should be kind of amazing. R, the vector R, has some existence in a deep sort of mathematical sense, completely independently of the coordinate system we use to describe the numbers in the list describing R. R, the vector that takes us from there, from the origin to there, still exists independently of the numbers used in her. Which is kind of neat, right? Sort of fundamentally sort of idea. Now, if the new basis vectors, these guys B, are at 90 degrees to each other, then it turns out the projection product has a nice application. We can use the projection or dot product to find out the numbers for R in the new basis B, so long as we know what the B's are in terms of E. So here I've described B1 as being 2, 1, as being E1 plus E2, twice E1 plus 1 E2. And I've described B2 as being minus 2 E1s plus 4 E2s. And if I know B in terms of E, I'm going to be able to use the projection product to find R described in terms of the B's. But this is a big if. The B1 and B2 have to be at 90 degrees to each other. If they're not, we end up being in big trouble and need matrices to do what's called a transformation of axes from the E to the B set of basis vectors. We'll look at matrices later, but this will help us out a lot for now. Using dot products in this special case where the new basis vectors are orthogonal to each other is computationally a lot faster and easier. It's just less generic. But if you can arrange the new axes to be orthogonal, you should, because it makes the computations much faster and easier to do. So you can see that if I project R down onto B1, so I look down from here and project down at 90 degrees, I get a length here for the scalar product, and that scalar projection is the shadow of R onto B1, and a number of the scalar projection describes how much of this vector I need. And the vector projection is going to actually give me a vector in the direction of B1 of length equal to that projection. Now if I take the vector projection of R onto B2, going this way, I'm going to get a vector in the direction of B2 of length equal to that projection. And if I do a vector sum of that vector projection plus this guy's vector projection, I'll just get R. So if I can do those two vector projections and add up their vector sum, I'll then have RB being the numbers in those two vector projections. And so I've found how to get from R in the E set of basis vectors to the B set of basis vectors. Now, how do I check that these two new basis vectors are at 90 degrees to each other? I just take the dot product. So we said before the dot product cos theta was equal to the dot of two vectors together, so B1 and B2, divided by their lengths. So if B1 dot B2 is 0, then cos theta is 0, and cos theta is 0 if they're at 90 degrees to each other, if they're orthogonal. So I don't even need to calculate lengths, I'll just calculate the dot product. So B1 dot B2, here, I take 2 times minus 2, and I add it to 1 times 4, which is minus 4 plus 4, which is 0. So these two vectors are at 90 degrees to each other. So it's going to be safe to do the projection. So having talked through it, let's now do it numerically. So if I want to know what R described in the basis E, and R's pink, right? So if I take R in the basis E, and I'm going to dot him with B1, and the vector projection divides by the length of B1 squared. So R in E dotted with B1 is going to be 3 times 2 plus 4 times 1, 4 times 1, divided by the length of B1 squared. So that's the sum of the squares of the components of B. So that's 2 squared plus 1 squared. So that gives me 6 plus 4 is 10 divided by 5, which is 2. So this projection here is of length 2 times B1. So that projection there, that vector, is going to be 2 times B1. So that is, in terms of the original set of vectors B, the original vectors E, RE dot B1 over B1 squared times B1 is the vector, is 2 times the vector 2, 1, is the vector 4, 2. And I can do then now this projection onto E2, so I can do RE dotted with B2 and divide by the length of B2 squared. And RE dot B2 is 3 times minus 2 plus 4 times 4 divided by the length of B2 squared, which is minus 2 squared plus 4 squared. So that's 3 times minus 2 is minus 6, plus 4 times 4 is 16, so that's minus 6 plus 16 is 10. Divided by this length here is 4 squared is 16, 2 squared is 4, so 20, so that's equal to a half. So this vector projection here is that guy times B2, so that's RE dot B2 over the modulus of B2 squared, that's my half, times the vector B2, so that's a half times the vector B2, which is minus 2, 4. Now if I add those two together, 4, 2, this bit, that vector projection, plus this vector projection, so this guy is going to be a half B2, plus half minus 2, 4 is minus 1, 2. If I add those together, I've got 3, 4, which is just my original vector R, 3, 4, in the basis E. So in the basis of B1 and B2, RB is going to be 2, a half. Very nice, 2, a half. So actually in the basis B, it's going to be 2, a half there. So RB is 2 times B1 plus a half times B2. Very nice. So I've converted from the E set of basis vectors to the B set of basis vectors, which is very neat, just using a couple of dot products. So this is really handy, this is really cool. We've seen that our vector describing our data isn't tied to the axes that we originally used to describe it at all. We can redescribe it using some other axes, some other basis vectors. So the basis vectors we use to describe the space of data and choosing them carefully to help us solve our problem will be a very important thing in linear algebra and in general. And what we've seen is we can move the numbers in the vector we use to describe a data item from one basis to another. We can do that change just by taking the dot or projection product in the case where the new basis vectors are orthogonal to each other. So we've seen how we don't just have to have basis vectors that are our normal 1, 0 and 0, 1, the so-called natural basis. We can have different basis vectors that redefine how we move about space. In this video, we're going to define what we mean by a basis, by a vector space, and by the term linear independence, which is going to let us understand how many dimensions our vector space possesses. So first, let's define what we mean by a basis. A basis is a set of n vectors that are not linear combinations of each other, which means they're linearly independent of each other, and that span the space they describe. The space is then n-dimensional. This first criteria I can write down by saying that they're linearly independent if I can't write any of them down by taking some combination of the others. So for example, let's say I've got a vector b1 here. By taking multiples of b1, I can get anywhere along the 1D space of a line. If I take a second vector, b2, that isn't just a multiple of b1, then I can get anywhere in the plane of this board by taking combinations of b1 and b2, some number of b1s plus some number of b2s. And this is a 2D space. Now, let's take a third vector, b3. Now, for b3 to be a valid third basis vector, it has to be impossible for me to find some numbers, a1 and a2, such that I can satisfy this sum. So it has to be impossible for me to find b3 as some combination of b1s and b2s, where a1 and a2 are just numbers. That has to be impossible. And if it is impossible, b3 is a third basis vector, and b3 is linearly independent. if it is possible for me to find an A1 and A2 that satisfies that sum, B3 is then linearly dependent on B1 and B2, and it lies in the same plane as B1 and B2. And if it's impossible for me to find an A1 and A2, B3 must have some component out of the board, so I can then use B3 to give me a three-dimensional space. So that lets us define what we mean by the number of linearly independent basis vectors in our space. If I had a fourth basis vector, B4, that wasn't a linear combination of B1, B2, and B3, I'd have a four-dimensional space, and so on, up to as many dimensions as I like. Now, notice what my basis vectors B don't have to be. They don't have to be unit vectors, by which I mean vectors of length 1, and they don't have to be orthogonal, that is at 90 degrees to each other. But everything is going to be much easier if they are, so if at all possible, you want to use orthonormal basis vector sets, 90 degrees of unit length. Now, let's think about what happens when we map from one basis to another. The number line of the axis of the original grid then projects down onto the new grid, and potentially has different values on that grid, but the projection keeps the grid being evenly spaced. Therefore, any mapping we do from one set of basis vectors, from one coordinate system to another, keeps the vector space being a regularly spaced grid, where our original vector rules of vector addition and multiplication by a scalar still work. It doesn't warp or fold space, which is what the linear bit in linear algebra means. Things might be stretched or rotated or inverted, but everything remains evenly spaced, and linear combinations still work. Now, where the new basis vectors aren't orthogonal, then to do the change from one basis to another, we won't just be able to use the dot product. We'll need to use matrices instead, which we'll meet in the next module. So that's the formal definition of what we mean by a basis and by linear independence. For example, say I have a bunch of 2D data points like this. And say they all more or less lie on a straight line, right? We can kind of see that. These guys all more or less lie on a line that's going to be something like that. I can imagine redescribing that data by mapping them onto that line and then saying how far they're along that line. So I can map this guy down onto the line, and I can say the origin maps down there, and I can then say this data point is that far along the line. And he's also, so he's that far along the line, there, and he's this far away from the line. So I've got two dimensions here, how far I am along the line and how far I am from the line. And these guys, they're all slightly different distances from the line. Now, there's a little bit of an argument in stats as to whether we do the distance that way vertically or that way as a projection of the distance from the line. But it's sort of a theoretical argument. But notice that this distance from the line is effectively a measure of how noisy this data cloud is. If they are all tight on the line, they'd all be very small distances away. And if they were all quite spread, they'd be quite big distances away. So this distance from the lineness is effectively the noise. And that's information that isn't very useful to us, so we might want to collapse it. Except that that noise dimension tells me how good this line fit is. If the best fit line was all skewed, was all wrong, I get a much bigger numbers for the noisiness. And if the best fit line was as good as possible, I get the minimum possible number for the noisiness. So that noise dimension contains information that's going to tell me how good my fit is. So when I'm doing data science, it tells me how good my fit to my data is. And the way I've defined these two directions along the line and away from the line, they're orthogonal to each other. So I can use the dot product to do the projection to map the data from the xy space onto the space of the line, along the line and away from the line. Which is what we learned to do in the last little segment. Now, if we're thinking about a neural network in machine learning that recognises faces, say, maybe I'd want to make some transformation of all the pixels in a face into a new basis that describes the nose shape, the skin hue, the distance between the eyes, those sorts of things, and discard the actual pixel data. So the goal of the learning process of the neural network is going to be to somehow derive a set of basis vectors that extract the most information-rich features of the faces. So, in this video we've talked about the dimensionality of a vector space in terms of the number of independent basis vectors that it has. And we found a test for independence that the set of vectors are independent if one of them are a linear combination of the others. We've talked more importantly about what that means in terms of mapping from one space to another and how that's going to be useful in data science and machine learning. Let's just take a moment to think about what we've done in this module, because you've worked quite hard, and if all this is completely new to you, you've had to think about a lot of new ideas. We've looked at vectors as being objects that describe where we are in space, which could be a physical space, a space of data, or a parameter space of the parameters of a function. It doesn't really matter, it's just some space. Then we've defined vector addition and scaling a vector by a number, making it bigger or reversing its direction. Then we've gone on to find the magnitude or modulus of a vector and the dot, scalar and vector projection product. We've defined the basis of a vector space, its dimension, and the ideas of linear independence and linear combinations. We've used projections to look at one case of changes from one basis to another for the case where the new basis is orthogonal. So we've done a lot of stuff with vectors, and along the way we've done a bit of thinking about how this will apply to working with data. So hopefully that's been really useful and you've enjoyed giving it all a workout in the exercises and activities. And I'll see you in the next modules where we'll move on to think about the related idea of matrices. So, back at the start of the course, we encountered the apples and bananas problems. How to find the price of things when we only have the total bill. And we've looked at vectors so far, and now we're going to look at matrices. And these are objects that rotate and stretch vectors, but they're also objects that let us solve these sorts of problems. So let's go back to that apples and bananas problem. So I walk into a shop and I buy 2 apples and 3 bananas, and that costs €8. So we're saying 2 apples and 3 bananas cost €8. Now, so I go into the shop on another day and I buy 10 apples and 1 banana, and that costs me, or the shopkeeper charges me, €13. And I want to discover what the price for 1 apple and 1 banana is so I can decide which offers better value or even just predict my bill. Now you might say this is silly. What shop doesn't have sticker prices after all? But actually in business, with complicated products and service agreements and hire purchase, this sort of thing, price discovery, happens all the time. You know, think about what happens when you buy a car, for instance. Now, these are just simultaneous equations, but I can write them down in another way. So the way I would write this down with matrices would be as follows. I'd write it down as this matrix, what I'm now calling a matrix, an object with numbers in 2, 3, 10, 1. AB equals 8, 13. And these things I call matrices. This is a 2 by 2 matrix. This is a 2 row by 1 column matrix. And this is another 2 row by 1 column matrix. And the instruction here is to multiply this out in the following way. So I would multiply the elements in the rows by the elements in the column. So I'd multiply 2 by A plus 3 times B, that's that row times that column, and I'd say that equaled the top row on the right hand side. And I'd do the same for the next row. That row times that column is 10A plus 1B is equal to the row on the bottom on the right hand side. And that looks like my 2 simultaneous equations. But this is really handy because these things, notice, look like vectors. So this matrix operates on this vector to give this other vector, and my question is, what vector transforms to give me this guy on the right? Now, let's look at what happens if I multiply this matrix here by the unit basis vector, the x-axis vector. Well, when I do that multiplication, I'm going to get 2 times 1 plus 3 times 0. And I'm going to get 10 times 1 plus 1 times 0. So I get the vector 2, 10. So what this does is it takes the little unit vector, which we called E1 hat, and it transforms it to another place, which is 2, 10, which is going to be up here somewhere. So that's E1 hat changed, and that's equal to 2, 10. Now, if I do that with the other basis vector, if I do 2, 3, 10, 1 multiplied by 0, 1, then I'm going to get 2 times 0 plus 3 times 1, 10 times 0 plus 1 times 1. I'm going to get 3, 1. So the other basis vector, E2 hat, gets transformed over to 3, 1, which is going to be over here somewhere. So that's E2 changed. I'm using the prime here to indicate changed. 3, 1. So what this matrix does is it moves the basis vectors in some way. It transforms them. It changes the space. So what this matrix 2, 3, 10, 1 does is it's a function that operates on input vectors and gives us other output vectors. And the set of simultaneous equations here is asking, in effect, what vector I need in order to get a transform product at the position 8, 13, in order to get an output of 8, 13. Now, we can see what we mean now by the term linear algebra. Linear algebra is linear because it just takes input values, our a and b, and multiplies them by constants. So everything is linear. And it's algebra, that is, it's a notation describing mathematical objects and a system of manipulating those notations. So linear algebra is a mathematical system for manipulating vectors, and the space is described by vectors. So this is interesting. There seems to be some kind of deep connection between simultaneous equations, these things called matrices, and the vectors we were talking about last week. And it turns out that the key to solving simultaneous equation problems is appreciating how vectors are transformed by matrices, which is the heart of linear algebra. Previously, we introduced the idea of a matrix and related it to the problem of solving simultaneous equations. And we showed that the columns of a matrix just read as what it does to the unit vector along each axis. Now we'll look at different types of matrix and what they do to space, and what happens if we apply one matrix transformation and then another, which is termed composition. Now, because we can make any vector out of a vector sum of the scaled versions of E1 hat and E2 hat, then what that means is the result of the transformation is just going to be some sum of the transform vectors, which I'm calling E1 hat and E2 hat. This is a bit hard to see, but what it means is that the grid lines of our space stay parallel and evenly spaced. They might be stretched or sheared, but the origin stays where it is, and there isn't any curviness to the space. It doesn't get warped. And that's a consequence of our scalar addition and multiplication rules for vectors. So that is, if I write down the matrix as capital A, and the vector it's transforming as R, whatever it was, A, B in our apples and bananas problem, and that gives me some altered version. We said it was 813 before, but I'm going to call it R transformed or R prime. Then we can look at what happens if I do algebra with it. So if I multiply R by some number, just a number, let's call it n, and if I apply A to nr, what I'm saying is that I will get nr prime. And hopefully you can see if I put an n in there, when I multiply it all out, I'm going to get an n in there. Similarly, if I multiply A by the vector r plus s, then I will get ar plus as. So if I get that multiplication, do the whole thing again with another vector and get another vector s and add those two, that will be true. So what I'm saying here is that if I can then think of these as being the original basis vectors, E1 hat and E2 hat, I'll then get some addition of E2 and E1 primed. So if I say that's n e1 hat plus m e2 hat, I'll get a n times e1 hat plus m times a e2 hat, which is n e1 prime plus m e2 primed, which is just the vector sum of some multiple of those. So this space gets transformed, e1 and e2 get moved, and then I can just add up vectors with them. So that's very nice. That means that all of our vector sum rules work. Now, maybe that's a bit confusing, so let's try it with an example. So I've got my matrix A here from my apples and bananas problems of 2, 3, 10, 1, or if we like, the vector 2, 10 and the vector 3, 1. And let's try an example like a vector 3, 2. Now, if I multiply that out, just straightforwardly, as we probably did at school, I've got 2 times 3 plus 3 times 2, so that's 6 plus 6, that's 12. And I've got 10 times 3, which is 30, plus 1 times 2, which is 2, so that's 32. But I could think of that as being 2, 3, 10, 1 times 3 times 1, 0, plus 2 times 0, 1. That is 3 of e1 hat and 2 of e2 hat in a vector sum. Now, I can take the 3 out, so that's 3 times 2, 3, 10, 1 times 1, 0, plus 2 times 2, 3, 10, 1 times 0, 1. And this, we know that this is what happens from e1 hat to get to e1 prime here. So that's 3 times 2, 10. And that's 2 times what happens to e2 hat, and that goes to 3, 1. So that gives us 6 plus 6 is 12, and 30 plus 2 is 32. So it really is true. These rules really do work, and we can think of a matrix multiplication as just being the multiplication of the vector sum of the transformed basis vectors. So pause them for a moment and try that maybe with an example of your own and verify that that really does work, because that's really quite deep. This matrix just tells us where the basis vectors go. That's the transformation it does. It's not a complicated multiplying out thing. We don't need to worry about the mechanics of doing the sum. We can just think of it in terms of what it does to vectors in the space. Now, let's look at some special types of matrices that do simple things, and then we'll think about how to combine them to do complicated things. First, let's think about a matrix that doesn't change anything. A matrix that's just composed of the basis vectors of the space. So 1, 0, and 0, 1. So that, if I multiply it by some vector xy, that's not going to change xy. If I multiply it out, I'm going to get 1 times x plus 0 times y, 0 times x plus 1 times y, xy. So it doesn't change the vector xy. It's just composed of the basis vectors here, and it doesn't change them. And that's called, therefore, the identity matrix. It's the matrix that does nothing and leaves everything preserved, and it's called I. Now, what if I have different numbers along the leading diagonal, something like 3, 0, 0, 2, for instance? Well, that's going to scale the x-axis here by a factor of 3. It's going to go to 3, 0 when I multiply it out. And the y-axis is going to scale by a multiple of 2. It's going to go from 0, 1 to 0, 2. So I've scaled space this way by a factor of 3 and that way by a factor of 2. So my little unit square has gone to being a rectangle from being a square originally. It's scaled up this way 3 times, and this way 2 times. And of course, if the scale factor here was a fraction, if it was a third or something, then I'd have squished space that way instead. I'd have gone that way and made it thinner and taller, something like that. So a fraction then squishes space. The next thing to think about is what happens if I've got a matrix where I scale by, say, -1 here on one of the axes. Well, what that's going to do, so the original axes, is it's going to flip them around. So if I've got 1, 0 here, and 0, 1 being the other axis, of course, then that's going to scale the first one over here to being -1, 0. And of the 0, 2 is going to scale the other axis up to 0, 2 here. So my original little cube goes from here to here. So it's changed in area by a factor of 2, 1 times 2, but it's also flipped over. The x-axis has gone over there. Now what does that mean? Well, if I had previously an axis system where I went using my right hand, from my right hand there, that's my first one, that's my second axis, around, and I went counterclockwise. Now I'm going the other way. Now I've got a left-handed coordinate system, and I go clockwise, so I need to get my left hand out to describe them now. So I've changed the sense of the coordinate system in flipping it over. Now, the other matrix we need to think about, get another pen, is -1, 0, 0, -1. And that inverts everything. It inverts both axes. It takes 1, 0 to -1, 0, and it takes 0, 1 down here to 0, -1. So it flips everything in both coordinates, and that's called an inversion. Another matrix I can think of is 0, 1, 1, 0. That's kind of fun. What that does is it takes I hat 0, 1, 0 here. It takes it to 0, 1, so it takes it to there. 0, 1, that guy goes there. And it takes the other axis, which was there, which was also 0, 1, and it takes it to 1, 0. So what it does is it flips them around. It's like I've put a mirror in at 45 degrees. I could have another mirror, would be 0, -1, -1, 0. And that would take 1, 0 here, and it would make it 0, -1. Would take it down there, 0, -1. And it would take this axis, 0, 1, and it would make it to -1, 0, so it would make it over there. So that's like having a mirror plane in there. And just for completeness, I can think of another two mirrors, and they would be -1, 0, 0, 1. And that flips the x-axis. That's like a vertical mirror. That's that guy. And I can have another one, which would be 1, 0, 0, -1. And that flips the horizontal axis. That flips this guy down, but leaves this guy unchanged. So those are all my mirrors. Another thing I might want to think about are shears. So I wanted to keep E1 hat where it was, 1, 0, but move E2 hat over. So E2 hat is 0, 1. So I wanted to move E2 hat over to here, say. So I wanted to get E2 primed to be equal to 1, 1, say. Now, in which case, I can just write down my matrix, right? I can say that E1 becomes itself, 1, 0, and E2 becomes 1, 1. That would be the transformation matrix for that shear. It would be shearing the unit square over from being a little square to being a little parallelogram here, something like that. Of course, I could shear the x-axis as well. I could do some combination of shears, but that's basically how a shear would look. Now, the last sort of shape change I can do after stretches, inversion, mirrors, and shears is a rotation. If I take E1 hat again, and E2 hat, if I rotate them round, well, E1 hat's going to go round here, so E1 primed is going to be equal to 0, 1. And E2 hat is going to go round to here, and E2 primed is going to become minus 1, 0. So that 90-degree rotation there is going to have the transformation matrix 0, 1, minus 1, 0. And in general, I can write down a rotation by an angle here, let's say an angle here of theta. I can write that down as being cos theta, sine theta, sine theta, cos theta. And I need to put a minus sign in here where positive thetas are actually that way. So we did a rotation by minus 90, so sine of minus 90 is minus 1. And that's a general expression for a rotation in 2D. If I wanted to do it in 3D, I need to think about the axis I was doing it along or around. So if I was rotating about Z, I would preserve all of the Z's for a 3D rotation, something like that. But this isn't really a course about matrix rotations and matrix geometry and so on. That would be something like crystallography. This is a course about data science. So we don't need to think too much about rotations. But it is interesting if we need to do things like transform faces, if we're wanting to do facial recognition. We'll want to do these sorts of stretches and mirrors and shears and rotations to faces to get them all facing like that rather than facing like this or at some funny angle that we had from our camera that was looking at somebody. So we do need to do this in data science on occasion. And that's rotations. So what we've described in this video is we've described all the possible sort of changes we can do with a matrix. So now we need to think about how we do a rotation and then a stretch. And that's the next little part. Now, what's the point of telling about all these different geometric transformations? Well, if you want to do any kind of shape alteration, say of all the pixels in an image of a face or something like that, then you could always make that shape change out of some combination of rotations, shears, stretches, and inverses. That is, if I first apply one transformation, A1, to a vector R, then that makes some first change. Then if I apply another transformation, A2, to the result of that, then I can perform a composition of the two transformations. What I've done is I've performed first A1 and then A2 to R. Now, maybe this isn't so obvious, so let's slow down and do a concrete example. Let's start out with our basis vectors. So we've got our E1 as being 1, 0, and our E2 as being 0, 1. Now let's take our first transformation, A1, as being a 90-degree anti-clockwise rotation. So we're going to work out what happens if we rotate this by 90 degrees anti-clockwise. So E1 comes down to some transformed E1, let's call it E1 prime, of 0, minus 1. So we can put 0, minus 1 in there. And our E2 rotates down here to be some transformed version of E2, which we'll call, which will then be E2 primed, which will be at 1, 0. So then we've got an overall A1, which describes a 90-degree rotation. Now, then let's take another one, another matrix, which also transforms our original basis vectors, our original E1 and E2. And what we'll say is that that is a, let's say, a mirror, say. So that moves, a vertical mirror moves E1 to E1 prime is going to be minus 1, 0. And it's going to leave E2 where it was, if I just reflect vertically. So my transformation A2 now is going to be minus 1, 0, and it leaves the other one the same, 0, 1. Now, let's ask ourselves, what happens if I do A2 to A1? So now I'm going to reflect over the result of doing A1. So E1 prime is actually, when I reflect vertically, going to stay in the same place. And that's going to give me E1, let's say, double prime for doing it twice. And E2 prime is going to reflect over here, and it's going to become E2 double prime is going to be -1, 0. So I'm going to have an overall result of doing A2 to A1, which is going to be what I get. E1 prime I first write down, 0 minus 1, and E2 double prime I'm going to write down, -1, 0. Now, I can work out what that is actually in a matrix way without having to draw it all out by saying A2 to A1 is doing A2, which is -1, 0, 0, 1, to A1's basis vectors. And A1, sorry, A1 there, A1 was 0, -1, 1, 0, which is just the two transform basis vectors, the single primes. And when I do that, I just have to do this matrix to that basis vector, and then this matrix to that basis vector. And what that looks like, if I do that, is I do this matrix to that basis vector, so I do that row times that column, and that gives me -1 times 0 plus 0 times -1, that gives me 0. And that one to that one, so the second row, first column, gives me 0 times 0 plus 1 times -1 gives me -1. And then I do that A2 transformation to the second column now, to the second basis vector of A1. So -1 times 1 plus 0 times 0, and -1 times 1, second row, 0 times 1 plus 1 times 0 gives me 0. So I do the row times the column for all the possible row and column combinations. So that is, in fact, the same thing. So we can have discovered really how to do matrix composition or matrix multiplication, doing one matrix to another transformation matrix. Notice that geometrically we can show that A2 then A1 isn't the same as doing the transformations in the other order, first A1 then A2. So just watch that for a minute. So this one we've done A2, and then what if we then do A1? Well, A1 is a 90-degree rotation, so if we rotate E1 prime, then we find that E1 double prime would be equal to our original E2, that is O1, and our E2 primed, which was just staying where it was, when we rotate that down, then that'll come down to here. That'll come down to 1, 0. So our E2 double prime will be 1, 0. Let's look how that works out matrix-wise. So if we do A1 to A2, A1 was 0, 1, -1, 0. And if we do that to A2, which was -1, 0, 0, 1, then we've got to do that matrix multiplication. And what that's going to give us is 0 times -1 plus 1 times 0, 0. Then this one times this one, -1 times -1 plus 0 times 0 is 1. This row, second column, 0, 0, 1, 1. And second row, second column, -1, 0, 0, 1 gives me 0. So that is, the first column is 0, 1, and the second column is 1, 0. So that isn't the same as doing the operations in the other sequence. You see these minus signs are flipped. In effect, what's happened is this composition, rotating and then flipping over, is the equivalent of reflecting the whole lot, the original basis vectors, in this mirror, and flipping and then rotating round. The effect is I've just flipped my original axes, E1 and E2, which is putting a mirror in here. So doing the two operations in opposites in different sequences doesn't give you the same operation. What we've shown is that matrix multiplication isn't commutative. A2, A1 isn't the same as A1, A2. So we have to be very careful with matrix multiplication. We can do them in any order, meaning they're associative. That is, if we do A3 to A2 to A1, we can do A2, A1, and then do A3, or we can do A3, A2 to A1. So we could do that and then that. Those are the same. They're associative. But we can't interchange the order. We can't swap them around. It's not commutative. So this is interesting. There seems to be some deep connection between simultaneous equations, these things called matrices, and the vectors we were talking about in the last module. And it turns out the key to solving simultaneous equation problems is appreciating how vectors are transformed by matrices, which is the heart of linear algebra. So now we're finally going to find a way to solve the apples and bananas problem. And along the way, we're going to find out about a thing called the inverse of a matrix and a method for finding it. So let's go back to that apples and bananas problem. We said that I walked into a shop and I bought 2 apples and 3 bananas, and that cost $8 or euros or whatever my currency is. Then I went into the shop on another day and I buy 10 apples and 1 banana, and I got charged 13 euros for that. So I wrote that down as a matrix times a vector. And I could call that matrix A, and I could call this vector R, and I could call that its output vector S. So A operates on R and gives me S. And what I want to do is I want to find out what R is, what this vector AB is, in order to give me the right numbers for the output vector. Now, let's just think about this matrix A for a moment. Let's see if I can think of another matrix. I'm going to call this matrix A to the -1, that when I multiply it by A gives me the identity matrix. And I call this matrix here the inverse of A. Because what it does to A is it exactly reverses whatever A does and gives me just the identity. So if I take this equation, AR equals S, if I multiply it on the left by A to the -1 on both sides, well, what I find is that this is just going to be the identity, which is the matrix that does nothing. So when I multiply the identity by R, I just get R. So then I've got R is equal to A to the -1 times S, the inverse matrix of A times S. So if I could find the inverse of A, the matrix when multiplied by A that gives me the inverse, if I can find the inverse of A, I can solve my problem, and I can find what my A and B are, and I've solved my apples and bananas problem. Now, hold that thought about inverses for just a moment. So we said the inverse of A times A was the identity matrix. And we'll just park that up there for a moment. Now, I actually don't have to go all the way to the inverse to solve the apples and bananas problem. I can do it just by substitutions. So let's look at a slightly more complicated problem and see what I mean. So I'm going to take a matrix that looks like this. 1, 1, 3, 1, 2, 4, 1, 1, 2. And I'm going to say that I have apples and bananas and carrots, say. Okay, they're not a fruit, but they're another sort of fruit-like object that we eat. And so I'm saying that I bought 1 apple, 1 banana, and 3 carrots, and that cost me, let's say, 15 euros. Another day I went in, I bought 1, 2, and 4, and that cost me 21 euros. And another day I bought 1, 1, and 2, and that cost me 13 euros. Now, the thing to notice about a system of equations like this is that I can, if I take this row off of another row, I haven't changed anything, right? So I know that an apple, a banana, and 3 carrots cost 15. So if I take an apple, a banana, and 3 carrots and 15 off of the next row, I haven't changed anything really about that row. The same for the third row. So I can make this problem simpler by going and doing that. That's sort of a process of elimination. So if I take, if I call this row 1, row 2, and row 3, if I take row 1 off of row 2, then I would have, take row 1 off of row 2, I'll have 0, 1, 1. If I take row 1 off of row 3, I'll have 0, 0, and -1. I'd still have A, B, and C. And I've taken, on the right-hand side, I've taken row 1. I've taken row 1 off of row 2, so I've taken 15 off of 21, so I'll have 6 left. And I've taken row 1 off of row 3, so I'll have 15 minus 13 is 13 minus 15 is minus 2. So, interesting. So now I can see that actually minus C is equal to minus 2. So I can multiply that row through by minus 1 here. I'll just change pens. And I've got a solution now for C, that C is equal to 2. So that's interesting. Now I've got what it's called a triangular matrix. That is, everything below the body diagonal is 0. And that's a very interesting sort of matrix. I've reduced it to what's called echelon form. All the numbers below the leading diagonal are 0. Now I can do what's called back substitution. I can take my answer for C here and I can put my answer for C back into the first 2 rows. So if I take 1C equals 2, I know that 1 times C here is 2 here, so I can take that off there. And I can do the same, I can take 3 times that off of the first row. So if I take 3 times it off the first row, I'm going to get 1, 1, 0, A, B, C. And I've taken 3 times the first row off of here, so I've taken 3 2's off of here, so I'm going to get 9. If I take that third row off of the second row, I'm going to get 0, 1, 0. And I've got 2 off of 6 is 4. And I can complete, I haven't changed the last row at all. So now I know that C here is equal to 2. I know that if I multiply that row by that column, I've got just B is equal to 4. And I've got A plus B is equal to 9. But I can take my answer for B back off this first row. So I've got then 1, 0, 0, 0, 1, 0, 0, 0, 1. A, B, C. And I've taken 1B, I've taken 4 off of the first row, so that's 5, 4, 2. So my solution here for my apples, bananas and carrots problem is that apples cost €5, bananas cost €4, and carrots cost €2. And that's solved the problem for me. Very nice. So I didn't really have to compute the inverse at all. But I've only found out the answer for this specific set of, this specific output vector. So we said that this was A times R is equal to S. I've only found it for this specific S. If I did the inverse in a general case, I could do it for any S. I could find R for any S. So what I've done here is I've done what's first elimination. I've taken multiples of rows and I've taken them off of each other to get to having a triangular form where the bottom corner here is 0s, and I've just got 1s on the leading diagonal. And then I've done back substitution, well, I've gone back up of putting the numbers for C back into the first 2 rows, the number for B back into the first row, and so on, to get my solution to my problem. And that's very nice. This is actually one of the most computationally efficient ways to solve this problem. And it's going to work every time, and it's very simple to understand. We can do it in relatively few operations, so it's really, really nice. And one thing to notice here is that in doing so, what I've done is I've transformed A into the identity matrix here. This is just the identity matrix. This 1's on the leading diagonals and 0's everywhere else. So this is going to be a key to a way to find the inverse, which is what we'll look at next. Now, let's think about how I can apply this idea of elimination to find the inverse matrix, which solves the more general problem no matter what vector I write down on the right-hand side. So I have a 3 by 3 matrix A and its inverse B, which are multiplied together to give the identity matrix I. So before we had the matrix for A was 1, 1, 3, 1, 2, 4, and 1, 1, 2. And B here is I'm going to actually introduce some notation. I'm going to call B composed of elements B11, B12, B13, where the first digit represents the row. So then I'll have B21. The second digit represents the column. So this would then be B22, and this one would be B row 2, column 3. I'd have B31, B32, B33. So that's the row, and that's the column, equals I. And what we're saying here is that B is actually the inverse of A. So that is, if I multiply A by its inverse, I'll get the identity. And actually the inverse is special because I can do it either way round. I can apply it to A on the right or on the left and it'll still work. Because I times the inverse of A is just the inverse of A, so it doesn't really matter which way round I do it. But I'm just doing it here so that I've got some B's to play with and I don't get confused between my A's and my B's. Right? But for this example, I'm saying B is the inverse matrix of A. Now, notice that this first column of B here is just a vector. It's a vector that describes what the B matrix, the inverse of A, does to space. Actually, it's the transformation that that vector does to the the x-axis, if you like. So, and the identity matrix is just 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So I could write this down. I could write down this A, that big square guy, times B11, B21, B31, and I would get just the first column of the identity matrix, 1, 0, 0. Now, I could solve that by my elimination method and back substitution, just in the way I did before, except I'd be juggling different numbers here. Then I could do it again for the second column of B, the second vector of B, for the second vector of the identity matrix. And I could do it again for the third one. So I'd be doing that in some series, if you like. But, here's the fun bit, I could do it all at once. So I'm going to do this process of elimination and back substitution all at once. I'm going to do it for all the columns on the right-hand side simultaneously. So if I take the first row here and I take it off the second row, as before, I'm going to get rid of this one. And if I take the first row off of the third row, I'm going to get rid of both this one and this one. So if I've got, put the unaltered ones down here, 1, 1, 3. If I take that off of the second row, I'm going to get 0, 1, 1. And if I take that off the third row, I'm going to get 0, 0, minus 1. So on the right-hand side, I'm going to have the unaltered one is 1, 0, 0. And I've taken that off of the second row. So I've got taken 1 off that. That's minus 1, 1, 0. And I've taken that off of the third row as well. So I've got minus 1, 0, 1. And so now I can multiply that third row through by minus 1. And that's in the form I then want. Well, I've got 1s on the leading diagonal and 0s below it. So when I multiply that through by minus 1, I get a plus there and a minus there. Now I can substitute that third row back into the second and first rows. So I can take one of it off of the second row and I can take 3 of it off of the first row. So now the unaltered one is the bottom one, 1, 0, minus 1. If I take one of those off of the second row, then I've got 0, 1, 0 there. I'm going to take that off of the second row over here. So if I take 1 off of minus 1, I get minus 2. Take 0 off 1, I've got 1. Take minus 1 off of 0, I'm effectively adding 1. Then I want to do that again to the first row. I want to take 3 of them off to make this guy here 0. So I've got then 1, 1, 0 there. And I want to take 3 of these off of the first row. So I take 3 off of 1, gives me minus 2. Take 0 off there. And I've got to take 3 of minus 1 off of 0, so that gives me plus 3. So we're nearly there. I've just got this irritating one here. I've got to take this row off of this row, and I'll be home. So if I take my third row is unaltered. Let's put some brackets in. My third row is unaltered. My second row is going to be unaltered. 1, 0, minus 1, minus 2, 1, 1. If I take that row off of that row, then that altered one gives me 1, 0, 0. Take the 1 off there. Take this row off of this row, minus 2 off of minus 2. I've got to take minus 2 off of minus 2, so that gives me 0. Got to take 1 off of 0, that gives me minus 1. And I've got to take 1 off of 3, which gives me 2. So that's my answer. So now I've got the identity matrix here for A, in effect. I've transformed A till it's the identity matrix. I've got my B matrix, which I haven't really changed. And my identity matrix over here I've changed. So now I've got an identity times a B matrix is equal to this guy. So the identity times something is just itself. So this is, in fact, my answer for the inverse of A, or B. So I've found a way here to find the inverse of a matrix just by doing my row elimination and then my back substitution, which is really cool. So what we've done is we've found an inverse matrix, A to the minus 1 here, and if we multiply A times A to the minus 1, we'll get the identity. And prove to yourself, if you like, just pause for a moment and have a go at doing that for yourself and verify that that times that does in fact give you the identity matrix. And in school you probably did this a different way, but computationally this way is much easier, particularly when you come to higher dimensions, 100 rows and columns or something like that. There are computationally faster methods of doing what's called a decomposition process. And in practice, what you do in any program that you write is you simply call the solver for your problem, or the function, something like inv A, or whatever it is, and it will pick the best method by inspecting the matrix you give it and return the answer. But the point here is to show how these problems are actually solved in a computer, and also we'll observe some of the properties of these methods in different circumstances that will affect the sorts of things we want to do when solving these sorts of problems. So what we've done here is figured out how to solve both sets of linear equations in the general case by a procedure we can implement in a computer really easily. And we've made that general by finding a general method to find the inverse of a matrix in the general case for whatever is on the right-hand side of our system of equations. And hopefully that's really satisfying and really nice. In the final video in this module, we're going to look at a property of a matrix called the determinant, and what happens when the matrix doesn't have linearly independent basis vectors, picking up on the basis vectors we looked at in the last module. Let's go back and look at a simple matrix like A0, 0, D. What this matrix does is it scales space. So if we have our original basis vectors, E1 hat and E2 hat, it scales them out by a factor of A in this direction to A0, and by a factor of D in this direction to 0D. And we call those E1 prime and E2 prime. Now see what I've done to the space. It was originally this size, 1 by 1. And what I've done is I've scaled the space, every vector in the space, by a factor of A this way and by a factor of D this way. And therefore I've scaled the space by a factor of AD. All areas in the space, everything's got bigger by a factor of AD. And I call that the determinant of the transformation matrix. Now, if I instead have a matrix which is A0, BD instead, the same but with a B, what that does is E1 hat stays as it was, it's scaled by a factor of A, but E2 hat goes somewhere different. So E1 hat goes to A0, but E2 goes to BD, somewhere like this, BD. Now, see what's happened to the space. I've gone from being something like this to being something like this. I've made a parallelogram. But the area of the parallelogram is still AD. It's its base times its perpendicular height. So the determinant is still AD of this transformation matrix. Now, if I have a general matrix, A, C, B, D, then it turns the original unit square into a parallelogram like this. It moves this vector to here, this vector to here. Then to find the area of this parallelogram, I'm going to have to do a bit of maths. So I'm going to do that, and then we'll have a look at it in a moment. So I've done the maths, and it's here. And you can do the geometry and puzzle it out for yourself and pause it if you like to verify that I'm correct. But the area of the parallelogram here is actually AD minus BC. And I'm going to denote the operation of finding that area with vertical lines like this, and call that finding the determinant of A, which you probably saw in school. Now in school, when you looked at matrices, you probably saw that you could find the inverse of a matrix like A, B, C, D by flipping the terms on the leading diagonal and taking the minus of the off-diagonal terms for a 2 by 2. So let's do that and see what we get. So when we multiply that out, we get AD minus BC. Interesting. Then on this element here is A minus B minus plus BA. And so we've got A minus B plus BA, so that's 0. When we do this term, we get CD minus CD. And when we do this term here, we get CB times minus B, so that's minus BC, plus AD, so that's AD minus BC. Interesting. So that's the determinant. So if I multiply by 1 over the determinant, AD minus BC, then these terms will become 1, and I'll get the identity matrix. So if this was the matrix A, and I think of this and this together as being A to the minus 1, then I've got this is in fact, when I pre-multiply by 1 over the determinant, is in fact the inverse of A. So we proved here that that determinant, that inverse you learned in school, is in fact correct. But the interesting thing is that this determinant there, this amount that it scales space, if we then take this matrix when we do the flipping around, we haven't changed its scaling of space. We need to undo that scaling and bring it back down to a scale of 1. So the determinant here is what we need to divide the inverse matrix by in order for it to properly be an inverse. Now we could spend another video looking at the extension of the idea of row echelon form to find out how to find determinants in the general case computationally. But this is both tricky to show and it's kind of pointless. Knowing how to do the operations isn't a useful skill anymore because we just type det A into our computer. And Python or MATLAB will do it for us. From a learning perspective, it doesn't add much to row echelon. Row echelon does actually, which is why we went through it. I'm not going to teach you how to find determinants in the general case. If you want to know, look up QR decomposition and then follow that through, and that's how computationally you go and find it out, or in a linear algebra textbook is the other place to look. That's how you do it in the general case. Now, let's think about this matrix A here. It transforms E1 and E2 hat to 2 points on the same line. It transforms E1 hat to 1, 1, and it transforms E2 hat from there over to 2, 2. And they're both points on the same line. They're just a multiple of each other. They're not linearly independent. What this matrix in fact does is it transforms every point in space on a line. And notice that the determinant of that matrix is going to be 0. If I take AD minus BC, determinant of A is 0, because the area of any area has gone onto a line, and therefore that area is 0. So however you compute it, either geometrically or computationally, you get a determinant of 0. So if I had a 3 by 3 matrix with a similar situation describing a 3D space, and if I had the same position where one of the new basis vectors was just a linear multiple of the other two, it wasn't linearly independent, then that would mean the new space was either a plane, or if there was only one independent basis vector, a line like we have here. In either case, the volume enclosed would be 0, so the determinant would be 0. Now let's turn back to our row echelon form and apply that idea. Let's take this set of simultaneous equations, say. You can see that the third row is just the sum of the first two. So row 3 is equal to row 1 plus row 2. And you can see that column 3 is just given by 2 of column 1 plus column 2. If you want to pause for a moment to verify that, but it really is true. So this transformation matrix doesn't describe 3 independent basis vectors. One of them is linearly independent on the other 2. So this doesn't describe a new 3D space. It collapses into a 2D space. So let's see what happens when I try to reduce this to row echelon form. If I take off the first row from the second, okay, so far so good. I've got that, and my ABC stays the same. And I take the first one off the second one. So I've got 12, take 12 off 17, I've got 5. If I then take the first and second ones off the third one, I've now got zeros everywhere here. And if I do that on here, I take 12 and 17 off 29, I get 0 here. So now I've got 0c equals 0, which is sort of true, but not useful. There are an infinite number of solutions for c, in effect. Any value of c would work. So now I can't solve my system of equations anymore. I don't have enough information. So if we're thinking about this from a sort of solving simultaneous equations point of view, my mistake was when I went into the shop to buy apples and bananas and carrots, the third time I went in, I just ordered a copy of my first 2 orders. So I didn't get any new information. And I don't have enough data, therefore, to find out the solution for how much individual apples and bananas and carrots costs. So what we've shown is that where the basis vectors describing the matrix aren't linearly independent, then the determinant is 0, and that means I can't solve the system of simultaneous equations anymore. Which means I can't invert the matrix because I can't take 1 over the determinant either. And that means I'm stuck. This matrix has no inverse. So there are situations where I might want to do a transformation that collapses the number of dimensions in a space, but that will come at a cost. Another way of looking at this is that the inverse matrix lets me undo my transformation. It lets me get from the new vectors to the original vectors. And if I've dumped a dimension by turning a 2D space into a line, I can't undo that anymore. I don't have enough information because I've lost some of it during the transformation. I've lost that extra dimension. So in general, it's worth checking before you propose a new basis vector set and then use a matrix to transform your data vectors, that this is a transformation you can undo by checking that the new basis vectors are linearly independent. So what we've done in this last video, in this module, is look at the determinant, how much we grow space. We've also looked at the special case where the determinant is 0, which means that the basis vectors aren't linearly independent, which means the inverse doesn't exist. In this first module on matrices, what we've done so far is define what a matrix is as something that transforms space. We've looked at different archetypes of matrices like rotations and inverses and stretches and shears, and how to combine them by doing successive transformations. Then we've looked at how to solve systems of linear equations by elimination and how to find inverses. And then finally we've looked at determinants and linear independence. So, what we've done in this last video in this module is look at the determinant, how much we grow space, the area change. We've also looked at the special case where the determinant is 0 and found that that means that the basis vectors aren't linearly independent and that means that the inverse doesn't exist. So in this first module on matrices, what we've done is define what a matrix is as something that transforms space. We've looked at different archetypes of matrices like rotations and inverses and stretches and shears, and how to combine them by doing successive transformations, matrix multiplication or composition. Then we've looked at how to solve systems of linear equations by elimination and how to find inverses. And then finally we've looked at determinants and linear independence. And next week we'll carry on and look at matrices in some more detail. Now, there's an important other way to write matrix transformations down, which is called the Einstein summation convention. And that writes down what the actual operations are on the elements of a matrix, which is useful when you're coding or programming. It also lets us see something neat about the dot product that I want to show you, and it lets us deal with non-square matrices. When we started, we said that multiplying a matrix by a vector or with another matrix is a process of taking every element in each row in turn, multiplying it with the corresponding element in each column in the other matrix, and adding them all up and putting them in place. So let's write that down just to make that concrete. So I'm going to write down a matrix A here, and I'm going to give it elements. A is an n by n matrix, and I'm going to give it elements A1, 1, A2, 1, all the way down to AN1, and then A1, 2, all the way across to A1n. And then I'll have A2, 2 here, all the way across, all the way down, until I fill it all in, I've got ANN down here. So the first suffix on this matrix, or first suffix on all of these elements in the matrix, is the row number, and the second one is the column number. Now if I want to multiply A by another matrix B, and that's also going to be an n by n matrix, and that'll have elements B1, 1, B1, 2, across to B1n, and down to Bn1, and across to Bnn, dot, 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 dot. If I multiply this together, I'm going to get another matrix, which I'll call AB. And then what I'm going to do is I'm going to take a row of A, multiply it by the elements of a column of B, and put those in the corresponding place. So let's do an example. So if I want element, let's say AB, element 2, 3, I'm going to get that by taking row 2 of A, multiplied by column 3 of B. So I'm going to take row 2 of A, that's going to be A21, A22, and all the others up to A2n. And I'm going to multiply it by column 3 of B, so that's B13, B23, all the way to Bn3. And I'm going to add all those up. And I'll have a dot, dot, dot in between. So that's going to be this element, row 2, column 3 of AB. Now in Einstein's convention, what you do is you say, well, okay, this is the sum over some elements j of Aij, Bj, k, where, so if I add these up over all the possible j's, I'm going to get A11, B11 plus A12, B21, and so on, and that's for I and k is 1. And I'm going to then go around all the possible i's and k's. So what Einstein then says is he then says, well, okay, if I've got a repeated index, I just won't bother with the sum, and I'll just write that down as being Aij, Bjk, and that's equal to this, the product ABIK. So ABIK is equal to AI1B1k plus AI2B2k plus I3B3k, and so on, until you've done all the possible j's. And then you do that for all the possible i's and k's, and that will give you your whole matrix for AB, for the product. Now this is quite nice. If you were coding, you just run 3 loops over I, j, and k, and then use an accumulator on the j's here to find the elements of the product matrix AB. So the summation convention gives you a quick way of coding up these sorts of operations. Now we haven't talked about this so far, but now we can see it. There's no reason, so long as the matrices have the same number of entries in J, that we can't multiply them together, even if they're not the same shape. So we could multiply a 2 by 3 matrix, something with 2 rows and 3 columns, so 1, 2, 3, 1, 2, 3, by a 3 by 4 matrix, 3 there and 4 there, so it's got 1, 2, 3, 4 times. And when I multiply those together, I'm going to go that row times that column. I've got the same number of j's in each case. So, and then I'm going to be able to do that for all of the possible columns. So I'm going to get something with 4 columns. And when I'm going to be able to do that for the 2 rows here, I'm going to be able to do that row times that one. So I'm going to get a 2 by 4 matrix out. So it's going to have 1, 2, 3, 4, 1, 2, 3, 4. So I can multiply together these non-square matrices if I want to, and I'll get, in the general case, some other non-square matrix. I'm going to have the number of rows of the one on the left and the number of columns of the one on the right. Now, all sorts of matrix properties that you might want, inverses and so on, determinants, all start to get messy and mucky, and you sometimes can't even compute them when you're doing this sort of thing. But there are times when you want to do it. And the Einstein summation convention makes it very easy to see how you do it and how it's going to work. As long as you've got the same number of j's, you're good. You can multiply them together. Now, let's revisit the dot product in light of the summation convention. So if we've got two vectors, let's call them u and v. And we'll say u is a column vector having elements ui, and v is another column vector having elements vi. And when we dot them together, what we're doing is we're multiplying u1 by v1, adding u2, v2 all the way up. So in the summation convention, that's just ui, vi, where we repeat over all the i's and add. But this is just like writing U as a row matrix, pushing U over from being a vector to being a matrix with elements U1, U2, all the way up to UN, and multiplying it by another matrix, V1, V2, all the way up to Vn. That's the same, that matrix multiplication is the same thing as the dot product. I just push the U vector over, and then my dot product is just like doing a matrix multiplication, which is sort of neat. So there's some equivalence between a matrix transformation, a matrix multiplication, and the dot product. So let's look at that. Now, if I take a unit vector here, let's call him u hat, with components u1 and u2. And let's imagine what happens if I dot him with the axis vectors. So if I've got an axis here, E1 hat, which would be 1, 0, and I've got another axis here, E2 hat, which will be 0, 1. Now let's think about what happens when I dot U hat with E1, when I do the projection of U hat onto E1. So when I drop U hat down onto the axis here, when I do the projection of U hat onto E1, I'm going to get a length here just of U1, just of the x-axis element of U hat. Now what happens if I drop, project E1 onto U hat? Well, I'm then going to get this projection, and I'm going to get a length here, this projected length here. Now, the fun thing is, we can actually draw a line of symmetry here through these two projections where they cross. And this little triangle and this little triangle are actually the same. You can go and do a bit of geometry and prove to yourself that that's true. So this length here, this projection, there, that projection, is the same length as that projection, which is implied by the dot product. If I dot E1 with U hat, when I do this multiplication here, it's symmetric. I can flip them around and I get the same answer. So this shows geometrically why that's true. And if we repeat this with the other axes, with E2 here and any other axes there are, then we'll also get the same results. So this is why the projection is symmetric and the dot product is symmetric, and why projection is the dot product. So there's this connection between this numerical thing, matrix multiplication, and this geometric thing, projection, which is quite beautiful and mind-blowing, really. And that's why we talk about a matrix multiplication with a vector as being the projection of that vector onto the vectors composing the matrix, the columns of the matrix. So what we've done in this video is look at the summation convention, which is a compact and computationally useful but not very visual way to write down matrix operations. And that's opened up looking at funny shaped matrices, and that's opened up re-examining the dot product here. So that's really nice. We've said before that the columns of a transformation matrix are the axes of the new basis vectors of the mapping in my coordinate system. We're now going to spend a little while looking at how to transform a vector from one set of basis vectors to another. Let's say I have two new basis vectors that describe the world of Panda Bear here, and Panda's world is orange. So Panda's got first a basis vector there, and then another basis vector there, say. And let's say in my world, Panda Bear's basis vectors are at 3, 1 and are at 1, 1. And my basis vectors here are E1 hat equals 0, 1 for E2 hat, and E1 hat is equal to 1, 0. So those are my basis vectors, and the orange ones are Panda's basis vectors. Now, and so Panda's basis vectors, the first one for Panda is his 1, 0, and the second one is 0, 1 in Panda's world. So Bear's basis vectors are 3, 1 and 1, 1 in my blue frame. That is, I can write down Bear's transformation matrix as 3, 1, 1, 1. Now, let's take some vector I want to transform. Let's say that vector is, in Bear's world, is the vector a half of 3, 1 in Bear's world. So it's 3 over 2, 1 over 2. So the instruction there is do 3 over 2 of 3, 1, and then do 1 over 2, a half of 1, 1, in my frame, if you like. So in my world, that's going to give me the answer of 3 times 3 over 2 plus 1 times 1 over 2 is 9, 10 halves, which is 5. And 1 times 3 over 2 plus 1 times a half, so that's a total of 2. So that's the vector 5, 2 in my world. 5, 2. Those two are the same things. So this is Bear's vector, and this is my vector. So this transformation matrix here are Bear's basis in my coordinates, in my coordinate system. So that transforms Bear's vectors into my world, which is a bit of a problem. You know, usually I'd want to translate my world into Bear's world. So we need to figure out how to go the other way. So my next question is, how do I perform that reverse process? Well, it's going to involve the inverse. So if I call Bear's transformation matrix B, I'm going to want B inverse, which b to the minus 1. And the inverse of this matrix, well, it's actually pretty easy. We can write down the inverse of that matrix pretty easily. It's going to be a half of 1, 3, flip the elements on the leading diagonal, and put a minus on the off-diagonal terms. And we can see the determinant of that's 3 minus 1 is 2, so we divide by the determinant as a half. So that's going to be b to the minus 1. And that's the my basis vectors in Bear's coordinates. So that's my basis in Bear's world. So my 1, 0 is going to be a half of 1 minus 1 in Bear's system, and my 0, 1 is going to be a half of minus 1, 3 in Bear's system. And we can verify that this is true if we take this guy, a half 1 minus 1, and compose it with Bear's vectors. We've got 1 plus minus 1 of those is going to give me 3 plus 1 is 3 minus 1 is 2, 1 minus 1 is 0, so that's 2, 0, halve it, gives you 1, 0. So that really does work. If I take a half 1 minus 1 of Bear's vectors, I get my unit vector. Okay, so that really does do the reverse thing. So then if I take my vector, which was 5, 2, and then I do that sum, I should get the world in Bear's basis. So I've got 5 times a half minus a half, using that guy, plus 2 times minus 1, 3, and that will give me a half of 3, 2 when I multiply it all out. And if I do the same thing here, I've got 5 times 1 minus 1 times 2 gives me 3 over 2, gives me 3 over 2. It all works out. If you do it that way, or if you do it that way, you still get that answer. So that's Bayes' vector, again, which is the vector we started out with. So that's how you do the reverse process. You need to, if you want to take Bayes' vector into my world, you need Bayes' basis in my coordinate frame. And if you want to do the reverse process, you want my basis in Bayes' coordinate frame. That's probably quite counterintuitive. So let's try another example where this time Bayes' world is going to be an orthonormal basis vector set. So here's our basis vectors at 1, 0 and 0, 1 in my world in blue. And Bayes' world is in orange. Bayes' world has 1, 1 times, and I've made it unit length, so it's 1 over root 2, and minus 1, 1. Again, the unit lengths are 1 over root 2, so they're those two. And those you can do a dot product and verify that those two are at 90 degrees to each other. And they're Bayes' vectors 1, 0 and 0, 1. So then I can write down Bayes' transformation matrix that transforms a vector of Bayes. Now, if I've got the vector in Bayes' world that's 2, 1, then I can write that down. And I will therefore get the vector in my world. So when I multiply that out, what I get is I'll get 1 over root 2 times 2 minus 1, which is 1. And then 1 times 2 plus 1 times 1 gives me 3. So in my world, the vector is, as I've written down, 1 over root 2 times 1, 3. So if I want to do the reverse transformation, I need b to the minus 1. And b to the minus 1 is actually quite easy because this is an orthonormal basis. The determinant of this matrix is 1, so it all becomes quite easy. So I just get 1 over root 2, keep the leading terms the same, flip the sign of the off-diagonal terms because it's a 2 by 2 matrix, so it's really simple. And if you go and put that in, if you say, if I take 1 over root 2 times 1 minus 1, so I take one of those plus one of those, multiplied by root 2, I do in fact get 1, 0, and the same for 0, 1. It all works. So then if I take the vector in my world, this vector in my world, which is 1, 3, and multiply it out, then what I get is the vector in Bayes' world. So that's 1 plus 3, which is 4, minus 1 plus 3 is 2, and I've got 1 over root 2 times 1 over root 2, so that's a half. So in Bayes' world, this vector is 2, 1, which is what we originally said, so it really works. Now this was all prep really for the fun part, which is, we said before in the vectors module that we could do this just by using projections if the new basis vectors were orthogonal, which these are. So let's see how this works with projections. So let's try it with projections. What we said before was that if I take my version of the vector and dot it with Bayes' axis, so the first of Bayes' axes is that in my world, then I will get the answer of the vector in Bayes' world. So that gives me 1 over root 2 times 1 over root 2, which is a half, of 1 plus 3, which is 4. So that gives me 2. And that's going to be the first component of Bayes' vector because it's the first of Bayes' axes. And I can do it again with the other of Bayes' axes. So that's 1 over root 2, 1, 3. That's the vector in my world with the other of Bayes' axes, which is 1 over root 2 times minus 1, 1. And when I do that dot product, what I'll get, the 1 over root 2's will multiply to give me a half again, and I've got 1 times minus 1 plus 3 times 1 is a total of 2, which is 1. And that's Bayes' vector, notice, 2, 1. So I've used projections here to translate my vector to Bayes' vector just using the dot product. Now remember, with the vector product, what I'd have to do is I'd have to remember to normalise when I did the multiplication by Bayes vectors. I'd have to normalise by their lengths, but in this case their lengths are 1. So it's actually really easy. So we don't have to do the complicated matrix maths. We can just use the dot product if Bayes vectors are orthogonal. Now there is one last thing. If you try this with the example we did before, with Bayes vectors of 3, 1 and 1, 1, so before we had those being Bayes vectors, if you try the dot product with those, because they're not orthogonal to each other, it won't work. And give it a go for yourself and verify that it really won't work, that they need to be orthogonal for this to work. If you have them not being orthogonal, you can still do it with the matrix transformation, you just can't do it with the dot product. Now, let's look at how we do the transformation of a vector that's already in a change basis. Last time we looked at Bayes basis. Bayes basis had a first axis of 3, 1 and a second axis of 1, 1. And let's say I have a vector xy defined in Bayes basis. And say I want to transform it by doing something like a rotation of 45 degrees. But the problem is, I don't know how to write a 45-degree rotation in Bayes' funny coordinate system. I only know how to write down a 45-degree rotation in my normal 1001 system. So in my system, which is 1001, a 45-degree rotation rotates 10 up like that. So it becomes, if it's still a unit vector, 1 over root 2, 1 over root 2. That is a normalised 1, 1. And it takes 01 round to minus 1 over root 2, 1 over root 2. That is that 45 degrees there, that 45 degrees there. So I can write down the rotation in my notation, let's call it R, being a 45-degree rotation, as being 1 over root 2 times 1, 1 minus 1, 1. That's what a 45-degree rotation is in my world. So what I need to do is first transform the vector xy into my basis. And I do that by multiplying it by b, right? Then I can apply my nice sensible rotation r to that vector that's now in my basis. So what I get here when I do rb, I've got the vector in my coordinate frame. Now, the problem is, Bayer doesn't care about my world. He wants to get the rotation in his basis. So then I have to transform the resulting vector back into Bayes' basis. And I do that by applying b to the minus 1. And b to the minus 1 I get by flipping the terms on the leading diagonal, taking minus the off-diagonal terms, and dividing by the determinant here, which is 2. So I multiply by a half. So that then gives me the vector back in Bayes' frame. So overall what I've done is I've done b to the minus 1 times r times b, and what that's giving me is it's giving me the rotation in Bayes' coordinate system, which is really neat. So now all we have to do is do the sums. And when we do that, RB gives us this, and b to the minus 1 RB gives us this. I've written them down there, so pause and ponder if you want to verify those on your own. So this is what a 45-degree rotation looks like in Bayes' coordinate system. Notice that it's completely different to the one in my standard basis. It isn't very easy necessarily or obvious to intuit just out of your head. You have to do the calculation. So if you want to do some kind of transformation but in some funny basis, this equation b to the minus 1 rb is going to be very useful. To step back here, the point is that if we want to transform to non-orthonormal coordinate systems, then the transformation matrices also change. And we have to be mindful of that. And this is the sort of algebra you see all the time. We've got the transformation matrix R wrapped around by b to the minus 1 that does the translation from my world to the world of the new basis system. So thanks a lot, Bear. You really helped us out to understand all this stuff. So what we've done in these two videos is we've looked at how the numbers in a vector change when we change the basis. And we thought about the coordinate systems and how to do transformations in non-orthogonal coordinate systems. It's been quite hard work, but this really sets us up, for example, in principal component analysis, to operate in different basis systems. Now, it's going to be really useful if we can make a transformation matrix whose column vectors make up a new basis, all of whose vectors are perpendicular or what's called orthogonal to each other. In this video, we're going to look at this and why this is. But first, I want to define a new operation on a matrix called the transpose. This is where we interchange all the elements of the rows and columns of the matrix. So I denote the transpose as a T, and I say that the ijth element of the transpose of A is equal to the elements on the opposite diagonal, AJI. So if I had a matrix like 1, 2, 3, 4, and I wanted to know its transpose, then I'd interchange the elements that are off the diagonal. So the 1 and the 4 stay where they are, because if I and j were the same, 1, 1, 1, 1, they would stay the same. The same for 2, 2. But the element 1, 2 interchanges with element 2, 1. So they go like that. So 1, 2, 3, 4 becomes, when I transpose it, 1, 3, 2, 4. Now, let's imagine that I have a square matrix of dimension n by n that defines a transformation with a new basis, and the columns of that transformation matrix A are some vectors A1, A2, that are the basis vectors in the new space, right, as we've said before. And I'm going to make this a special matrix where I impose the condition that these vectors are orthogonal to each other and they have unit length. That is, AI dotted with AJ is equal to 0 if I isn't equal to j, that is, they're orthogonal, and it's equal to 1 if I is equal to j, that is, they're of unit length. Now, let's think about what happens if I multiply this matrix on the left by A transpose. So A transpose is going to be given by just flipping the rows and columns of so all of the elements across the leading diagonal of A. So that is, I'm going to have A1 is going to become a row, A2 is going to become the next row, all the way down to AN, because I flip all of the elements across the leading diagonal. So when I multiply AT by A, let's see what happens. It's going to be quite magical. So if I get AT times A, then I'm going to get, well, the first element here is going to be the first row times the first column, and that's A1 times dotted with A1, and that's 1. The second element here, the first row, the second column, is A1 dotted with A2, and that's 0. And A1 dotted A3 all the way up to AN is going to give me a whole series of zeros, where this guy, remember, is AN. And then when I do the second row and the first column, I'm going to get another 0. And when I do the second row and the second column, I'm going to get a 1. Second row, third column, 0, all the way across. And when I do the third one, I'm going to get the same again. I'm going to get 0, 0. It's all going to be zeros except A3 times A3, and that's going to be that element all the way across. And what I'm gradually building up here is I'm building up the identity matrix. So what I found is that AT times A gives me the identity matrix. And what that means is that AT is a valid inverse of A, which is really kind of neat. A set of unit length basis vectors that are all perpendicular to each other are called an orthonormal basis set. Orthonormal. And the matrix composed of them is called an orthogonal matrix. One thing also to know about an orthogonal matrix is that because all the basis vectors in it are of unit length, it must scale space by a factor of 1. So the determinant of an orthogonal matrix must be either plus or minus 1. The minus 1 arises in the new basis if the new basis vector set flips space around, that is, they sort of invert it, they make it left-handed. Notice that if AT is the inverse, then I should be able to post-multiply A by AT and get the identity. That is, I can do this either way around. Which also means, by the same logic, that the rows of the orthogonal matrix are orthonormal, as well as the columns, which is kind of neat. And we saw in the last video that actually the inverse is the matrix that does the reverse transformation. So the transpose matrix of an orthonormal basis vector set is itself another orthogonal basis vector set, which is really neat. Now remember that in the last module on vectors, we said that transforming a vector to a new coordinate system was just taking the projection or dot product of that vector, so say that's the vector, with each of the basis vectors. So basis vector this one, basis vector that one, and so on, so long as those basis vectors were orthogonal to each other. If you want to pause and think about that for a moment, in the light of all we've learned about matrices, just look and think about this for a moment. Now, in data science, what we're really saying here is that wherever possible, we want to use an orthonormal basis vector set when we transform our data. That is, we want our transformation matrix to be an orthogonal matrix. That means the inverse is easy to compute. It means the transformation is reversible because it doesn't collapse space. It means that the projection is just the dot product. Lots of things are nice and pleasant and easy. If I arrange the basis vectors in the right order, then the determinant is 1, and that's an easy way to check. And if they aren't, just exchange a pair of them, and actually then they will be a determinant 1 rather than minus 1. So what we've done in this video is look at the transpose, and that's led us to find out about the most convenient basis vector set of all, which is the orthonormal basis vector set, which together make the orthogonal matrix whose inverse is its transpose. So that's really cool. We've said several times now that life is much easier if we can construct an orthonormal basis vector set, but we haven't talked about how to do it. So in this video we'll do that, starting from the assumption that we already have some linearly independent vectors that span the space we're interested in. So let's say I have some vectors v, and I've got a whole group of them, v1, v2, all the way up to vn, and there's enough of them that they span the space. So let's sort of sketch them out. So I've got, say, a v1 here, a v2 over here, another v3 down there somewhere. And they're linearly independent. Let's assume that. If you want to check linear independence, you can write down their columns in a matrix and check the determinant isn't 0. If they were linearly dependent, that would give you a 0 determinant. But they aren't orthogonal to each other or of unit length. My life would probably be easier if I could construct some orthonormal basis somehow. And there's a process for doing that, which is called the Gram-Schmidt process. The Gram-Schmidt process, which is what we're going to look at now. Let's take arbitrarily the first vector in my set, call him v1. So we take v1. In this first step, let's call him she actually, she gets to survive unscathed. So we're just going to normalize her, and we're going to say that my eventual first basis vector e is going to be equal to v1 just normalized to be of unit length, just divided by its length. So e is just going to be some normalized version of v1. And I can now think of v2 as being composed of two things. One is a component, and let's do this in orange, a component that's in the direction of E1, like that, plus a component that's perpendicular to E1. And but the component that's in the direction of E1 I can find by taking the vector projection of V2 onto E1. So I can say V2 is equal to the vector projection of V2 onto E1, dotted together. And if I want to get that actually as a vector, I'll have to take E1 which is of unit length. I'd have to divide by the length of E1, but the length of E1 is 1, so you can forget it. And if I take that off of V2, then I'll have this guy, and let's call him U2. So I can then say that U2, so plus U2, so I can then rearrange this and say that U2 is equal to V2 minus this projection, V2 dot E1 times E1. And if I normalize U2, if I take U2 divided by its length, then I'll have a unit vector which is going to be normal to V1. So if I take a normalized version of that, let's say it's that will be E2. And that will be at 90 degrees to E1, so it'll actually be there, E2, once I've moved it over. And that will be another unit length vector, normal to E1, so that's the first part of taking an orthonormal basis. Now, my third vector, V3, isn't a linear combination of V1 and V2, so V3 isn't in the plane defined by V1 and V2. So it's not in the plane of E1 and E2 either. So I can project V3 down, let's say something like that, onto the plane of E2 and E1, and that projection will be some vector in the plane composed of E2s and E1s. So I can then write down that V3 minus V3 dotted with E1, E1s, that's going to be the component of V3 that's made up of E1s, minus V3 dotted with E2, E2s, that's the component of V3 that's made up of E2s. And then all that's going to be left is going to be this perpendicular guy there. So that's going to be a perpendicular vector, which we'll call U3, which is perpendicular to the plane. Now, it's some funny 3D space, so this diagram gets quite messy. And then if I normalize U3, divide by the length of U3, then I'll have a unit vector which is normal to the plane, normal to the other two. So now I've got an orthonormal basis for E1, E2, E3. And I can keep on going through all the VNs until I've got enough orthonormal basis vectors to complete the set and span the space that I originally had. But I've gone from a bunch of awkward, non-orthogonal, non-unit vectors to a bunch of nice orthogonal unit vectors, an orthonormal basis set. So that's how I construct an orthonormal basis set and make my life easy so that my transformation vectors are nice, my transformation matrices are nice, sorry, and so that I can do the transposes, the inverse, and all those lovely things. So I can use dot product projections for the transformations, all those nice things that are going to make my life very, very much nicer whenever I'm doing any transformations or rotations or whatever it is I want to do with my vectors. So that's going to be really nice. This is a really nice process. And what we'll do next is we'll apply this, we'll try this for an example and see how it rolls, and then apply that to doing a transformation. Okay, so let's put all this together. Let's use our transformations knowledge and our basis knowledge in order to do something quite tricky and see if we can't actually make our life quite simple. What I want to do here is know what a vector looks like when I reflect it in some funny plane. For example, the way this board works, when I write on the light board here, if you're looking at it, all the writing would appear mirrored. But what we do to make that work is we reflect everything in post-production, left, right, and then everything comes out okay. The example we're going to do here asks what the reflection of Bear, say, something in a mirror, would look like to me if the mirror was off at some funny angle. Now, my first challenge is going to be that I don't know the plane of the mirror very well. But I do know two vectors in the mirror, 1, 1, 1, and 2, 0, 1. And I've got a third vector, which is out of the plane of the mirror, which is at 3, 1, minus 1. That's my third vector. So I've got vectors v1, v2, and v3. And these two guys are in the plane of the mirror. We could draw it something like v1 and v2, and they're in some plane like this, and v3 is out of the plane. So I've got v3 there, V1 and V2. So first let's do the Gram-Schmidt process and find some orthonormal vectors describing this plane and its normal V3. So my first vector E1 is going to be just the normalized version of V1. V1 here is of length root 3, 1 squared plus 1 squared plus 1 squared, all square rooted. So it's going to be 1 over root 3 times 1, 1, 1. That's a normalized version of V1. So then we can carry on, and I can find U2 is equal to V2 minus some number of E1s. So that's going to be, then the sum number is going to be the projection of V2 onto E1 times E1. So that's going to be 201 minus 201 dotted with E1, which is 1 over root 3, 1, 1, 1, times 1 over root 3, 1, 1, 1, because that's E1. So that's 201 minus, the root 3's are going to come outside, so I can just have them being a third. 201 dotted with 1, 1, 1 is 2 plus 0 plus 1 is 3. So that actually goes and has a party and becomes 1. And yeah, okay, I confess I fixed the example. So it's 201 minus 111, which is going to give me 1 minus 1, 1 minus 1 is 0. So 1 minus 1, 0. That's U2. Now if I want to normalize U2, I can say E2 is equal to the normalized version of U2, which is just 1 over root 2 times 1 minus 1, 0. So then I just need to find U3, and I can do the same again with U3. I can say that that's equal to V3 minus the projection of V3 onto E1 minus the projection of V3 onto E2. So that's going to be 3, 1 minus 1 minus 3, 1 minus 1 dotted with 1 over root 3, 1, 1, 1. And that's a number, and it's going in the direction of the unit vector of E2, of E1, minus V3 dotted with E2, so that's 3, 1 minus 1, dotted with 1 over root 2, 1 minus 1, 0, times E2, which is 1 over root 2, 1 minus 1, 0. So it's quite a complicated sum. So I've got an answer here, which I can do. 3, 1 minus 1 minus, the 1 over root 3's come out again. 3 plus 1 minus 1 is 3, so that goes, and I've got 1, 1, 1 there, so that becomes 1, minus, the halves are going to come out, the 1 over root 2's. I've got 3 minus 1 minus 0, so that's 2. So they cancel and become 1 again. As I say, I fixed the example to make my life easy. So then I've got 3, 1 minus 1 minus 1, 1, 1 minus 1 minus 1, 0. So therefore I get an answer for U2 being 3 minus 1 minus 1, so that's 1. 1 minus 1 is 0, minus minus 1 is plus 1, minus 1 minus 1 is minus 2. And so I can then normalize that and get E3. So E3 is just the normalized version of that, which is going to be 1 over root 6 of 1, 1 minus 2. Now let's just check. So 1, 1 minus 2 is normal to 1, 1, 0. It is normal to 1, 1, 1. Those two are normal to each other, so our normal base is set. Just need to make sure that's 1 over root 6. They are all of unit length. So I can write down my new transformation matrix, which I'm going to call E. It's the transformation matrix described by the basis vectors E1, E2, E3. So I've got E1, E2, E3, all written down as column vectors, and that's going to be my transformation matrix. that first contains the plane, notice, and then contains the normal to the plane. So I've redrawn everything just to get it all more compact so we can carry on. We've got our original two vectors v1 and v2, and we've defined e1 to be the normalized version of v1, and we've defined e2 to be the perpendicular part of v2 to e1, normalized to be of unit length. So these are all in a plane, and then e3 is normal to that plane. It's the bit of v3 that we can't make by a projection onto v1 and v2, then of unit length. Now say I've got a vector r over here, r. Now what I want to do is reflect r down through this plane. So I'm going to drop r down through this plane. There he is when he intersects the plane, and then out the other side to get a vector r prime. And let's say that r has some number like, I don't know, 2, 3, 5. 2, 3, 5. Now, this is going to be really awkward. This plane's off at some funny angle composed of these vectors and even these basis vectors. It's at some funny angle, and then how do I drop it down and do the perpendicular? There's going to be a lot of trigonometry. But the neat thing here is that I can think of r as being composed of a vector that's in the plane, so some vector that's composed of e1s and e2s. So here's e1 here. And some vector that's normal, so some vector that's some number of e3s. And when I reflect it through, the bit that's in the plane is going to be the same, but this bit that's some number of e3s, this bit here, I'm just going to make into minus this bit here. So if I wrote that down as a transformation matrix, the transformation matrix in my basis E is going to be to keep the E1 bit the same, keep the E2 bit the same, so that's the E1 bit, that's the E2 bit, and then reflect the E3 bit from being up to being down, 0, 0, minus 1. So that's a reflection matrix in E3. So that's a reflection in the plane. So just by thinking about it quite carefully, I can think about what the reflection is. And that TE is in the basis of the plane, not in my basis, but in the basis of the plane. So that is easy to define. And therefore, if I can get the vector r defined in the plane's basis vector set, in the E basis, I can then do the reflection, and then I can put it back into my basis vector set, and then I have the complete transformation. So a way of thinking about that is that if I've got my vector r, and I'm trying to get it through some transformation matrix to r prime, but that's going to be hard. That's going to be tricky. But I can transform it into the basis of the plane. So I can make an r in the basis of the plane. And I'm going to do that using e to the minus 1. E to the minus 1 is the thing that got me into, got a vector of mine into Bayes' basis, remember? Then I can do my transformation, I can do my reflection in the basis of the plane. I can do my reflection transformation. And then I will get r that's been transformed, primed, in the basis of the plane. Then I can read that back into my basis by doing E, because E is the thing that takes Bayes' vector and puts it back into my basis. So if I go, I can avoid the hard thing by going around doing these three operations. So r e to the minus 1, E inverse, t in the E basis, E. If I do those three things, I've done the complete transformation and I get r prime. So this problem reduces to doing that matrix multiplication. So we've got that, so we can just do the maths now, and then we'll be done. So I've just put the logic up there so that I can have the space down here for later, and I've put the transformation we're going to do there. A couple other things to note. One is because E we've carefully constructed by our Gram-Schmidt process to be orthonormal, we know that E transpose is the inverse. So calculating the inverse here isn't going to be a pain in the neck. The other thing is, compared to the situation with Bear where we're changing bases, here we're changing from our vector R to Bear's, or actually the plane's coordinate system. Then we're doing the transformation of the reflection in the plane, and then we're coming back to our basis. So the E and the e to the minus 1 are flipped compared to the last video because we're doing the logic the other way around. It's quite neat, right? The actual multiplication of doing this isn't awfully edifying. It doesn't build you up very much. It's just doing some arithmetic. So I'm going to write it down here, and if you want to verify it, you can pause the video, and then we'll come back and we'll comment on it. So this is TE times the transpose of E. Then I take that and multiply it by E itself, and I get E, TE, E transpose, which is this guy, simplifies to this guy, so that's T. All comes out quite nicely. So that's very, very nice. So then we can apply that to R. So we can say that T times R is equal to T times our vector 2, 3, 5. And that's going to give us R prime. And that gives us an answer of 1/3 of 11, 14, 5. So R prime here is equal to 1/3 of 11, 14, and 5. So that's a process that would have been very, very difficult to do with trigonometry, but actually with transformations, once we get into the plane of the mirror and the normal to the mirror, then it all becomes very easy to do that reflection operation. And it's quite magical, really. It's really amazing. So that's really nice, right? It's really cool. So what we've done here is we've done an example where we've put everything we've learned about matrices and vectors together to describe how to do something fun like reflect a point in space in a mirror. This might be useful, for instance, if you want to transform images of faces for the purposes of doing facial recognition. You know, transform my face from being like that to being like that. And then we could use our neural networks, our machine learning, to do that facial recognition part. In summary, this week we've gone out into the world with matrices and learned about constructing orthogonal bases, changing bases, and we've related that back to vectors and projections. So it's been a lot of fun. And it sets us up for the next topic, which Sam is going to lead on eigenvalues and eigenvectors.
Welcome to the final module. I'm Dr. Sam Cooper from the Dyson School of Design Engineering at Imperial College London, and I'm an energy researcher who uses machine learning as a tool to help me understand lithium-ion batteries. I'll be taking over from Dave for the last topic of the linear algebra course, but if you continue with the specialization, I'll also be leading the next course, which is on multivariate calculus. In this final module, we're going to be focusing on eigenproblems, which will require us to draw on nearly all of the ideas that you've learned in the previous modules. Then to finish the course, you'll be applying this tool in a coding exercise to recreate Google's famous Pagerank algorithm, which takes your internet search results and displays them in some kind of convenient order. I hope you enjoy this module and make use of the forums to let us know how you're getting on. The word eigen is perhaps most usefully translated from the German as meaning characteristic. So when we talk about an eigen problem, we're talking about finding the characteristic properties of something. But characteristic of what? This module, like the previous weeks, will try and explain this concept of eigenness primarily through a geometric interpretation, which allows us to discuss images rather than immediately getting tangled up in the maths. When I first learnt this topic, not only did we start by grinding through formulae, we also spent very little time discussing what all the maths was doing. This topic is often considered by students to be quite tricky, but it's my belief that once you know how to sketch these problems, the rest is just algebra. So, as you've seen from previous weeks, it's possible to express the concept of linear transformations using matrices. These operations can include scalings, rotations, and shears. Often, when applying these transformations, we are thinking about what they might do to a specific vector. However, it can also be useful to think about what it might look like when they're applied to every vector in the space. This can be most easily visualized by drawing a square centered at the origin, and then seeing how your shape is distorted when you apply the transformation. So if we apply a scaling of 2 in the vertical direction, the square would now become a rectangle. Whereas if we applied a horizontal shear to the space, it might look something like this. Now, here's the key concept. We are using our little square to help us visualize what is happening to many vectors. But notice that some vectors end up lying along the same line that they started on, whereas others do not. To highlight this, I'm going to draw 3 specific vectors onto our initial square. Now, let's consider our vertical scaling again and think about what will happen to these 3 vectors. As you can see, the horizontal green vector is unchanged, pointing in the same direction and having the same length. The vertical pink vector is also still pointing in the same direction as before, but its length has doubled. Lastly, the diagonal orange vector used to be exactly 45 degrees to the axis. Its angle has now increased, as has its length. I hope you can see that actually, besides the horizontal and vertical vectors, any other vector's direction would have been changed by this vertical scaling. So in some sense, the horizontal and vertical vectors are special. They are characteristic of this particular transform, which is why we refer to them as eigenvectors. Furthermore, because the horizontal vector's length was unchanged, we say that it has a corresponding eigenvalue of 1, whereas the vertical eigenvector doubled in length, so we say it has an eigenvalue of 2. So, from a conceptual perspective, that's about it for 2D eigenproblems. We simply take a transform and we look for the vectors who are still laying along the same span as before, and then we measure how much their length has changed. This is basically what eigenvectors and their corresponding eigenvalues are. Let's look at 2 more classic examples to make sure that we can generalize what we've learned. Here's our marked up square again. And now let's look at pure shear, where pure means that we aren't performing any scaling or rotation in addition, so the area is unchanged. As I hope you spotted, it's only the green horizontal line that is still laying along its original span, and all the other vectors will be shifted. Finally, let's look at rotation. Clearly, this thing has got no eigenvectors at all, as all of the vectors have been rotated off their original span. In this lecture, we've already covered almost all of what you need to know about eigenvectors and eigenvalues. Although we've only been working in 2 dimensions so far, the concept is exactly the same in 3 or more dimensions. In the rest of the module, we will be having a look at some special cases, as well as discussing how to describe what we've observed in more mathematical terms. As we saw previously, eigenvectors are those which lie along the same span both before and after applying a linear transform to a space. And then eigenvalues are simply the amount that each of those vectors has been stretched in the process. In this video, we're going to look at 3 special cases to make sure the intuition we've built so far is robust, and then we're going to try and extend this concept into 3 dimensions. The first example we're going to consider is that of a uniform scaling, which is where we scale by the same amount in each direction. As you will hopefully have spotted, not only are all 3 of the vectors that I've highlighted eigenvectors, but in fact, for a uniform scaling, any vector would be an eigenvector. In this second example, we're going to look at rotation. In the previous video, we applied a small rotation, and we found that it had no eigenvectors. However, there is one case of non-zero pure rotation which does have at least some eigenvectors, and that is 180 degrees. As you can see, the 3 eigenvectors are still laying on the same spans as before, but just pointing in the opposite direction. This means that once again, all vectors for this transform are eigenvectors, and they all have eigenvalues of -1, which means that although the eigenvectors haven't changed length, they are all now pointing in the opposite direction. This third case, we're going to look at a combination of a horizontal shear and a vertical scaling, and it's slightly less obvious than some of the previous examples. Just like the pure shear case we saw previously, the green horizontal vector is an eigenvector, and its eigenvalue is still 1. However, despite the fact that neither of the two vectors shown are eigen, this transformation does have two eigenvectors. Here, I've now added the second eigenvector onto the image, and it shows us that although the concept is fairly straightforward, eigenvectors aren't always easy to spot. Let's now apply the inverse transform and watch our parallelogram go back to its original square, but this time with our eigenvector visible. Hopefully, you're at least convinced that it is indeed an eigenvector, and as it stays on its own span. This problem is even tougher in 3 or more dimensions, and many of the uses of eigentheory in machine learning frame the system as being composed of hundreds of dimensions or more. So clearly, we're going to need a more robust mathematical description of this concept to allow us to proceed. Before we do, let's just take a look at one quick example in 3D. Clearly, scaling and shear are all going to operate in much the same in 3D as they do in 2D. However, rotation does take on a neat new meaning. As you can see from the image, although both the pink and green vectors have changed direction, the orange vector has not moved. This means that the orange vector is an eigenvector, but it also tells us, as a physical interpretation, that if we find the eigenvector of a 3D rotation, it means we've also found the axis of rotation. In this video, we've covered a range of special cases, which I hope have prompted the questions in your mind about how we're going to go about writing a formal definition of an eigenproblem. And this is exactly what we're going to be discussing next time. See you then. Hopefully, you all now have a reasonable feeling for what an eigenproblem looks like geometrically. So in this video, we're going to formalize this concept into an algebraic expression, which will allow us to calculate eigenvalues and eigenvectors whenever they exist. Once you've understood this method, we'll be in a good position to see why you should be glad that computers can do this for you. If we consider a transformation A, what we have seen is that if it has eigenvectors at all, then these are simply the vectors which stay on the same span following a transformation. They can change length and even point in an opposite direction entirely, but if they remain on the same span, they are eigenvectors. If we call our eigenvector x, then we can say the following expression. Ax equals lambda x. Where on the left-hand side, we're applying the transformation matrix A to a vector x. And on the right-hand side, we are simply stretching the vector x by some scalar factor lambda. So lambda is just some number. We're trying to find values of x that make the two sides equal. Another way of saying this is that for our eigenvectors, having a applied to them just scales their length, or does nothing at all, which is the same as scaling the length by a factor of 1. So in this equation, a is an n-dimensional transform, meaning it must be an n by n square matrix. The eigenvector x must therefore be an n-dimensional vector. To help us find the solutions to this expression, we can rewrite it by putting all the terms on one side and then factorizing. So, a minus lambda I times x equals 0. If you're wondering about where the I term came from, it's just an n by n identity matrix, which means it's a matrix the same size as A, but with 1s along the leading diagonal and 0s everywhere else. We didn't need this in the first expression we wrote, as multiplying vectors by scalars is defined. However, subtracting scalars from matrices is not defined, so that I just tidies up the maths without changing the meaning. Now that we have this expression, we can see that for the left-hand side to equal 0, either the contents of the brackets must be 0, or the vector x is 0. So we're actually not interested in the case where the vector x is 0. That's when it has no length or direction, and is what we call a trivial solution. Instead, we must find when the term in the brackets is 0. Referring back to the material in the previous parts of the course, we can test if a matrix operation will result in a 0 output by calculating its determinant. So, det of A minus lambda I equals 0. Calculating the determinants manually is a lot of work for high-dimensional matrices. So let's just try applying this to an arbitrary 2 by 2 transformation. Let's say A equals A, B, C, D. Substituting this into our eigenfinding expression gives the following. Det of A, B, C, D minus lambda 0, 0, lambda. Evaluating this determinant, we get what is referred to as the characteristic polynomial, which looks like this. So lambda squared minus A plus D lambda plus AD minus BC equals 0. Our eigenvalues are simply the solutions of this equation, and we can then plug these eigenvalues back into the original expression to calculate our eigenvectors. Rather than continuing with our generalized form, this is a good moment to apply this to a simple transformation for which we already know the eigensolution. Let's take the case of a vertical scaling by a factor of 2, which is represented by the transformation matrix A equals 1, 0, 0, 2. We can then apply the method that we just described and take the determinant of A minus lambda I and then set it to 0 and solve. So the determinant of 1 minus lambda, 0, 0, 2 minus lambda equals 1 minus lambda, 2 minus lambda, which is of course equal to 0. This means that our equation must have solutions at lambda equals 1 and lambda equals 2. Thinking back to our original eigenfinding formula, A minus lambda I x equals 0, we can now sub these two solutions back in. So thinking about the case where lambda equals 1, we can say 1 minus 1, 0, 0, 2 minus 1 times this x vector, x1 and x2, must equal to 0, 0, 0, 1 times x1, x2. Therefore, we've got 0 and x2 must equal 0. Now thinking about the case where lambda equals 2, at lambda equals 2, you get 1 minus 2 and 2 minus 2. And then you get, of course, minus 1, 0, 0, 0, which equals 2 minus x1, 0, which equals 0. So what do these two expressions tell us? Well, in the case where our eigenvalue lambda equals 1, we've got an eigenvector where the x2 term must be 0. But we don't really know anything about the x1 term. Well, this is because, of course, any vector that points along the horizontal axis could be an eigenvector of this system. So we write that by saying at lambda equals 1, x, our eigenvector, can equal anything along the horizontal axis as long as it's 0 in the vertical direction. So we put in an arbitrary parameter, t. Similarly, for the lambda equals 2 case, we can say that our eigenvector must equal 0 t, because as long as it doesn't move at all in the horizontal direction, any vector that's purely vertical would therefore also be an eigenvector of this system, as they all would lie along the same span. So now we have two eigenvalues and their two corresponding eigenvectors. Let's now try the case of a rotation by 90 degrees anti-clockwise to ensure that we get the result that we expect, which, if you remember, is no eigenvectors at all. The transformation matrix corresponding to a 90-degree rotation is as follows. A equals 0, minus 1, 1, 0. So, applying the formula once again, we get the determinant of 0 minus lambda minus 1, 1, 0 minus lambda, which if we calculate this through, comes out to lambda squared plus 1 equals 0, which doesn't have any real numbered solutions at all, hence no real eigenvectors. We could still calculate some complex eigenvectors using imaginary numbers, but this is beyond what we need for this particular course. Despite all the fun that we've just been having, the truth is that you will almost certainly never have to perform this calculation by hand. Furthermore, we saw that our approach required finding the roots of a polynomial of order n, i.e. the dimension of your matrix, which means that the problem will very quickly stop being possible by analytical methods alone. So when a computer finds the eigensolutions of a 100-dimensional problem, it's forced to employ iterative numerical methods. However, I can assure you that developing a strong conceptual understanding of eigenproblems will be much more useful than being really good at calculating them by hand. In this video, we translated our geometrical understanding of eigenvectors into a robust mathematical expression and validated it on a few test cases. But I hope that I've also convinced you that working through lots of eigenproblems, as is often done in engineering undergraduate degrees, is not a good investment of your time if you already understand the underlying concepts. This is what computers are for. Next video, we'll be referring back to the concept of basis change to see what magic happens when you use eigenvectors as your basis. See you then. So now that we know what eigenvectors are and how to calculate them, we can combine this idea with the concept of changing basis, which was covered earlier in the course. What emerges from this synthesis is a particularly powerful tool for performing efficient matrix operations called diagonalization. Sometimes we need to apply the same matrix multiplication many times. For example, imagine that a transformation matrix T represents the change in location of a particle after a single time step. So we can write that our initial position, described by vector v0, multiplied by the transformation t, gives us our new location v1. To work out where our particle will be after 2 time steps, we can find v2 by simply multiplying v1 by t, which is of course the same thing as multiplying v0 by t 2 times. So, v2 equals t squared times v0. Now, imagine that we expect this same linear transformation to occur every time step for n time steps, where we can write vn is t to the power of n times v0. You've already seen how much work it takes to apply a single 3D matrix multiplication. So if we were to imagine that t tells us what happens in 1 second, but we'd like to know where our particle is in 2 weeks from now, then n is going to be around 1.2 million, i.e. we'd need to multiply t by itself more than 1 million times, which may take quite a while. If all the terms in the matrix are 0, except for those along the leading diagonal, we refer to it as a diagonal matrix. And when raising matrices to powers, diagonal matrices make things a lot easier. In fact, have a go just now to see what I mean. All you need to do is put each of the terms on the diagonal to the power of n, and you've got the answer. So, in this case, t to the n is a to the n, b to the n, and c to the n. It's simple enough. But what if t is not a diagonal matrix? Well, as you may have guessed, the answer comes from eigenanalysis. Essentially, what we're going to do is simply change to a basis where our transformation t becomes diagonal, which is what we call an eigenbasis. We can then easily apply our power of n to the diagonalized form and finally transform the resulting matrix back again, giving us t to the power of n but avoiding much of the work. As we saw in the section on changing basis, each column of our transform matrix simply represents the new location of the transformed unit vectors. So, to build our eigenbasis conversion matrix, we just plug in each of our eigenvectors as columns. C equals eigenvector 1, eigenvector 2, an eigenvector 3 in this case, as we're using a three-dimensional example. However, don't forget that some of these may be complex, so not easy to spot using the purely geometrical approach, but they appear in the maths just like the others. Applying this transform, we find ourselves in a world where multiplying by t is effectively just a pure scaling, which is another way of saying that it can now be represented by a diagonal matrix. Crucially, this diagonal matrix, D, contains the corresponding eigenvalues of the matrix T. So D equals lambda 1, lambda 2, and lambda 3, with zeros elsewhere. We're so close now to unleashing the power of eigen. The final link that we need to see is the following. Bringing together everything we've just said, it should now be clear that applying the transformation T is just the same as converting to our eigenbasis, applying the diagonalized matrix, and then converting back again. So T equals C D C inverse, which suggests that T squared can be written as C D C inverse multiplied again by C D C inverse. So hopefully you've spotted that in the middle of our expression, on the right-hand side, you've got C multiplied by C inverse. But multiplying a matrix and then by its inverse is just the same as doing nothing at all. So we can simply remove this operation. Equals C D D C inverse. And then we can finish this expression by saying, well, this must be C D squared C inverse. We can, of course, then generalize this to any power of t we'd like. So finally, we can say that t to the power of n is going to equal C D to the power of n multiplied by C inverse. We now have a method which lets us apply a transformation matrix as many times as we'd like without paying a large computational cost. This result brings together many of the ideas that we've encountered so far in this course, and in the next video we'll work through a short example just to ensure that this approach lines up with our expectations when applied to a simple case. See you then. Now that we've walked through the theory of eigenbases and diagonalization, let's have a go at a simple 2D example where we can see the answer graphically, so we'll know whether or not our method has worked as expected. Consider the transformation matrix T equals 1, 1, 0, 2. Hopefully, you'd feel fairly comfortable at this point in drawing the transformed square and vectors that were used in the previous examples. As the first column is just 1, 0, this means that our I hat vector will be unchanged. However, the second column tells us that j hat, the second vector, will be moving to the point 1, 2. Let's also consider the orange diagonal vector to point 1, 1. Multiplying through gives us 1, 1, 0, 2 multiplied by 1, 1. So thinking about rows times cols, we're going to get 1 plus 1 and 0 plus 2, which gives us 2, 2. It's interesting to consider that this particular transform could be decomposed into a vertical scaling by a factor of 2, and then a horizontal shear by a half step. Because we've chosen such a simple transformation, hopefully you've already spotted the eigenvectors and can state their eigenvalues. These are, at lambda equals 1, our eigenvector is 1, 0, and at lambda equals 2, our eigenvector equals 1, 1. Now let's consider what happens to the vector minus 1, 1 when we apply t. So 1, 1, 0, 2 applied to minus 1, 1. This time is going to equal rows times cols minus 1 plus 1 and 0 plus 2, which equals 0, 2. And if we apply t again, we're going to get the following. 1, 1, 0, 2 applied to 0, 2, which is going to equal rows times cols again, 0 plus 2, and 0 plus 4. So this thing finally is going to equal 2, 4. Now instead, if we were to start by finding t squared, so t squared is going to equal this matrix multiplied by itself. So applying rows times cols, we're going to get 1 times 1 times 1 times 0, so that's 1. Rows times cols here, we're going to get a 3. Rows times cols here, we're going to get a 0. Rows times cols here, we're going to get a 4. Now we can apply this to our vector and see if we get the same result. So 1, 3, 0, 4 multiplied by minus 1, 1 is going to equal rows times cols, so we're going to get minus 1 plus 3 and 0 plus 4, which of course equals 2, 4. We can now try this whole process again, but using our eigenbasis approach. We've already built our conversion matrix C from our eigenvectors. So C is going to equal 1, 0, 1, 1. But we're now going to have to find its inverse. However, because we've picked such a simple 2 by 2 example, it's possible just to write this inverse down directly by considering that C would just be a horizontal shear one step to the right. So C inverse must just be this same shift back to the left again. So C inverse is going to equal 1 minus 1, 0, 1. It's worth noting that despite how easy this was, I would still always feed this to the computer instead of risking making silly mistakes. We can now construct our problem. So t squared is going to equal c d squared c inverse, which of course in our case is going to equal 1, 1, 0, 1 multiplied by our diagonal matrix, which is going to be 1 and 2, and that's all squared, multiplied by c inverse, which is 1 minus 1, 0, 1. Working this through, we can see that, let's keep this first matrix, 1, 1, 0, 1, and work out this bit. So we'll say, okay, this is going to be 1 and 4 on the diagonal, 1 minus 1, 0, 1. And let's work out these two matrices here. So we've got 1, 1, 0, 1 multiplied by, so we're doing rows times cols in each case. So for example, 1, 0 times 1, 0, we get a 1 here. We're going to do the second row in the first column, we get a 0 there. First row and second column, we're going to get a minus 1 there. And the second row and the second column, we're going to get a 4 here. Okay, and then working it through one more step, we're going to see that we get more grinding. We get first row, first column, 1. Second row, first column, 0. First row, second column is 3. And second row, second column is 4. And applying this to the vector minus 1, 1, we're going to get something like this. So 1, 3, 0, 4 applied to minus 1, 1 is going to be rows times cols, so minus 1 plus 3 and 0 plus 4, which equals 2, 4, which pleasingly enough is the same result as we found before. Now, there is a sense in which, for much of mathematics, once you're sure that you've really understood a concept, then because of computers, you may never have to do this again by hand. However, it is still good to work through a couple of examples on your own, just to be absolutely sure that you get it. There are of course many aspects of eigentheory that we haven't covered in this short video series, including undiagonizable matrices and complex eigenvectors. However, if you are comfortable with the core topics that we've discussed, then you're already in great shape. In the next video, we're going to be looking at a real-world application of eigentheory to finish off this linear algebra course. This is a particularly famous application which requires abstraction away from the sort of geometric interpretations that we've been using so far, which means that you'll be taking the plunge and just trusting the maths. See you then. The final topic of this module on eigenproblems, as well as the final topic of this course as a whole, will focus on an algorithm called Pagerank. This algorithm was famously published by and named after Google founder Larry Page and colleagues in 1998, and was used by Google to help them decide which order to display their websites when they returned from search. The central assumption underpinning Pagerank is that the importance of a website is related to its links to and from other websites. And somehow, eigentheory comes up. This bubble diagram represents a model mini-internet, where each bubble is a web page, and each arrow from A, B, C, and D represents a link on that web page which takes you to one of the others. We're trying to build an expression that tells us, based on this network structure, which of these web pages is most relevant to the person who made the search. As such, we're going to use the concept of procrastinating Pat, who is an imaginary person who goes on the internet and just randomly clicks links to avoid doing their work. By mapping all the possible links, we can build a model to estimate the amount of time we would expect Pat to spend on each web page. We can describe the links present on page A as a vector, where each row is either a 1 or a 0 based on whether there is a link to the corresponding page, and then normalize the vector by the total number of links, such that they can be used to describe a probability for that page. For example, the vector of links from page A would be 0, 1, 1, 1, because vector A has links to sites B, to C, and to D, but it doesn't have a link to itself. Also, because there are 3 links on this page in total, we would normalize by a factor of a third, so that the total click probability sums to 1. So we can write LA equals 0, a third, a third, a third. Following the same logic, the link vectors of the next 2 sites are shown here, and finally for page D, we can write LD is going to equal, so D is connected to B and C but not A, 2 sites in total, 0, a half, 0. We can now build our link matrix L by using each of our link vectors as a column, which you can see will form a square matrix. What we're trying to represent here with our matrix L is the probability of ending up on each of the pages. For example, the only way to get to A is by being at B. So you then need to know the probability of being at B, which you could have got to from either A or D. As you can see, this problem is self-referential, as the ranks of all the pages depend on all the others. Although we built our matrix from columns of outward links, we can see that the rows describe inward links normalized with respect to their page of origin. We can now write an expression which summarizes the approach. We're going to use the vector R to store the rank of all web pages. To calculate the rank of page A, you need to know 3 things about all other pages on the internet. What's your rank? Do you link to page A? And how many outgoing links do you have in total? The following expression combines these 3 pieces of information for web page A only. So, RA is going to equal the sum from J equals 1 to N, where N's all the web pages, of the link matrix relevant to web page A and location J multiplied by the rank at location J. So this is going to scroll through each of our web pages, which means that the rank of A is the sum of the ranks of all the pages which link to it, weighted by their specific link probability taken from matrix L. Now we want to be able to write this expression for all pages and solve them simultaneously. Thinking back to our linear algebra, we can rewrite the above expression applied to all web pages as a simple matrix multiplication. So R equals LR. Clearly, we start off not knowing R, so we simply assume that all the ranks are equally and normalize them by the total number of web pages in our analysis, which in this case is 4. So R equals a quarter, a quarter, a quarter, a quarter. Then, each time we multiply R by our matrix L, this gives us an updated value for R. So we can say that Ri plus 1 is going to be L times Ri. Applying this expression repeatedly means that we are solving this problem iteratively. Each time we do this, we update the values in R until eventually R stops changing. So now R really does equal LR. Thinking back to the previous videos in this module, this implies that R is now an eigenvector of matrix L, with an eigenvalue of 1. At this point, you might well be thinking, if we want to multiply R by L many times, perhaps this would be best tackled by applying the diagonalization method that we saw in the last video. But don't forget, this would require us to already know all the eigenvectors, which is what we're trying to find in the first place. So, now that we have an equation, and hopefully some idea of where it came from, we can ask our computer to iteratively apply it until it converges to find our rank vector. You can see that although it takes about 10 iterations for the numbers to settle down, the order is already established after the first iteration. However, this is just an artifact of our system being so tiny. So now we have our result, which says that as procrastinating Pat randomly clicks around our network, we would expect them to spend about 40% of their time on page D, but only about 12% of their time on page A, with 24% on each of pages B and C. We now have our ranking, with D at the top and A at the bottom and B and C equal in the middle. As it turns out, although there are many approaches for efficiently calculating eigenvectors that have been developed over the years, repeatedly multiplying a randomly selected initial guess vector by your matrix, which is called the power method, is still very effective for the PageRank problem for two reasons. Firstly, although the power method will clearly only give you one eigenvector, when we know that there will be n for an n web page system, it turns out that because of the way we've structured our link matrix, the vector it gives you will always be the one that you're looking for, with an eigenvalue of 1. Secondly, although this is not true for the full web page mini-internet, when looking at the real internet, you can imagine that almost every entry in the link matrix will be 0, i.e., most pages don't connect to most other pages. This is referred to as a sparse matrix, and algorithms exist such that multiplication can be performed very efficiently. One key aspect of the PageRank algorithm that we haven't discussed so far is called the damping factor, D. This adds an additional term to our iterative formula. So Ri plus 1 is now going to equal D times Lri plus 1 minus D over n. D is something between 0 and 1, and you can think of it as 1 minus the probability with which procrastinating Pat suddenly randomly types in a web address rather than clicking on a link on his current page. The effect that this has on the actual calculation is about finding a compromise between speed and stability of the iterative convergence process. There are over 1 billion websites on the internet today, compared with just a few million when the PageRank algorithm was first published in 1998. And so the methods for search and ranking have had to evolve to maximize efficiency, although the core concept has remained unchanged for many years. This brings us to the end of our introduction to the PageRank algorithm. There are, of course, many details which we didn't cover in this video, but I hope this has allowed you to come away with some insight and understanding into how the PageRank works, and hopefully the confidence to apply this to some larger networks yourself. This brings us to the end of the 5th module, and also to the end of this course on linear algebra for machine learning. We've covered a lot of ground in the past 5 modules, but I hope that we've managed to balance the speed with the level of detail to ensure that you stayed with us throughout. There is a tension at the heart of mathematics teaching in the computer age. Classical teaching approaches focused around working through lots of examples by hand, without much emphasis on building intuition. However, computers now do nearly all of the calculation work for us, and it's not typical for the methods appropriate to hand calculation to be the same as those employed by a computer. This can mean that despite doing lots of work, students can come away from a classical education missing both the detailed view of the computational methods, but also the high-level view of what each method is really doing. The concepts that you've been exposed to over the last 5 modules cover the core of linear algebra that you will need as you progress your study of machine learning. And we hope that at the very least, when you get stuck in the future, you'll know the appropriate language so that you can quickly look up some help when you need it, which after all is the most important skill of a professional coder.
That's it for this course on linear algebra in our specialisation on mathematics for machine learning. Our goal was to give you some of the underpinnings of linear algebra in order to enable you to access neural networks, machine learning and data science courses more generally. This is intended as a course for a social scientist, engineer or physicist to develop the insight required to access other courses on machine learning tools and in order to do useful work to solve problems with machine learning in the real world. It's not intended as a foundation for a graduate linear algebra course, and nor have we had the time to discuss topics like the cross product that don't have applications in machine learning. We started out in the course by thinking of some data problems, fitting functions to data, or the apples and bananas price discovery problem, which we used to take us on a journey into linear algebra, first vectors and then matrices. Through it all, you did exercises to try out what you'd learned and then took those into a couple of programming exercises in Python at the end. This will have given you the confidence to say that you're really getting towards having an intuitive understanding of linear algebra and how to apply it in code. If you've enjoyed this course, we continue the journey in machine learning and data science in the next course in this specialisation, Multivariate Calculus. There, we look at calculus and how to find the gradients of functions of more than one variable. This will let us examine minimization and how to fit models to data. Once we have minimization and linear algebra and probability, you'll have all the underpinning mathematical tools and concepts you need to then look at principal component analysis, machine learning and neural networks. Sam and I and all the team here at Imperial really hope that you found this course valuable and useful and fun. And of course, we wish you the very best for the future, and we'll look forward to seeing you again in the next course.
Welcome to Introduction to Multivariate Calculus, Course 2 of the Mathematics for Machine Learning specialisation. We'll be embarking on a whistle-stop tour of calculus with a special focus on interactive animations and practical coding examples. I'm Dr. Sam Cooper from the Dyson School of Design Engineering at Imperial College London, and I use machine learning as a tool to help me characterize and design energy materials. I'm also an online learning addict. To understand multivariate calculus, you need to be able to apply the linear algebra methods covered in the previous course, so if you've not completed it already, you may wish to go back. Many important machine learning approaches, such as neural networks, have calculus at their very core. So the aim of this course is for you to see the connection between the maths and the meaning. The ideal outcome would be for you to finish this specialization and then feel confident enough to immediately dive into one of the many wonderful applied machine learning courses already available online. We're going to start the course by laying down the foundations of calculus through the use of intuition building animations. Then, we're going to generalize these concepts to multidimensional systems where you will discover how to navigate mountain ranges in the dark. Next, you'll be learning exactly how calculus is used to train neural networks, as well as working through how we would actually write some code to do this using the Python programming language. Finally, you will put all of your multivariate calculus skills into action with my colleague Professor David Dye, who will explain the fundamentals of regression before asking you to write some code to fit complicated functions to real data. I really hope you enjoy the course, and I look forward to hearing from you in the forums. Welcome to Module 1 of 6 on this course introducing you to various concepts in calculus that we believe you'll find useful when studying machine learning. We start right from the basics, but build you up fairly quickly to some interesting applications in Modules 5 and 6. This week, we'll be focusing on the fundamental theory of calculus, as well as some handy rules to speed things up. Where possible, I'm going to try and represent the concepts graphically so that you can see the derivations rather than just reading them. This sometimes means that we'll be skimming over a few details, but I'll also provide you with links to the more rigorous descriptions so that you can check them out if you're interested. Speaking for myself, I find it generally true that if I can't draw something, then I don't really get it, even if I could write down all the relevant equations. So, for the tests, I'm going to be asking you to identify solutions on graphs rather than grinding through the algebra for the most part. I hope you enjoy this first module, and I look forward to meeting many of you in the discussion forums. Before diving into calculus, we should first talk briefly about what functions are and where we use them. Essentially, a function is a relationship between some inputs and an output. So for example, if I had a function for modelling the distribution of temperature in this room, I might input the x, y, and z coordinates of a specific location I'm interested in, as well as the time t, and then the function would return me the temperature at that specific point in space at that moment in time. Like so many areas of maths, even if the idea is quite straightforward, often the notation can make things unnecessarily confusing. We'll be confronted by this again later in the course, and although it's sometimes fairly arbitrary historical reasons that decide this, like different people inventing different parts of maths at different times, it can also be because a particular notation style is more convenient for the specific application that it was developed for. However, and here is where a lot of the problems seem to arise, in order to use and play with the interesting applications of maths, it requires you to have done quite a large amount of often quite boring groundwork. Mathematical language is like learning any other language in that respect. You can't enjoy French poetry until you've learned a lot of French vocabulary and grammar, including all its quirks and irregularities. Quite understandably, some people find this off-putting. My French is still terrible, for example. This is made worse by the fact that most people have not even realised that there is maths poetry waiting for them at the end of this algebra tunnel. Machine learning is a whole genre of this poetry, so stick with us for the rest of the specialization and you'll be ready to appreciate it and even write some of your own. Back to functions. We often see expressions such as f of x equals x squared plus 3. Perhaps the only thing worth mentioning about this notation style is, yes, I admit it, it is absurd that you should somehow just know that f brackets x means f is a function of x and not f multiplied by x. Sometimes this gets genuinely unclear when other bracket terms appear in your expression. For example, f of x equals this thing over here. You can assume that g, h, and a are all not variables, otherwise I would have to write f of x, g, h, and a. But you could only know for sure what was going on here if it was explained to you with more context. For example, is g a function being applied to x? What about h and a over here? Maybe they're both just constants, although you do face the same problem of missing context in any language, like the famous panda who goes to a restaurant and eats, shoots, and leaves, and they were both delicious. I can only apologise on behalf of maths and hopefully console you with two facts. Firstly, maths is at the core of my day job, and I often still get confused myself. And secondly, I still love it, and it get better at second-guessing any missing context all the time, just like any other language. In the following exercise, I'm either going to show you some data or describe a concept to you, and you're going to have to select a function which you think might be used to represent it. This is not intended to be a difficult exercise, but what I would like you to understand is that selecting a function is the creative essence of science. This process of selecting a candidate function or hypothesis to model the world is what the great geniuses of science are remembered for. There then follows a potentially long and difficult process of testing this hypothesis, but there would be nothing to test without that first creative step. Calculus is simply the study of how these functions change with respect to their input variables, and it allows you to investigate and manipulate them, but ultimately it's just a set of tools, and by the end of this course you'll be using them yourself to model some real-world data. In the last video, I told you that calculus is just a set of tools for describing the relationship between a function and the change in its variables. And so in this video, we're going to explore what this means and how it might be useful. Let's start by having a look at a classic example, a speed versus time graph for a car. The most obvious thing this graph tells us is that the car's speed is not constant, because a constant speed would just be a flat, horizontal line. Furthermore, starting from 0 speed at 0 time, this car's speed is initially increasing with time, which is another way of saying that it is accelerating. Towards the end of the time period, the car's speed is shown to be rapidly decreasing, meaning that it is decelerating. There's a lot of information in this graph, and calculus will allow us to extract much more than just the speed. As we've already said, a horizontal line implies a constant speed, and then the more the line is sloping up, the greater the acceleration. In fact, acceleration can be defined as the local gradient of a speed-time graph. And clearly, acceleration itself is also a function of time in our example. We refer to the gradient at a single point as the local gradient, and we can illustrate this concept by drawing a tangent line, which is a straight line that touches the curve at a point and is also the same gradient of the curve at that point. After the initial acceleration, the car's speed reaches a peak and then begins to decelerate again. Deceleration has a negative slope. By recording the slope of these tangent lines at every point, we could plot an entirely new graph which would show us acceleration against time rather than speed against time. Before we plot this, for the complex case, let's think about what this acceleration time graph would look like for a car travelling at constant speed. Constant speed, we've got a flat horizontal line on our speed time graph. Then we can say that its gradient is of course 0. So the acceleration time graph would also just be a horizontal line, but in this case, at acceleration equals 0. Going back to our more complex case, let's just talk through what we should expect before we have a go at plotting it. So, initially, the gradient is positive and fairly constant, before it drops to 0 at the peak. It then becomes negative for a period before returning to 0. Let's now take a look at the graph for acceleration versus time overlaid onto the speed-time graph. Don't forget, the vertical axis for the blue line is speed and will have units of distance per time, whereas the vertical axis for the orange line is acceleration and will have units of distance per time squared. Because they've got different units, we could scale either of these two lines vertically in this plot, and the meaning would still be identical. However, these have been scaled just to make the most use of this plot area available. You can see that the points at which the acceleration function is 0, i.e. where it crosses the horizontal axis, coincide with where the speed-time graph is flat and has 0 gradient, as we would expect. Although we will be discussing the formal definition of a derivative in a later video, what we've just done by eye is the essence of calculus, where we took a continuous function and described its slope at every point by constructing a new function, which is its derivative. We can, in principle, plot the derivative of the acceleration function following the same procedure, where we simply take the slope of the acceleration function at every point. This is the rate of change of acceleration, which we can also think of as being the second derivative of the speed, and it's actually referred to as the jerk of the car. Think of the jerky motion of a car as it stops and starts. Now, you may have never heard of this concept before, but hopefully, just by telling you that it's the derivative of the acceleration curve, this should be all you need to know to approximately sketch the jerk. Also very interesting is the idea of taking our baseline speed function and trying to imagine what function this would have been the gradient of, as in applying the inverse procedure to the one that we've just discussed. We can refer to this as the antiderivative, which for those who've done calculus before, you may remember that it's closely related to something called the integral. For the example we're discussing here, it would represent the distance of the car from its starting position. This should make more sense when you consider that the change in the distance with respect to time, i.e. the slope of the distance time graph, i.e. how much distance you are covering per unit time, is just the speed. This analysis of slopes is all we're going to discuss in the video, and even though you haven't laid out yet the formal definition of calculus, you should already be able to answer lots of gradient-type questions in the following exercise, which will put you in a very strong position to start thinking about differentiation more formally. Now that we've explored the relationship between functions and their gradient, we should be ready to lay out the more formal definition of a derivative. All we're going to do is translate the understanding about gradients that we saw in the previous video into some mathematical notation that we can write down. Unfortunately, this is the bit that a lot of people seem to find uncomfortable, so I will do my best to make it as painless as possible. We talked in the last video about horizontal lines having a gradient of 0, whilst upwards and downwards sloping lines having positive or negative gradients respectively. We can write down a definition of this concept by taking the example of a linear function which has the same gradient everywhere. So if we start by picking any 2 points, let's say here and here, we can then say that the gradient of this line is equal to the amount of that function that increases in this interval, divided by the length of the interval that we're considering. This description is often just condensed to the expression rise over run, where rise is the increase in the vertical direction and run is the distance along the horizontal axis. So, we've got the rise here and the run down here. If our function was sloping down and we picked points at the same horizontal locations, then our run would be the same, but our rise would now be negative. So our gradient equals rise divided by run. Fairly straightforward so far, but how does it relate to the more complicated functions we saw previously, where the gradient is different at every point? Now, the rise over run type gradient varies depending on where we choose our points. Let's pick a single point where we'd like to know the gradient, which we'll say is at point x on the horizontal axis. The value of our function at this point is therefore clearly just f of x. We're going to use the same logic as before, so we now need to pick a second point to draw our rise over run triangle. We can call the horizontal distance between our 2 points delta x, where, as usual, a delta is being used to express a small change in something, which means our second point must be at position x plus delta x. We can also write down the vertical position of our second point as a function f evaluated at our new location x plus delta x, i.e. f of x plus delta x. So we can now build an expression for the approximate gradient at our point x, based on the rise over run gradient between point x and any second point, remembering that the run will be our distance delta x and our rise is just the difference in heights of the 2 points. The last step in this process is simply to notice that for nice smooth continuous functions like the one we're showing here, as delta x gets smaller, the line connecting 2 points becomes a better and better approximation of the actual gradient at our point x. We can express this concept formally by using the limit notation scheme, which says that as delta x goes to 0, our expression will give us a function for our gradient at any point we choose, which we write as f dash of x or df by dx, depending on which notation scheme you prefer. This is a slightly strange concept as we're not talking about delta x equals 0, as dividing by 0 is not defined, but instead just when x is extremely close to 0. This process of extreme rise over run is what differentiation is. So when you're asked to differentiate a function, this literally just means substitute the function into this expression. We could fill up several videos with more robust interpretations of this infinitely small but non-zero delta x, but for now, just don't worry about it too much. We know more than enough to continue on our journey. Let's now put our new derivative expression into practice and see if it works. First, we should try this out on a linear function once again, as we know that the answer is just going to be a constant. So, what will the gradient of f of x equals 3x plus 2 be? So we can immediately sub this straight in and say, okay, f dash of x is going to equal the limit as delta x goes to 0 of, so we're taking our function and subbing it in, 3x plus delta x plus 2 minus 3x plus 2, all divided by delta x. Okay, and now we just work through the algebra. So we can say the limit of delta x goes to 0 of, and so we can expand these brackets out, so we're going to get 3x plus 3 delta x plus 2 minus 3x minus 2, all divided by delta x, Okay, and now we can look at this and say some of the terms are going to cancel. So this 3x here goes with this 3x here, and this plus 2 here goes with this minus 2 here. So we can keep going with this line and say, well, the limit, and it's going to be 3 delta x all over delta x. And then working down here, we can say, okay, well, the delta x's themselves are just going to cancel. So you end up with the limit of delta as delta x goes to 0 of just 3. Now this thing doesn't have a delta x in it. So actually, the answer for this one is just the number 3. Because all of the delta x terms have disappeared in this case, then the limit expression has no effect, so we can just ignore it. The gradient of our linear function is just a constant, as we expected. In fact, I'm sure many of you will have known already that the gradient of an equation of the form f equals ax plus b is just a. But it's reassuring to see this result emerging from our expression. Something else to take away from this simple example is that we actually differentiated two things at once, a 3x bit and a plus 2 bit. We could have differentiated them separately and then added them together and still got the same result. This interchangeability of the approach is called the sum rule, and it's pretty handy. Let's now try a slightly more complicated example. So, if we take the function f of x equals 5x squared, all we're going to do is take this thing and put it into our differentiation expression at the top. So, f dash of x equals the limit as delta x goes to 0 of, well, we've got 5x plus delta x all squared minus 5x squared, all divided by delta x. And all we're going to do now is work through the algebra and see what comes out the other side. So equals the limit, once again, as delta x goes to 0 of, and let's expand this thing out. So we're going to think x plus delta x squared, we're going to get x squared plus 2x delta x plus delta x squared. So which means we're going to get 5x squared plus 10x delta x plus 5 delta x squared. Once again, minus our 5x squared here. And all of that is divided by delta x. And now what have we got on this top row here? So we've got a pair of 5x squareds. So we can get rid of those because it's 5x squared and minus 5x squared over here. Okay, and we can also see that we've got a delta x in both the top terms and also in this bottom term here. So we can get rid of that with this and this over here. Okay, so let's write that line again. So we can now say it's the limit as delta x goes to 0 of, we've just got 10x plus 5 delta x. Okay, and we're looking at this thing. So it's saying the limit as delta x goes to 0 of this expression here. Now, only the second term has got a delta x in it. So what's going to happen? As our delta x goes to 0, we're going to just forget about this term. It's going to become extremely small. So we can write that this is equal to just 10x. So the derivative of the expression 5x squared is just 10x. We can generalize the lesson from this example to a rule for handling functions with powers of x. For example, if we take the function f of x equals ax to the power of b and substitute it into our differentiation expression, we will find that the derivative is always f dash of x equals abx to the power of b minus 1. So the original power gets multiplied to the front, and then the new power is just one less than it was before. This is known as the power rule, and you can put this into your calculus toolbox along with the sum rule that we saw earlier. So, you've now seen two examples in which we've applied the limit of rise over run method to differentiate two simple functions. But as you can probably imagine, if we wanted to differentiate a long, complicated expression, this process is going to become quite tedious. What we're going to see in later videos are more rules, like the sum rule and the power rule, which will help us speed up the process. However, before we do that, we're just going to look at some fairly magical special case functions which differentiate in an interesting way. In this video, we're going to run through 3 special case functions which give us interesting results when differentiated. The first example we're going to work through is the function f of x equals 1 over x, which you can see plotted in the corner. Now take a minute to notice that the gradient of this function is negative everywhere, except at the point x equals 0, where we can't see what it is. And actually, something quite interesting must be happening at this point, as on the negative side the function drops down, presumably towards negative infinity, but then it somehow re-emerges from above on the positive side. This sudden break in our otherwise smooth function is what we refer to as a discontinuity. We've mentioned already that the operation divide by 0 is undefined, which means that this function simply doesn't have a value at the point x equals 0. But what about the gradient? Well, let's sub our function into the differentiation expression to investigate. So if we take it f of x equals 1 over x, we can say that f dash of x must equal the limit as delta x goes to 0 of 1 over x plus delta x minus 1 over x, all divided by delta x. And we look at this thing and we say we're going to have to make this top row, the numerator, have a single fraction. So we're going to have to combine these 2 fractions here, which means that we're going to have to make the denominators the same. So we'll multiply top and bottom by x here, and top and bottom by x plus delta x here. So we can say that the limit of x over x brackets x plus delta x minus x plus delta x over x brackets x plus delta x, all divided by, once again, delta x. Looking at these 2, we can see that we've got an x and a minus x, both with the same denominator. So we can subtract these now. So this cancels with this. So we can say, OK, this thing is going to be the limit of minus delta x divided by x brackets x plus delta x, all divided by delta x. Now at this point, you can see that you've got a delta x at the very top and a delta x at the bottom. So once again, these 2 terms cancel each other out. And what you're left with is the limit as delta x goes to 0 of minus 1 divided by x squared, we're going to open up this bracket, plus x delta x. And this, once again, is where the magic of limits comes into play. So we look at this function and we say, OK, this term here has got a delta x in it. This means that as delta x becomes very, very small, this term itself is going to become very small and therefore eventually become irrelevant. So what we can say is, as we apply our limit, we can actually ignore this term here entirely. And we get minus 1 divided by x squared, which looks like this. So as we realized just by looking, this derivative function is negative everywhere. And like our base function, the derivative is also undefined at x equals 0. The second function we're going to look at, I'll start simply by explaining what it does. It's a function that has the special property that the value of the function, f of x, is always equal to the value of its own gradient, f dash of x. Now there is a boring function which has this property, which is the function f of x equals 0, because as it's a horizontal line, clearly both the function and the gradient are 0 everywhere. But there's also a much more interesting case. We're not going to work through the rigorous derivation, but we can skip through some of the more interesting bits. So let's start by noticing that our mystery function must always either be positive or always be negative, as if it ever tried to cross the horizontal axis, then both the function and the gradient would be 0, and so it would get stuck. So we'd just be at our boring function 0 again. The next thing to realise is that by virtue of always increasing or always decreasing, it can never return to the same value again. Plenty of functions could fit these criteria, and focusing on the positive case, they all look something like this. However, besides the zero function, there is only one function that will satisfy all our demands. This is the exponential function, e to the x, where e is Euler's number, named after the 18th century mathematician. The number e, which is approximately 2.718, is very important for the study of calculus, but more than that, e, like pi, turns up all over mathematics and seems to be written all over the fabric of the universe. As differentiating e to the x gives us e to the x, clearly we can just keep differentiating this thing as many times as we'd like and nothing's going to change. This self-similarity is going to come in very handy. The last special case function that we're going to talk about in this video are the trigonometric functions, sine and cosine. You may recall that for a right-angled triangle, sine of angle x multiplied by the hypotenuse r gives you the length of the opposite side to the angle. And the graph of sine x looks like this. Let's take a look at this function and see if we can work out what shape its derivative would be by I. So, sine x starts with a positive gradient, which gently decreases until it's 0 at the top of the bump, and then it starts being negative again until it gets to the bottom of the next bump, and it turns out that the derivative of sine x is actually just cosine x. Now, what happens when we differentiate cosine x? Well, actually, we get minus sine x. Differentiating a third time gives us minus cosine x, and then amazingly, differentiating a fourth time brings us all the way back to our original function, sine x. And then the pattern, of course, repeats. This self-similarity may remind you somewhat of the exponential function we discussed above, and that is because these trigonometric functions are actually just exponentials in disguise, albeit quite a convincing disguise, which we won't be discussing here. Many of the details of the functions that we've talked about in this video were skimmed over rather quickly. But for the benefit of this particular course, all I need you to understand is that differentiation is fundamentally quite a simple concept. Even when you might not be able to battle through all the algebra, you're ultimately still just looking for the rise over run gradient at each point. This pragmatic approach to calculus is going to come up again when we start talking about calculating gradients with computers. Sometimes we really can just find an equation for the gradient as we've been doing for all of our examples so far. However, if instead of a nice smooth function, we just have discrete data points, then it can seem as if there's nothing for us to differentiate. But, as we shall see, rise over run comes back once again to save the day. Now that we've defined the differentiation operation in terms of an exact mathematical formula, it's become clear that even for relatively simple functions, calculating derivatives can be quite tedious. However, mathematicians have found a variety of convenient rules that allow us to avoid working through the limit of rise over run operation whenever possible. So far, we've met the sum rule and the power rule. In this video, we will cover a convenient shortcut for differentiating the product of two functions, which sensibly enough is called the product rule. It is of course possible to derive the product rule purely algebraically, but it doesn't really help you to develop much insight into what's going on. For all the topics covered in this course, I'd always prefer you came away with some degree of intuitive understanding rather than just watching me grind through examples. So, let's see if we can make any progress by drawing things. Imagine a rectangle where the length of one side is the function f of x and the other side is the function g of x. This means that the product of these two functions must give us the rectangle's area, which we can call a of x. Now consider that if we differentiate f of x times g of x, what we're really looking for is the change in area of our rectangle as we vary x. So let's see what happens to the area when we increase x by some small amount, delta x. A quick footnote here. For the case we've shown, we've picked a particularly friendly pair of functions where they both happen to increase with x. However, this won't necessarily always be the case, but it does just make drawing things a lot easier, and the conclusions would ultimately be the same. we can now divide up our rectangle into 4 regions, one of which was our original area, A of x. As the total edge length along the top is now f of x plus delta x, this means that the width of the new region must be the difference between the original width and the new width. And of course, the same logic applies to the height. We can now write an expression for just the extra area, which we will call delta A. This is the sum of the area of the 3 new rectangles. I want to avoid a drawn-out conversation about limits, but fundamentally, I hope you can see that as delta x goes to 0, although all of the new rectangles will shrink, it's the smallest rectangle that is going to shrink the fastest. This is the intuition that justifies how we can ultimately ignore the small rectangle and leave its contribution to the area out of our differential expression altogether. Now that we've got our expression for approximating delta x, we return to our original question. What is the derivative of a with respect to x? So we want the limit of delta a divided by x, i.e. rise over run, which means we also need to divide the right-hand side by delta x. We are so close at this point, all we need to do is slightly rearrange this equation. So firstly, by splitting it into 2 fractions, and then secondly, by moving f of x and g of x out of the numerators. What I hope you can see now is that the first part contains the definition of the derivative of g of x, and the second part contains the derivative of f of x, which means that we are now ready to write down our final expression for the derivative of a with respect to x, which has now just been reduced to this. The derivative of a of x is just f of x times the derivative of g of x plus g of x times the derivative of f of x. So, we can now add the product rule to the list of tools in our calculus toolbox. If we want to differentiate the product of 2 functions, f of x and g of x, we simply find the sum of f of x, g dash of x, and g of x, f dash of x. This is going to come in really handy in later videos as we start to deal with some more complicated functions. See you then. So far, we have learned about the sum rule, the power rule, and the product rule. In this video, we will be discussing our 4th and final tool for this module, which is called the chain rule. Following this, our toolbox will then be sufficiently well stocked that we'll be ready to start tackling some heftier, more interesting problems. Sometimes we use functions as the inputs of other functions. As you can probably imagine, describing this can get a little bit confusing. So what we're going to do is give each of our functions meanings so that we can hopefully keep track of what's going on. Consider the nested function h of p of m. We have the function h, which is describing how happy I am, as a function of p, how many pizzas I've eaten that day. Then the pizzas I get to eat per day is itself a function of m, which is how much money I make. So we're still ultimately relating money to happiness, but via the concept of pizza. This nested function scenario comes up a lot in science and engineering as you relate chains of concepts together. And I suppose this particular example I've chosen here also gives you some insight into my priorities in life. So first I'm going to give you the function relating happiness and pizza, which has the following polynomial form. h of p equals minus a third p squared plus p plus 1 over 5, which is easily understandable from a plot. What we can see is that although without any pizza it's still possible to be happy in principle, my peak happiness is with about 1.5 pizzas. Any more pizza than this and I become less happy, and then beyond about 3 pizzas my happiness becomes rapidly negative. Next is our function relating pizza and money. P of m equals e to the power of m minus 1, which is also fairly straightforward to understand by looking at a plot. If you've got no money, you can't buy any pizza. But the more money you have, your pizza purchasing power increases exponentially. As at first you can take advantage of bulk buy discounts, but as you start getting really rich, you can buy your own pizza oven and eventually even build your own pizza factory. What we'd like to know is, by considering how much money I have now, how much effort should I put into making more if my aim is to be happy? To work this out, we're going to need to know what the rate of change of happiness is with respect to money, which is of course just dh by dm. For now, this relatively simple example, we could just directly substitute our pizza money function into our happiness pizza function, which would give us this, and then differentiate this thing directly. However, the chain rule provides us with a more elegant approach, which importantly will still work even for complicated functions where direct substitution like this may not be an option. Consider the derivative of h with respect to p and of p with respect to m. You'll notice that in this particular notation convention, where the derivatives are represented by quotients, the product of these two quantities looks like it would give you the desired function dh by dm. And in actual fact, this is a perfectly sensible way to think about what's going on. This approach is called the chain rule because in a sense we are making a chain of derivative relationships. Now this is certainly not what you might describe as a formal derivation, but it is already good enough to enable you to make use of the chain rule effectively. So let's now apply this rule to our function. Firstly, let's differentiate our two functions, which give us dh by dp equals 1 minus 2 over 3p. dp by dm equals e to the power of m. And then multiplying these together is simple enough. However, we just need to remember that if we don't want pizza's p to appear in our final expression, then we just need to sub in our expression for p in terms of m. And then finally, by simply rearranging the terms, we recover the expression that we saw at the start of the video. So dh by dm equals 1/3 e to the m times 5 minus 2 e to the power of m. And there we have it. Now don't forget that although for this simple example the chain rule didn't save us a huge amount of time compared to substituting in before the differentiation, don't let that fool you. What's magic about the chain rule is that for some real-world applications, we may not have a nice analytical expression for our function, but we may still have the derivatives. So being able to simply combine them with the chain rule becomes very powerful indeed. Before we finish, let's have a quick look at our money happiness function and its derivative on a graph. As we can see, if you're broke and it's really worthwhile making some money, but the benefit of getting more, especially once you have enough pizza, decreases dramatically and quickly becomes negative. We now have a fourth and final tool for the module, and in the next video we'll be putting them all to use in an example. In this video, we're going to work through a nasty looking function that will require us to use all 4 of the time-saving rules that we've learnt so far. To make matters worse, this function isn't going to describe anything familiar, so we'll just be flying blind and have to trust the maths. This will hopefully give you the confidence to dive into questions in the following exercise. Consider the rather nasty function f of x equals sine of 2x to the power of 5 plus 3x, all over e to the 7x. The essence of the sum, product, and chain rules are all about breaking your function down into manageable pieces. So the first thing to spot is that although it is currently expressed as a fraction, we can rewrite f of x as a product by moving the denominator up and raising it to the power of minus 1. There is actually another rule specifically for dealing with fractions directly called the quotient rule, but it requires memorizing an extra expression, so we're not going to cover it in this course, as you can always use the approach that we've used here and rewrite your fraction as a product. Next, we'll split f of x up into the 2 parts of the product and work out how to differentiate each part separately, ready to apply the product rule later on. Let's start with the first part, which we can call g of x. We've got the trigonometric function sine applied to a polynomial 2x to the 5 plus 3x. This is a classic target for the chain rule. So all we need to do is take our function and split it up into the 2 parts in order to apply the chain rule. So we can take g of u equals sine of u, and u of x equals 2x to the power of 5 plus 3x. Now we've got these 2 separate functions and we're going to want to differentiate each of them in order to apply the chain rule. So we say, okay, g dash of u is going to just equal sine differentiates to cos, so cos u, and u dash of x is going to equal 10 x to the power of 4 plus 3. Now we've got these two expressions, and I'm going to use a mixed notation for convenience. And I'm going to say, okay, well, dg by du multiplied by du by dx is going to give us, so we've got cos of u multiplied by 10x to the power of 4 plus 3. And now we're going to want to have a final expression that doesn't include a u. So we can think about these two cancelling each other out, and we get dg by dx. And this just equals, okay, cos of u, which is just 2x to the power of 5 plus 3x, multiplied by 10x to the power of 4 plus 3. And that's it. We now have an expression for the derivative of g of x, and already we've made use of the chain rule, the sum rule, and the power rule. Now for the second half of our original expression, which we will call h of x, once again we can simply apply the chain rule after splitting our function up. So we can say that h of v equals e to the v, and v of x equals minus 7x. Now once again, we've got our two functions, we just want to find the derivatives. So h prime of v is just going to equal, well, we've seen this one before, e to the v again. And v prime of x is going to just be minus 7. So combining these two back together and using different notation, we can say that dh by dv multiplied by dv by dx is just going to give us, we've got minus 7 times e to the minus 7x. And actually, already all of our v's have disappeared, so this is already our final expression. As we now have expressions for the derivatives of both parts of our product, we can just apply the product rule to generate the final answer. And that's it. We could rearrange and factorize this in various fancy ways, or even express it in terms of the original function. However, there is a saying amongst coders that I think can be applied quite generally, which is that premature optimization is the root of all evil, which in this case means don't spend time tidying things up and rearranging them until that you're sure that you've finished making a mess. I hope that you've managed to follow along with this example and will now have the confidence to apply our 4 rules to other problems yourself. In calculus, it's often the case that some initially scary-looking functions, like the one we worked with just now, turn out to be easy to tame if you have the right tools. Meanwhile, other seemingly simple functions occasionally turn out to be beasts. But this can also be fun, so happy hunting. That brings us to the end of Module 1. I hope those of you familiar with calculus from high school still managed to find this a useful refresher, and for those of you new to calculus, well done for sticking it out to the end of the first module. In the rest of this course, we're going to be extending our analysis of functions to multivariable systems, and also applying calculus to some interesting data analysis problems. However, the basic ideas that we learnt in this module, like the limit of rise over run operation, will be at the core of everything we'll be doing. So if you're happy so far, then you're in a great position to make it through to the end. See you in Module 2. Welcome to Module 2 of this course on calculus. As I mentioned at the end of the first module, if you're happy with the concept of differentiation, then in many ways everything we add from here will just be extensions of this core idea, as well as some interesting applications. The title of this course is Multivariate Calculus, so you won't be surprised to hear that we are now going to generalize the concept of gradients to multivariable systems. The words multivariable and multivariate are typically used interchangeably, and I will undoubtedly be using both in this module. There is, however, a subtle difference between these two terms, which is related to whether there are multiple input variables or multiple output variables, or both. But this distinction is not critical in the study of calculus that we're doing here, so we can leave it to the statisticians to sweat over. With more than one variable to play with, we will now be able to use calculus to help us navigate around high-dimensional spaces, and hopefully by the end of the module, we'll find some treasure. See you then. In the first module, we started by trying to develop a strong visual intuition relating derivatives to the gradient of a function at each point. We then followed this up by describing 4 handy rules to help speed up the process of finding derivatives. However, all of the examples we looked at were for systems involving a single variable. So now we're going to have to see what happens when we apply the same idea to systems with many variables, known as multivariate systems. But before we do that, we need to talk about what a variable is in the first place. Previously, we've shown examples of problems where one of the variables is a function of the other, i.e. y equals f of x. But where it wouldn't necessarily make sense to say that x equals g of y. For example, a vehicle's speed is clearly a function of time, as at each time the vehicle can only have one speed. However, we could not say that the time was a function of the vehicle's speed, as there might be multiple times at which the vehicle was travelling at any given speed. This is why we typically refer to the speed as a dependent variable, as it depends on time, and so time can be thought of as an independent variable in this particular context. Typically, when you first learn calculus, you take functions containing variables and constants, and then differentiate the dependent variables, such as speed, with respect to independent variables like time. However, what gets labelled as a constant or a variable can be subtler than you might think and will require you to understand the context of the problem being described. Let's continue using the example of a car to see how this might come up. Consider the following highly simplified expression relating the force F generated by a car's engine to its mass m, acceleration a, aerodynamic drag d, and velocity v. If you're driving a car, then you can change your speed and acceleration by pressing the accelerator pedal to adjust the force. But the mass and the drag are fixed features of the car's design. This means that we would call the force an independent variable as you control it directly, but your speed and acceleration depend on the variables as they are consequences of your applied force. Your mass and drag coefficients are clearly constants in this context. However, if you are a car designer looking to design each engine size in a new fleet, perhaps your market research has given you a specific acceleration and speed target. So in this context now, your force is still the independent variable, but now speed and acceleration are constants, whereas the mass and drag have become variables which you can adjust by redesigning your car. We refer to these slightly confusing variable design constants as parameters. We often think of varying them as exploring a family of similar functions, rather than describing them as variables in their own right. But these are largely engineering distinctions and not the kind of thing that would worry a mathematician. As you will see later in this course, when fitting functions to some data, it's the parameters of our fitting function which we are varying to find the best fit, which means that we'll have to differentiate with respect to these parameters. There is still some logic at work here, but my advice to you is just don't worry about it too much. The key takeaway here is you can in principle differentiate any term with respect to any other, so don't get caught off guard when things you thought were constants suddenly start to vary. Let's now look at a different example. Imagine that you wanted to manufacture a metal can. So you need to understand the relationship between the various key design parameters. We can start by writing a reasonable approximation for the can's empty mass m by breaking the area down into pieces. So the circles on top and bottom are pi r squared each, and when we unroll the body we get a rectangle where the width must be the same as the circumference of the circle, i.e. 2 pi r, and we'll just call the height h. So, taking these areas and multiplying them by a thickness t, we get the total volume of metal in the can. Finally, multiplying this by the metal's density, ρ, we get its mass. So, we can say that the mass, m, is going to equal the area of these two little circles, pi r squared times 2 of course, plus the area of the rectangle in the middle, so that's the circumference, 2 pi r, multiplied by the height h, and both of these are going to be multiplied by the thickness t and the density ρ. So t ρ and t ρ. I've written it in this long form here to make life a bit easier later on. At this point, what should we label as a constant or a variable? Well, with the exception of pi, which is definitely a constant for this universe, it's not entirely clear. We could in principle change any of the radius, the height, the wall thickness, even the material's density. So let's find the derivative of the can's mass with respect to each of them. To calculate these, all we do is, when differentiating with respect to a certain variable, simply consider all of the others to behave as constants. So, starting with an easy one, let's try h. So dm by dh is going to equal this thing, 2 pi rt rho. As the first term did not contain the variable h, and we're treating all the other terms as constants, then just like last week, a constant simply differentiates to 0, so we ignored it. Whereas for the second term, it does contain h, and so it's just multiplied by some constants. So differentiating this just leaves those constants. We can see from this expression that the partial derivative with respect to h no longer even contains h, which is what you would expect, as the mass will vary linearly with the height when all else is kept constant. Notice that instead of using the normal d that we saw from doing derivatives in last module, we must use the curly partial symbol, which signifies that you've differentiated a function of more than one variable. Let's now find the partial derivative with respect to the other variables, starting with r. So partial m by partial r is going to equal, so there's an r squared term here which differentiates to 2r, so we're going to have 4 pi r t rho, and this term just contains an r, so the r disappears, 2 pi ht rho. Next we're going to do the variable t, and we can say dm by dt is going to equal, well there's just a t in here so it's not very exciting, 2 pi r squared rho plus 2 pi rh rho. And finally, all we've got left is rho, so we can say dm by d rho is just going to equal 2 pi r squared t, 2 pi r squared t, and 2 pi r ht plus 2 pi r ht. And really, although this is quite a straightforward example, that's basically it for partial differentiation. It's no more complicated than univariate calculus we met last module, the only difference being that you have to be careful to keep track of what you're considering to be held constant when you take each derivative. I hope this short introduction to multivariate calculus has helped you see that this concept is nothing to be intimidated by. Partial differentiation is essentially just taking a multidimensional problem and pretending that it's just a standard 1D problem when we consider each variable separately. I look forward to showing you the pretty amazing things that we can use this concept for later in the module. See you then. We've already seen how to think about partial differentiation as just a simple extension of the single variable method that we derived in the last module. In this video, we're going to explore some slightly more complicated partial differential examples, and we're also going to build something called the total derivative of a function. So, let's dive straight into a slightly more tricky problem than we saw last time. Consider the function f of x, y, and z equals sine of x e to the power of y z squared. We're now just going to work through and find the derivatives with respect to each of these three variables. So, let's start with x. As the exponential term does not refer to x, we can treat it as a constant, and sine, as we saw last week, differentiates to cosine. So we can write df by dx is just going to equal cos x e to the y z squared. Next, we'll differentiate with respect to y. In this case, the sine term does not refer to y, so we treat this as a constant, but for the exponential term, we can either apply the chain rule to it, or just remember that the result of this operation for an exponential will just be to multiply the derivative of the exponent to the front. And the derivative of yz squared with respect to y is just z squared. So we can write df by dy is going to equal sine of x e to the yz squared multiplied by z squared. Lastly, we'll differentiate with respect to z. once again, the only z is in the exponential term. So similar to the previous example, we simply multiply through by the derivative of the exponential with respect to z. So we just get df by dz is going to equal sine x once again, e to the y z squared, and this time the derivative of this thing is 2y z. So, now that we have these three partial derivatives, we're going to introduce a new idea called the total derivative. Imagine that the variables x, y, and z were actually all themselves a function of a single other parameter t, where x equals t minus 1, y equals t squared, and z equals 1 over t. And what we're looking for is the derivative of x with respect to t. In this simple case, we could just substitute for all our three variables directly in terms of t, simplify a little bit, and then differentiate directly with respect to t, which gives us sine of t minus 1 times e. However, in a more complicated scenario with many variables, the expression we needed to differentiate might have become unmanageably complex, and perhaps we won't have a nice analytical expression at all. The alternative approach is to once again use the logic of chain rule to solve this problem, where the derivative with respect to our new variable t is the sum of the chains of the other three variables, as shown in this expression. Since we've already got our three partial derivatives of f with respect to x, y, and z, now we just need to find the derivatives of the three variables with respect to t, and we'll have all the things we need to evaluate our expression. So, dx by dt is clearly 1, dy by dt is 2t, and dz by dt, if you remember from our 1 over t example, is minus t to the power of minus 2. Nothing hugely complicated here. However, when we then sub it into our total derivative expression, you can probably see why I've chosen not to write this all out by hand, as at first the expression is a bit of a monster. However, after substituting for x, y, and z all in terms of t, and then simplifying down again, we can see that the second and third terms are the same, just with opposite signs, and so they will cancel each other out. Then, kind of amazingly, we arrive at the same result as we saw at the beginning of the lecture. So, hopefully now you'll be feeling reasonably comfortable with partial differentiation, as we've already done quite a lot of it, and maybe you can even see why the total derivative function might be quite handy. You are now ready to have a go yourselves in the following exercises, and then you'll have all the pieces that you'll need in place for us to build our partial derivatives into something really useful. See you then. Previously, we saw that we can differentiate functions of multiple variables, and that it isn't much harder than the univariate calculus we met at the start of the course. In this video, we're going to introduce the Jacobian, which brings in some of the ideas from linear algebra to build these partial derivatives into something particularly useful. The concept of the Jacobian can be applied to a variety of different problems, but in the context of getting started with optimization and machine learning, there is a particular scenario that comes up a lot, which is the Jacobian of a single function of many variables. In short, if you have a function of many variables, so f of x1, x2, x3, etc., then the Jacobian is simply a vector where each entry is the partial derivative of f with respect to each one of those variables in turn. By convention, we write this as a row vector rather than a column vector, for reasons that will become clear later in the course. Let's start by looking at a nice simple function to see just how straightforward building a Jacobian can be. Consider the function f of x, y, and z equals x squared y plus 3z. To build the Jacobian, we just find each of the partial derivatives of the function one by one. So we've got df by dx is going to equal, we're just differentiating with respect to x, so we get 2xy when we treat everything else as constants. df by dy is going to equal just x squared, and df by dz is just going to be, so this thing's just a constant and the z disappears, so we just get the number 3. Now bringing all of those together, we just end up with a Jacobian j, which is just going to be 2 xy x squared 3. So, what does this tell us? We now have an algebraic expression for a vector which, when we give it a specific xyz coordinate, will return a vector pointing in the direction of steepest slope of this function. The vector for this particular function has a constant contribution in the z direction, which does not depend on the location selected. For example, at the point 0, 0, 0, we can see that our Jacobian is just going to be j of 0, 0, 0 is just going to be, well, 0, 0 again, but the number 3 over here. So we can see that our Jacobian is a vector of length 3 pointing directly in the z direction. Some of the numerical methods that we will discuss later in this course require us to calculate Jacobians in hundreds of dimensions. However, even for the 3D example we just solved, graphical representation is already quite difficult. So we are now going to drop down to 2 dimensions so that we can actually see what's going on here. But to keep things interesting, we're going to look at a particularly complicated but rather attractive function. So here is the equation that we're going to plot. But I'm showing it to you briefly just so that you can see that even though it is a bit of a monster, I hope you would agree that just with the tools we've seen so far, we really could calculate the partial derivatives of this thing. But you wouldn't really learn anything new from grinding through this. Instead, I'm going to show you the results graphically. So here is this function with the x-axis horizontal and the y-axis vertical, and the colours are indicating the value of z, with the bright regions suggesting high values and the dark regions suggesting low values. Because of the nature of this particular function, I know that nothing interesting happens outside of the regions shown here, so we can forget about it for now. Although this plot is fairly clear, our intuition about the gradient is a bit lacking in this format. So let's briefly make things 3D, where the values of z are now also represented by the height. So, as we said at the start of the video, the Jacobian is simply a vector that we can calculate for each location on this plot, which points in the direction of the steepest uphill slope. Furthermore, the steeper the slope, the greater the magnitude of the Jacobian at that point. Hold the image of this 3D space in your mind as we now go back to 2D. And rather than showing all of the grid points I used to plot the graph, let's instead convert to a contour plot, where just like a map of actual mountains, we will draw lines along the regions of the same height, which for us means the same value of z. This removes a lot of the clutter from the plot, which is useful for the final step that I'd like to show you, which will be adding lots of Jacobian vectors on top of our contour plot. However, before I do that, let's take a look at these 4 points and see if your intuition is now in tune by guessing which one will have the Jacobian with the largest magnitude. Overlaying the Jacobian vector field, we can see that they are clearly all pointing uphill, away from the low dark regions and towards the high bright regions. Also, we see that where the contour lines are tightly packed, this is where we find our largest Jacobian vectors, such as at point A. Whereas at the peaks of the mountains and at the bottom of the valleys, or even out on the wide flat plains, our gradients, and therefore our Jacobians, are small. My hope is that this clear 2-dimensional example will give you the confidence to trust the maths when we come up against much higher dimensional problems later in the course. See you then. In this video, we're going to extend the concept of the Jacobian from vectors up to matrices, which will allow us to describe the rates of change of a vector-valued function. However, before we do this, we are first going to recap by applying what we've learnt so far about Jacobians to another simple system. If we consider the function f of x and y equals e to the power of minus x squared plus y squared, then using our knowledge of partial differentiation, it's fairly straightforward to find its Jacobian vector. So we're now going to do the reverse of our approach from the last time and start by looking at the vector field of the Jacobians. Then see if we can understand how the function must look. Let's start by finding the Jacobian at a few specific points. Firstly, the point -1, 1, which we'll highlight on our axis in pink. Substituting these coordinates into our Jacobian expression and simplifying, we can see a vector pointing directly towards the origin. Next, if we move further out to the point 2, 2, find the Jacobian, we now get a much smaller vector, but pointing, once again, directly at the origin. Lastly, before I reveal the whole vector field, let's look at what's going on at the origin itself. Subbing the point 0, 0 returns the 0 vector, suggesting that the function is flat at this point, which must mean one of three things. Either this point is a maximum, minimum, or something called a saddle, which we'll cover later in this module. However, if we now reveal the rest of the Jacobian vector field, it becomes clear that the origin must be the maximum of this system. Let's now move back to the color map representation of this function, where the brighter regions represent high values of f. So, finally, we can remove the vector field and observe the function in 3D, which I hope matches up with your expectations. Next, we're going to build a Jacobian matrix which describes functions that take a vector as an input, but unlike our previous examples, also give a vector as the output. If we consider the two functions u of x and y equals x plus 2y and v of x and y equals 3y minus 2x, we can think of these as two vector spaces, one containing vectors with coordinates in u, v, and the other with coordinates in x and y. Each point in x, y has a corresponding location in u, v. So, as we move around x, y space, we would expect our corresponding path in u, v space to be quite different, and so it is. For those of you familiar with the linear algebra, you may have guessed already where this is going. We can of course make separate row vector Jacobians for u and v. However, as we are considering u and v to be components of a single vector, it makes more sense to extend our Jacobian by stacking these vectors as rows of a matrix, like this. So, now that we have the structure and motivation for building a Jacobian matrix for vector-valued functions, let's apply this to our example functions and see what we get. So we have u of x, y equals x minus 2y, and we've also got v of x, y equals 3y minus 2x. We can build the Jacobian from these two by simply saying, well, the Jacobian is going to be, let's open some big brackets and say, well, it's du dx, du dy, dv dx, dv dy. So let's just work through it. So du dx is just going to be 1. du dy is just minus 2, dv dx is minus 2 again, and dv dy is 3. Our Jacobian matrix no longer even contains any variables, which is what we should expect when we consider that clearly both u and v are linear functions of x and y, so the gradient must be constant everywhere. Also, this matrix is just the linear transformation from xy space to uv space. So if we were to apply the xy vector 2, 3, we'd get the following. 2, 3, and that's going to equal 2 minus 6, that's minus 4, and minus 4 plus 9, that's 5. Now, this is all well and good, but of course many of the functions that you'll be confronted with will be highly non-linear, and generally much more complicated than the simple linear example that we've just looked at here. However, often they may still be smooth, which means that if we zoom in close enough, we can consider each little region of space to be approximately linear, and therefore, by adding up all the contributions from the Jacobian determinants at each point in space, we can still calculate the change in the size of a region after transformation. A classic example of this occurs when transforming between Cartesian and polar coordinate systems. So if we have a vector expressed in terms of a radius r and the angle up from the x-axis theta, but we'd like them expressed in terms of x and y instead, we can write the following expressions just by thinking about trigonometry. Now we can build the Jacobian matrix and take its determinant. The fact that the result is simply the radius r and not the function theta tells us that as we move along r away from the origin, small regions of space will scale as a function of r, which I hope will make a lot of sense to you when we look at our little animation here. That's all for this video. I hope you will now be able to build Jacobian vectors and matrices for yourself with confidence in the exercises, and more importantly, that your intuition on the meaning of this concept is starting to develop. See you next time. We've now seen that the Jacobian describes the gradient of a multivariable system, and that if you calculate it for a scalar-valued multivariable function, you get a row vector pointing up the direction of greatest slope with a length proportional to the local steepness. In this video, I'm going to briefly introduce a kind of gradient playground to help you further develop your intuition on the Jacobian, which will also set you up for the following exercises. In everyday language, we use the word optimization to describe the process of trying to make something as good as it can be. In mathematics, optimization basically means the same thing, as much of the research is dedicated to finding the input values to functions which correspond to either a maximum or a minimum of a system. Examples of mathematical optimization in action in the real world include the planning of routes through busy cities, the scheduling of production in a factory, or strategy for selecting stocks when trading. If we go back to the simplest function we saw in the last section, and we said that we wanted to find the location of the maximum, we could simply solve this system analytically by first building the Jacobian and then finding the values of x and y which make it equal to 0. However, when the function gets a bit more complicated, finding the maximum or minimum can get a bit tricky. If, as in this case, we still have an analytical expression, then we can at least still find the general expression for the Jacobian. But now simply setting it to 0 is not only much more complicated, but it also is not enough, as this function has multiple locations with 0 gradient. If we assume that all of the maxima and minima of this function can be seen in the region that we're plotting here, then just looking at the surface plot of our function makes it very clear where the tallest peak and deepest trough are. We refer to all the peaks as maxima, but in this case we have a single tallest peak, A, which we will call the global maximum, as well as several local maxima at C and E. Similarly, we refer to all the troughs as minima, and we also have a single deepest point at D, which we call the global minimum, as well as a local minimum at point B. All fairly straightforward. However, there's a very important point here that's perhaps so obvious that you might have missed it. Imagine standing on the surface with its hills and valleys, and we're trying to climb to the top of the highest peak. That's no problem. We just look around, spot the tallest mountain, and walk straight towards it. But what if we were walking at night? This would be much like the scenario where we didn't have a nice analytical expression for our function, so we simply aren't able to plot the whole function and look around. Perhaps each data point is the result of a week-long simulation on a supercomputer, or maybe the outcome of an actual real-world experiment. These nighttime scenarios very commonly arise in optimization and can be very challenging to solve. However, if we're lucky, we might find that using a torch, we can see the Jacobian vectors painted on road signs all around us, and each one would say, peak this way. We would have to remember that although the Jacobians all point uphill, they don't necessarily point to the top of the tallest hill, and you could find yourself walking up to one of the local maxima at C or E. And even worse, when you get there, you'll find that all of the road signs are pointing directly at you. This nighttime hill walking analogy is often used when discussing the problem of optimization. However, it does have some misleading features, such as the fact that when you're really evaluating a function, it's no problem to effectively transport all over the map by teleportation, as you can try the function at many different places, but there's no need to evaluate everywhere in between. And the calculation costs the same, essentially, no matter how far apart the points are. So we're not really walking. Instead, we're going to switch to the analogy of a sandpit with an uneven base. In the following exercises, you're going to try to find the deepest point of a sandpit by measuring the depth at various points using a long stick. This is a very deep sandpit, so once you push the stick down to the bottom, there's no way to move it around sideways. You just have to pull it out and try somewhere else. Also, crucially, just like our night walking scenario, you will have no idea what the peaks and troughs look like at the bottom of the pit, because you can't see, the sand is in the way. As you work through the exercise, I'm hoping that you'll start to pick up on a few of the subtleties of optimization, and hopefully leave you with a few new questions as well. See you next time, and have fun in the sandpit. So, now that you've all spent some time playing in the sandpit, we can introduce an additional concept which relates to multivariate systems called the Hessian. In many ways, the Hessian can be thought of as a simple extension of the Jacobian vector. For the Jacobian, we collected together all of the first-order derivatives of a function into a vector. Now, we're going to collect all of the second-order derivatives together into a matrix, which for a function of n variables would look like this. However, this is one of those scenarios where using an abbreviated notation style comes in really handy. We saw in the previous module that we can just keep differentiating a function using the same method to find higher and higher order derivatives. Similarly, for a partial derivative, if you want to find the second derivative with respect to x1, then x2, it's as simple as just differentiating with respect to x1, assuming all the other variables are constant, and then differentiating with respect to x2, again, assuming all the other variables are constant. As you can see, from this general form, our Hessian matrix will be an n by n square matrix, where n is the number of variables in our function f. Let's now take a look at a quick example. It often makes life easier to find the Jacobian first and then differentiate its terms again to find the Hessian. So for our function, f of x, y, and z equals x squared yz. So f of x, y, z equals x squared y z. We're going to first build the Jacobian for this thing, which of course is going to be j equals, so we've got differentiate with respect to x, we get 2x y z. Differentiate with respect to y, we're just going to get x squared z, and differentiate with respect to z, x squared y. Now, using this, we can then think about differentiating again with respect to each of the variables, which will then give us our Hessian matrix. So h is just going to equal, we'll put a big bracket here. So we want to take this thing and differentiate it with respect to x again. So we're going to get 2yz. So the next term along, we're going to differentiate this thing with respect to y. 2xz, and again with respect to z, 2xy. Okay, now we'll take the next row and we'll say we're going to differentiate this thing with respect to x, then y, then z. So you get 2xz. We're going to differentiate with respect to y, so we're going to get nothing. And we're going to differentiate this thing with respect to z, and we get x squared. Lastly, take this term, make the last row, differentiate with respect to x, we get 2xy. And then with respect to y, we get x squared. And with respect to z, we get nothing. So, one thing to notice here is that our Hessian matrix is symmetrical across the leading diagonal. So actually, once I'd worked out the top right region, I could just have written these directly in for the bottom left region. This will always be true if the function is continuous, meaning that it has no sudden step changes. We could now simply pass our Hessian an x, y, z coordinate, and it will return a matrix of numbers which hopefully tells us something about that point in the space. In order to visualize this, we're going to have to drop down to 2 dimensions again. Consider the simple function f of x and y equals x squared plus y squared. Calculating the Jacobian and the Hessian are both fairly straightforward, and hopefully you could have visualized how this function would have looked in your head. However, if you hadn't known what function we were dealing with and calculated the value of the Jacobian at the point 0, 0, you'd have seen that the gradient vector was also 0. But how would you know whether this thing was a maximum or a minimum at that point? You could of course go and check some other point and see if it was above or below, but this isn't very robust. Instead, we can look at the Hessian, which in this simple case is no longer even a function of x or y. Its determinant is clearly just 2 times 2 minus 0 times 0, which is 4. The power of the Hessian is firstly that if its determinant is positive, we know we are dealing with either a maximum or a minimum. Secondly, we then just look at the first term, which is sitting at the top left-hand corner of the Hessian. If this guy is also positive, we know we've got a minimum, as in this particular case. Whereas if it's negative, we've got a maximum. Lastly, slightly modifying our function to include a minus sign and recalculating our Jacobian and our Hessian determinant, we now see the third interesting case. This time our Hessian determinant is negative, so we know that we're not dealing with a maximum or a minimum. But clearly at this point 0, 0, the gradient is flat. So what's going on? Well, if you look at the animation, what we've got here is a location with 0 gradient, but with slopes coming down towards it in one direction, but up towards it in the other. We call this kind of feature a saddle point, and they can also cause a lot of confusion when searching for a peak. In the last module of this course, you're also going to see another way that the Hessian can help us with optimization. But for now, we've simply got another tool to help you navigate the sandpit. See you next time. In this module, we've discussed how to think about two-dimensional functions as landscapes, and we've also seen that we can construct Jacobian vectors which tell us both the direction and the magnitude of the gradient at each point in space. Last video, we added one further tool to our toolbox, which allowed us to double-check what kind of feature we were standing on when we landed on a point with a 0 gradient. These concepts will all be very useful to develop your understanding of optimization problems and have also let you see why multivariate calculus is worth knowing. However, in this video we are going to remind ourselves about two features of real systems which so far we've avoided. Firstly, for many applications of optimization, such as in the training of neural networks, you are going to be dealing with a lot more than 2 dimensions, potentially hundreds or thousands of dimensions. This means that we can no longer draw our nice surface and climb its mountains. All the same math still applies, but we now have to use our 2D intuition to guide us and enable us to trust the maths. Secondly, as we mentioned briefly before, even if you do just have a 2D problem, very often you might not have a nice analytical function to describe it, and calculating each point could be very expensive. So even though, in principle, a plot could possibly be drawn, you wouldn't be able to afford either the supercomputer time or perhaps the laboratory staff to fully populate this thing. Thirdly, all the lovely functions that we've dealt with so far were smooth and well behaved. However, what if our function contains a sharp feature like a discontinuity? This would certainly make navigating the sandpit a bit more confusing. Lastly, there are a variety of factors that may result in a function being noisy, which, as I'm sure you can imagine, might make our Jacobian vectors pretty useless unless we were careful. So, this brings us nicely to the second topic in this video, which is a question that I hope you've all been screaming at your screens for the past few minutes. If, as I said a minute ago, we don't even have the function that we're trying to optimize, how on earth are we supposed to build a Jacobian out of the partial derivatives? This is an excellent question, and leads us to another massive area of research called numerical methods. There are many problems which either don't have a nice explicit formula for the answer or do have a formula, but solving it directly would take until the end of time. To fight back against the universe mocking us in this way, we have developed a range of techniques that allow us to generate approximate solutions. One particular approach that is relevant to our discussion of the Jacobian actually takes us right back to the first few lectures on this course, where we defined the derivative. We started by using an approximation based on the rise of a run calculated over a finite interval, and then looked at what happens as this interval approached 0. All we're doing with the finite difference method is accepting that we're not going to work out the value of the function at every single point in space, so we're just going to use the points that we do have and build an approximation for the gradient based on that. In the example shown here, we have already calculated lots of points on this one-dimensional function, but clearly that's not going to be practical for higher dimensional scenarios. So all we do is take this logic one step further and say, if we start from an initial location and we would like to approximate the Jacobian, we will simply approximate each partial derivative in turn. So taking a small step in x allows us to calculate an approximate partial derivative in x, and a small step in y gives our approximate partial in y. Two things to bear in mind here. Firstly, how big should our little step be? Well, this has to be a balance, as if it's too big, you will make a bad approximation for reasons that I hope will be obvious by this point. But if it's too small, then we might run into some numerical issues. Just remember, when your computer calculates the value of the function at a point, it only stores it to a certain number of significant figures. So if your point is too close, your computer might not register any change at all. Second, as we mentioned earlier, what happens if your data is a bit noisy? To deal with this case, many different approaches have been developed, but perhaps the simplest is just to calculate the gradient using a few different step sizes and take some kind of average. This brings us to the end of this video. So I hope you can see that once we leave the world of nice, smooth functions and enter the real world of noisy data and computationally expensive functions, things start to get a lot more interesting. See you next time. That's it for Module 2 of the course. I hope you're now feeling reasonably confident about multivariate calculus and able to navigate multidimensional hyper sandpits of your own in future. See you in the next module, where we'll be discussing the multivariate chain rule and how it can help you optimize the weightings in a neural network. See you then. Welcome to Module 3 of the course. In the previous two modules, we've seen how to differentiate functions in single and multivariable spaces, as well as hopefully developing some intuition about what's really going on when we do this. We've also learned a selection of useful tools for both rapidly calculating derivatives and for navigating high-dimensional spaces. In this module, we're going to upgrade the univariate chain rule so that it can tackle multivariate functions, and then see an example of where this might come in handy. See you then. In the last module, we saw something called the total derivative, which showed us that when we have a multivariable function, such as f of x, y, and z, but the variables x, y, and z were themselves each a function of some additional variable t, then if we want to calculate the derivative of f with respect to t, we can use this expression, which is simply the sum of the chains relating f to t through each of its three variables. This allowed us to calculate the result in a piecewise manner, rather than substituting everything in at the start, and computers are really good at solving piecewise problems quickly. What we're now going to do is generalize this concept and also simplify the notation a little. If we had a function f of n variables, x1, x2, x3, all the way up to xn, I can write this as just f of x, but now you'll notice that I've written the x in bold, just to help you remember that this x represents a sequence of variables, which we'll now more conveniently think of as an n-dimensional vector. Once again, each of the components of our x vector are themselves functions of some other variable t, and what we'd like to know is the derivative of f with respect to t. At this point, we're going to need some more space to write. So we'll keep our function f at the top, but you'll just have to remember that each component of x is also a function of t. Now we're looking to once again build an expression linking f to t through the sum of the chains of each of its variables. So we're going to need all the partial derivatives of f with respect to x, as well as the derivatives of each component of x with respect to t. Once again, we're going to store all of these objects in a pair of n-dimensional vectors. Finally, we're looking to build a multivariable chain rule expression, so we are looking to find the sum of the product of each pair of terms in the same position in each vector. Thinking back to our linear algebra, this is exactly what the dot product does. But there is no need for us to write out these vectors in full, so we can simply write the dot of our two multivariable derivative expressions. And that's it. We now have our generalized form of the multivariable chain rule expressed nice and neatly. So we can now update our list of tools to reflect this. But actually, although we've seen this in practice already in the last module, it's worth pointing out that all the rest of our time-saving rules already work for multivariate problems as they are. So we'll be ready to put these into practice very soon. See you then. Last video, we finished up with an expression for the multivariate chain rule. In this video, we're going to start by picking up one more little detail which you might have already spotted, and then follow this up by adding another link to our chain. If we have a function f of x, where x is a vector in which each term in x depends on t, which we can compactly write like this, we also have our compact form of the multivariate chain rule to go with it. What I hope you might have noticed last time is that our vector of partial derivatives, df by dx, is just the same as the Jacobian vector which we saw last module, except that we wrote it as a column instead of a row vector. So from our knowledge of linear algebra, we can say that df by dx must be the transpose of the Jacobian of f. the last thing to realize is that taking the dot product of two column vectors is the same operation as multiplying a row vector by a column vector. So finally, we can see that our old friend the Jacobian offers us perhaps the most convenient representation of the multivariate chain rule. Next, we're going to see that the chain rule still works for more than two links. To start us off, we'll work through a really quick univariate example where we're going to add in another function separating f from t. So we can say f of x is going to equal 5x, and we can have x of u now can equal 1 minus u, and u of t finally can be t squared. So we've got three functions, and we're separating f from t now by an extra step. Of course, we can just sub in each step into each other and find an expression for f as a function directly of t, where we say, well, it's going to be 5 of whatever x is, and x is 1 minus whatever u is, and u is t squared. So this thing goes to 5 minus 5t squared. And of course, we can now directly differentiate this thing and say df by dt equals minus 10t. Or we can apply a two-step chain rule and say the following. So we can have df by dt is going to equal df by dx times dx by du, and finally du by dt. Okay? Now subbing in for each of our terms, we just get, well, this thing's going to equal df by dt is, so df by dx is just 5. We're going to multiply that by dx by du, which is just minus 1. And finally, du by dt is just going to be 2t. So once again, we're going to recover the same answer, which is minus 10t. So we can see that this approach works for chains of univariate functions, and we could extend it out to as many intermediary functions between f and t as we'd like. But what about the multivariate case? Well, the chain rule does work here too, but we do just have to pay attention to a few extra details. Let's start by considering the function f of x of u of t again, where the function f takes the vector x as an input, but this time x is a vector-valued function, which also takes a vector u as its input. As the last video, the bold symbols indicate vectors. So u is again a vector-valued function, and it takes the scalar t as its input. Ultimately, we are still relating the scalar input t to a scalar output f, but we're doing this via two intermediary vector-valued functions x and u. If once again we'd like to know the derivative of f with respect to t, we can essentially write the same expression as the univariate case, except that now several of our terms are in bold. We've already seen that differentiating the scalar-valued function f with respect to its input vector x gives us the Jacobian row vector. We've also seen that differentiating the vector-valued function u with respect to the scalar variable t gives us a column vector of derivatives. But what about the middle term, dx by du? Well, for the function x, we need to find the derivative of each of the two output variables with respect to each of the two input variables. So we end up with 4 terms in total, which, as we saw in the last module, can be conveniently arranged as a matrix. We still refer to this object as a Jacobian, so we can now say that the derivative of f with respect to t is the product of the Jacobian of f with the Jacobian of x and the derivative vector of u. Notice that the dimensions of these vectors and matrices, as shown here, are such that this operation is possible, and that they will return as scalar just as we expected. That's it for this video. I hope you're now starting to see the various threads of linear algebra and multivariate calculus weave together. See you in the next one. In this video, I'm going to introduce to you the concept of artificial neural networks in just enough detail that we will be ready to see how the multivariate chain rule is crucial for bringing them to life. I think it's safe to assume that everyone watching this video will at least have heard of neural networks, and you're probably also aware that they've turned out to be an extremely powerful tool when applied to a wide variety of important real-world problems, including image recognition and language translation. But how do they work? You will often see nice diagrams like this one, where the circles are our neurons and the lines are the network of connections between them. This may sound a long way removed from the topics we've covered so far, but fundamentally, a neural network is just a mathematical function, which takes a variable in and gives you another variable back, where both of these variables could be vectors. Let's now have a look at the simplest possible case so that we can translate these diagrams into some formulae. Here, we have a network which takes in a single scalar variable, which we'll call a0, and returns another scalar, a1. We can write this function down as follows. a1 equals sigma of w times a0 plus b, where b and w are just numbers, but sigma is itself a function. It's useful at this point to give each of these terms a name, as it will help you keep track of what's going on when things get a bit more complicated. So our a terms are called activities, w is a weight, b is a bias, and sigma is what we call an activation function. Now, you might be thinking, how come all the terms use a sensible letter except for sigma? But the answer to this comes from the fact that it is sigma that gives neural networks their association to the brain. Neurons in the brain receive information from their neighbours through chemical and electrical stimulation, and when the sum of all these stimulations goes beyond a certain threshold amount, the neuron is suddenly activated and starts stimulating its neighbours in turn. An example of a function which has this thresholding property is the hyperbolic tangent function tanh, which is a nice, well-behaved function with a range from -1 to 1. You may not have met tanh before, but it's just the ratio of some exponential terms and nothing your calculus tools can't already handle. Tanh actually belongs to a family of similar functions, all with this characteristic S shape called sigmoids, hence why we use sigma for this term. So here we are with our nonlinear function that we can evaluate on a calculator and also now know what all the terms are called. At the start of this video, I mentioned that neural networks could, for example, be used for image recognition. But so far, our network, with its two scalar parameters w and b, doesn't look like it could do anything particularly interesting. So what do we need to add? Well, the short answer is more neurons. So now, we're just going to start building up some more complexity whilst keeping track of how the notation adapts to cope. If we now add an additional neuron to our input layer, we can still call this scalar output variable a1, but we will need to be able to tell the difference between the two inputs. So we can call them a00 and a01. To include this new input in our equation, we simply say that a1 equals sigma of the sum of these two inputs, each multiplied by their own weighting plus the bias. As you can see, each link in our network is associated with a weight, so we can even add these to our diagram. Adding a third node to our input layer, a03, follows the same logic, and we just add this weighting value to our sum. However, things are starting to get a bit messy. So let's now generalize our expression to take n inputs, for which we can just use the summation notation, or, even better, notice that each input has a weight, so we can make a vector of weights and a vector of inputs, and then just take their dot product to achieve the same effect. We can now have as many inputs as we want in our input vector, so let's now apply the same logic to the outputs. Adding a second output neuron, we'd call these two values a10 and a11, where we now have twice the number of connectors, each one with its own weighting, and each neuron has its own bias. So we can write a pair of equations to describe this scenario, with one for each of the outputs, where each equation contains the same values of a0, but each has a different bias and vector of weights. Unsurprisingly, we can again crunch these two equations down to a more compact vector form, where the two outputs are each rows of a column vector, meaning that we now hold our two weight vectors in a weight matrix, and our two biases in a bias vector. Now, let's have a look at what our compact equation contains in all its glory. For what we call a single layer neural network with m outputs and n inputs, we can fully describe the function it represents with this equation. And peering inside, we can see all the weights and biases at work. The last piece of the puzzle is that, as we saw at the very beginning, neural networks often have one or several layers of neurons between the inputs and the outputs. We refer to these as hidden layers, and they behave in exactly the same way as we've seen so far, except that their outputs are now the inputs of the next layer. And with that, we have all the linear algebra in place for us to calculate the outputs of a simple feed-forward neural network. However, persuading your network to do something interesting, such as image recognition, then becomes a matter of teaching it all the right weights and biases, which is what we're going to be looking at in the next video, as we will bring the multivariate chain rule into play. See you then. In the previous video, we introduced the concept of neural networks, and then we worked through the algebra required to describe a fully connected feed-forward network with hidden layers. In this video, we're going to see how the multivariate chain rule will enable us to iteratively update the values of all the weights and biases, such that the network learns to classify input data based on a set of training examples. When we say that we are training a network, we typically mean using some kind of labeled data, which are pairs of matching inputs and outputs. For example, if we were to build a network to recognize pictures of faces and predict if they were happy, then for our training data, each of the inputs might be the intensity of a single pixel from the image, and this would be paired with an output, which just says whether this image contains a face and whether it was a happy face. The classic training method is called backpropagation, because it looks first at the output neurons and then works back through the network. If we start by choosing a simple structure, such as the one shown here, with 4 input units, 3 units in the hidden layer, and 2 units in the output layer, what we're trying to do is find the 18 weights and 5 biases that cause our network to best match the training inputs to their labels. Initially, we will set all of our weights and biases to be a random number, and so initially, when we pass some data into our network, what we get out will be meaningless. However, we can then define a cost function, which is simply the sum of the squares of the differences between the desired output, y, and the output that our untrained network currently gives us. If we were to focus on the relationship between one specific weight and the resulting cost function, it might look something like this, where if it's either too large or too small, the cost is high, but at one specific value, the cost is at a minimum. Now, based on our understanding of calculus, if we were somehow able to work out the gradient of c with respect to the variable w at some initial point w0, then we can simply head in the opposite direction. For example, at the point shown on the graph, the gradient is positive, and therefore increasing w would also increase the cost. So we should make w smaller to improve our network. However, at this point, it's worth noting that our cost function may look something more like this wiggly curve here, which has several local minima and is more complicated to navigate. Furthermore, this plot is just considering one of our weights in isolation, but what we'd really like to do is find the minimum of the multidimensional hypersurface, much like the 2D examples we saw in the previous module. So, also like the previous module, if we want to head downhill, we will need to build the Jacobian, by gathering together the partial derivatives of the cost function with respect to all of the relevant variables. So, now that we know what we're after, we just need to look again at our simple 2-node network, and at this point, we could immediately write down a chain rule expression for the partial derivative of the cost with respect to either our weight or our bias. And I've highlighted the A1 term, which links these two derivatives. However, it's often convenient to make use of an additional term, which we'll call Z1, that will hold our weighted activation plus bias terms. This will allow us to think about differentiating the particular sigmoid function that we happen to choose separately. So, we must therefore include an additional link in our derivative chain. We now have the 2 chain rule expressions we'd require to navigate the 2-dimensional WB space in order to minimize the cost of this simple network for a set of training examples. Clearly, things are going to get a little more complicated when we add more neurons, but fundamentally, we're still just applying the chain rule to link each of our weights and biases back to its effect on the cost, ultimately allowing us to train our network. In the following exercises, we're going to work through how to extend what we saw for the simple case to multi-layer networks. But I hope you've enjoyed already seeing calculus in action. See you next time. This brings us to the end of the third module on this calculus course. Hopefully, you are now starting to see how both calculus and linear algebra are going to be important for developing a detailed understanding of machine learning techniques. You already have a lot of powerful tools in your toolbox, and you are nearly ready to put them into action. Next module, we'll be looking at power series, which will bring us all the way back to the rise over run approximation from module 1 and help us tie up a few loose ends. See you then. Welcome to module 4 of the course. In this module, we're going to learn how to take a complicated function and build an approximation to it using a series of simpler functions. The particular approach that we're going to be looking at is known as the Taylor series, and it will require all of the calculus skills you've learnt so far to be put into practice. Both the Jacobian and the Hessian will be making appearances again when we consider the multivariate case, which will hopefully allow you to see how all of the concepts that you've seen so far are actually linked together. See you then. The Taylor series is one of a family of approaches used for building approximations to functions. So before diving into the maths, it's worth stopping for a minute to talk about when it might be useful to have an approximation. One example that seems to stick in people's minds is to do with cooking a chicken. Imagine that you could write a function which describes the relationship between the mass of a chicken, m, and the amount of time t it should be put in the oven before it would be perfectly cooked. Clearly, there are a lot of assumptions that we'd need to have in place for such a function to even exist. For example, this would only apply to a certain type of oven preheated to a certain temperature applied to a certain configuration of chicken, i.e. one that's in one piece rather than chopped up. Furthermore, the heat transfer properties of a chicken will almost certainly vary in a highly nonlinear fashion as a function of the mass. Let's have a look at the sample function that has some of the features that we've mentioned. You can imagine that on the one hand, the chicken cooking time t will be quite sensitive to a lot of parameters that we might expect to vary case to case. However, on the other hand, if we'd like to sell a nice recipe book, we're going to need to be pragmatic and simplify this monster, as people tend not to want to solve complicated equations while making dinner. So, what do? Firstly, we're going to make two assumptions, one about ovens and the other about chickens. So let's assume that it's reasonable to suggest that everyone who buys your cookbook will have a sufficiently similar oven, such that we can assume that they behave basically the same. Secondly, that everyone will be cooking a sufficiently similar chicken in terms of their heat transfer properties as a function of mass, that you can also assume that these will be the same in each case. This allows us to remove two potentially problematic terms that might themselves have been a function of many other variables, but we were still left with quite a messy function. The next thing we're going to do is have a look at a plot of this function. Now, already I'm telling you about what I view as relevant information in this system, as I'm not showing you timings for chickens heavier than 4 kilograms or chickens of negative mass. And in fact, what I'm going to do now is go one step further and say that considering a typical chicken from a supermarket is about 1.5 kilograms, so let's focus here and build a nice straight line approximation of the form y equals mx plus c. By using the Taylor series approach, which we will be learning in the following videos, it is possible for me to derive a function with the same height and slope as one of the points in my graph. This line is a fairly reasonable approximation to the function in the region close to the point of interest, but as you move further away, the approximation becomes pretty poor. However, this cookbook is not for people either roasting giant or miniature chickens, so we end up being able to write down an expression in a much more palatable format, where our approximation t star is approximately equal to 50 times the mass in kilograms plus 15. So if you'd like to roast a 2 kilogram bird, leave it for about 115 minutes. In the next few videos, we're going to go into a lot more detail about the Taylor series and also find out how to derive higher order terms. I really don't know whether the famous chefs around the world are knowingly using Taylor series approximations when they write their cookbooks, but I like to think that they are. See you next time. In this short video, I'm just going to give you one more teaser about what the Taylor series is doing before we try and write down anything like a formal definition. This will allow you to have a go at some graphical questions first, which is much like how we approached learning differentiation at the start of this course. Taylor series are also referred to as power series, and this is because they are composed of coefficients in front of increasing powers of x. So we can write a simple generalized expression for a power series as g of x equals a plus bx plus cx squared plus dx cubed, etc. Potentially going off for infinitely many terms, depending on what function we're considering. When we calculate a Taylor series in the next video, we will build it up coefficient by coefficient, where each term that we add improves the approximation, and in many cases, we will then be able to see a pattern emerge in the coefficients, which thankfully saves us the trouble of calculating infinitely many terms. However, many of the applications of Taylor series involve making use of just the first few terms of the series in the hope that this will be a good enough approximation for a certain application. Starting from just a single term, we call these expressions the zeroth, first, second, and third order approximations, etc. Collectively, these short sections of the series are called truncated series. So let's begin by looking at some arbitrary but fairly complicated function. If we start with something like this, where we have a function, and we're just making it up, perhaps shaped like this, all we're going to do is focus on one particular point on this curve. So let's say this point here. And then we're going to start building our function by trying to make it more and more like the point that we've chosen. So as the first term of our generalized power series is just a number, a, and we're ignoring all the other terms for now, we know that our opening approximation must just be a number that goes through the same point. So we can just dive straight in and add our zeroth order approximation function to our plot. It's going to be something like that. Clearly, this hasn't done a great job at approximating the red curve. So let's now go to our first order approximation. This thing can also have a gradient, and if we'd like to match our function at this point, it should have the same gradient. So we can have something a bit more like this, which is supposed to be a straight line. Clearly, our approximation has improved a little in the region around our point, although there is still plenty of room for improvement. We can of course move on to the second order function, which as we can see is a parabola, although at this point things get a little tough to draw, and matching second derivatives by eye is also not easy, but it might look something like this. So we can say, okay, let's go up, and we're going to come down like that. Hopefully, without having gone into any of the details about the maths, you'll now be able to match up some mystery functions to their corresponding truncated Taylor series approximations in the following exercise. In the next video, we're going to work through the detailed derivation of the terms, but I hope this activity will help you not to lose sight of what we're trying to achieve in the end. See you then. In this session, we're going to work through the derivation of power series representation of functions, which in short is the idea that you can use a series of increasing powers of x to re-express functions. Just to warm up by blowing your minds, we can take the function e to the x, which we met earlier in the course, and re-express it as the series 1 plus x squared over 2 plus x cubed over 6 plus higher order terms. Now, I hope you would agree with me that this is pretty incredible, and hopefully by the end of this video you will understand how to build series like this for many other interesting functions. What the Taylor series method tells us is that if we know everything about the function at some point, whereby everything, I mean the function's value, its first derivative, second derivative, third derivative, etc., then we can use this information to reconstruct the function everywhere else. So if I know everything about it at one place, I also know everything about it everywhere. However, this is only true for a certain type of function that we call well-behaved, which means functions that are continuous and that you can differentiate as many times as you want. That said, we know lots of functions like that, so it turns out to be a very useful tool indeed. So now we're going to try and explain this concept graphically by looking at a graph of some arbitrary function f of x, which looks like this, and building a sequence of gradually improving approximations. So, our first approximation, which we can call g0, we're going to build using just one piece of information from our function f of x, which will be the value of the function at our point of interest, which in this case is just x equals 0. As you can imagine, if all we're going to build our function off is this one single value, then clearly our guess function isn't going to be able to capture a very complicated shape like this. And in fact, all it can be is a horizontal line at the point f at 0. So we can plot this first approximation and also write an expression for calculating g0 of x, which is just f of 0. We call this our 0th order approximation, and clearly it's not very good. But also notice that as this line is flat, it's actually not even a function of x. We can do better. So let's now find our first order approximation. For this, we're now going to use two pieces of information, the value of the function at x equals 0, but also the value of the gradient at x equals 0, which we will call f dash at 0. Using these, we can build another straight line of the form y equals mx plus c, where the vertical axis intercept c is just f of 0, but just substituting in for f dash of 0 as the gradient of our line. So we can now plot our first order approximation to the function, which has the same value of the gradient and of the function f of x. And we can also write down its expression g1 of x is f of 0, f dash of 0 times x. This thing clearly does a better job than g0 at approximating f of x near the point x equals 0, but it's still not great. Moving quickly on to our second order approximation, g2 of x, we're going to use three pieces of information, f of 0, f dash of 0, and the second derivative, f double dash of 0. Now, to have a function that can make use of these three pieces of information, we're going to need a quadratic equation. So we can write y equals ax squared plus bx plus c. Differentiating this thing twice, we can just say, well, y prime equals 2ax plus b, and y double prime equals 2a. Now what we want is for this function to be the same as f of x when we sub it in at the point equals 0, x equals 0. So we can say, okay, at x equals 0, we want this thing to equal f double prime of 0. So clearly, our coefficient a, because this thing's not even a function of x, therefore a is just going to equal f double dash 0 divided by 2. Now if we look up at this equation here, we also want the first derivative to be equal to the function at 0. So we can set this equal to f dash of 0, and we're subbing in 0 for this x here, so this term just disappears. So we can now say that also b equals f dash at 0. Lastly, subbing in 0 here, and setting this thing just equal to f of 0, we can say that clearly c is also just equal to f of 0. c equals f at 0. So we now have all three coefficients for our equation. And we can say, let's now go back to our graph and add our second order approximation, which, as it's just an x squared term, will be a parabola. Notice that each time we update our approximation, the region in which it matches up with f of x grows a little. So let's now take one more step down the rabbit hole and find the third order approximation. So we can write y equals ax cubed plus bx squared plus cx plus d. As based on what we've already seen from the first three steps, it's only the coefficient a that we need to find, as b, c, and d will be the same as we found for g2. So let's now differentiate this thing three times. Y prime equals 3ax squared plus 2bx plus c. y double prime equals 6ax plus 2b, and y3 is just going to be 6a. So clearly, we want this thing, the third derivative of our approximation function, to equal our function f of x when we've differentiated it 3 times and evaluated it at the point x equals 0. So we're setting this x to 0. Now there is no x in this bit. We can say f3 at 0 equals 6a. Therefore, a just equals f3 at 0 divided by 6. Finally, we can add this third order approximation to our graph and write out its expression. You can now see that not only has the approximation improved significantly, but also that we can add higher order terms piecewise, and in each case the lower order terms remain the same. What we now want to build is a general expression. The lower order terms remain to just write down the fourth order approximation without working through it. Notice that the 1/6 coefficient in front of the cubic term was the result of having to differentiate a cubic term twice. So when we differentiate x to the 4th power 3 times, we are going to get 4 times 3 times 2 in front, leading to a coefficient of 1 divided by 4 times 3 times 2, which is 1 divided by 24. We have a name for the operation 4 times 3 times 2, which is 4 factorial. And in fact, all the terms can be thought of as having a factorial in front of them, even 0 factorial, which, for reasons I won't go into here, is in fact equal to 1. So with this last piece of the puzzle in place, we can now say that the nth term in the approximation is just the nth derivative of f, evaluated at 0, divided by n factorial multiplied by x to the power of n. And therefore, the complete power series can be written as follows. So you can see it's the sum from n equals 0 to infinity of these terms. Although what we've written here certainly does count as a Taylor series, because we're specifically looking at the point x equals 0, we often refer to this case as a Maclaurin series. So you're still going to have to wait one more video before seeing the Taylor series expression in all its glory. In the rest of this module, we're going to be applying the concept of power series to some interesting cases, as well as generalizing it to higher dimensions, where rather than building approximation curves, we will be constructing approximation hypersurfaces. See you then. I began our last session by trying to motivate you with the fact that we can re-express the function e to the x as a power series. So I want to make sure that your mind is well and truly blown by showing you that when we differentiate this function term by term, which isn't very difficult to do as it's just a polynomial, something rather satisfying happens, where, just as we'd expect for the derivative of e to the x, this infinitely long series remains unchanged, which I think is pretty awesome. So now, finally, you're going to get to see the Taylor series. Fundamentally, we are applying the same logic as the Maclaurin series that we derived previously. But whereas the Maclaurin series says that if you know everything about a function at the point x equals 0, then you can reconstruct everything about it everywhere, the Taylor series simply acknowledges that there is nothing special about the point x equals 0, and so says that if you know everything about the function at any point, then you can reconstruct the function anywhere. So, a small change, but an important one. Let's look again at the function e to the x, as well as the first 4 approximation functions. Now, using our understanding of the Maclaurin series, we can also rewrite this in a compact summation notation, such that we could, if we wanted, build a polynomial approximation function to an arbitrary degree of accuracy. So, what if now, instead of expanding around the point x equals 0, we wanted to start from the point x equals p? Well, to begin with, let's have a look at the first 4 approximation functions at this point. The expressions to describe these approximations are still going to require the value of the function, as well as all of its derivatives at this point. But how do we now adjust our general equation to allow for an arbitrary expansion point, x equals p? Well, clearly, the 0th order term, this is just straightforward. It's going to be a horizontal line that just uses the point f of p everywhere. But what if we take a closer look at the first order approximation? This should give us enough insight that we'll then be able to tackle all the other higher order terms. So we're essentially looking to build a tangent to the curve at point P. All straight lines are of the form y equals mx plus c. So let's now work through this by putting in place all the information that's available to us. So we can say, okay, here is some nice function that we're going to deal with. And if we're looking at the point P here, this is of course at f of P height. So its coordinates of this point are P, f of P. And we want to build an approximation function that is first order. So it's got a y-axis intercept and it's got a gradient. And it's going to look something like this. Okay, the same gradient and the same height of the function at that point. So of course that green line is going to have the equation y equals mx plus c. Now we know immediately that m is the gradient of this straight line. And we know the gradient of our function here is just f dash at p. So we can say y equals f dash at p x plus c. So all that's left is for us to find c. And to do that, we're going to need to know x and y. But we do know a point on our line. It's the point P, f of P. So we just sub these in. F of P equals f dash of P at P plus C. Rearranging for C, we can just see that C is going to equal f of P minus f dash of P at P. Subbing the C back into our general equation, we can now bring it round and say, well, this line has the equation y equals m, which is just f dash of P, times x plus c, which is just f of P minus f dash of P multiplied by P. Okay? Now the last thing I'm going to do is take this and factorize this f dash of P out. And that'll leave you with a nice form of this expression. Y equals f dash of P multiplied by, there's an x of it here, and there's a minus 1 of it here, and minus p of it here. So we can say x minus p plus, just this term here, f of P. What this shows us is that by building our approximation around the point P, when we use our gradient term f dash of P, rather than applying it directly to x, we instead now apply it to x minus P, which you can think of as how far are you away from P. So we can now write down our first two approximation functions to f of x at the point P, the 0th and the 1st. Thinking back to the Maclaurin series from the previous video, all we need to do to convert to Taylor series is use the second derivative at P rather than 0, and also replace x with x minus P. But notice that the factor of 1/2 still remains. So we can now look at our concise summation notation for the Maclaurin series and upgrade the whole thing to the more general Taylor series form, noticing of course that if we decide to set P to 0, then the expressions would actually become identical. So we now have our one-dimensional Taylor series expression in all its glory, which will allow us to conveniently re-express functions into a polynomial series. In the remainder of this module, we're going to play around with this result, as well as extending it to higher dimensions. See you then. In this video, we're going to put our understanding of power series to the test by looking at two interesting examples. First off, we're going to build a Maclaurin series expansion of the cosine function. Cosine is the epitome of a well-behaved function, as it is certainly continuous everywhere, as well as being infinitely differentiable. As we're building a Maclaurin series, we're going to want to find out everything about the function at the point x equals 0. So let's start by doing some differentiation. And what we get, if you remember from earlier in the course, is this cyclic pattern of cosines and sines, positive and negative, which takes us back to the cosine again after 4 steps. If we now evaluate this derivative at the point x equals 0, we see that the cosine terms are either 1 or minus 1, and the sine terms are all 0. This must mean, from a power series perspective, that every other term will have a 0 coefficient. Notice that these zeros will occur whenever we differentiate an odd number of times, which means that all the odd powers of x, like x to the 1, x cubed, x to the 5, etc., will all be absent from the series. The even powers of x are all what we call even functions, which means that they are all symmetrical around the vertical axis, just like cosine is. So, we can now bring back our general expression for the Maclaurin series and just start writing out the terms. The icing on the cake is that at this point, we just notice that we can build a neat summation notation which fully describes this series without having to write out all the terms. Notice that this expression doesn't even contain any reference to cosine, as all that we need to know is captured by the minus 1 to the power of n, which just keeps flipping from negative to positive and negative again. Now that we've done all the hard work, we can simply ask our computer to plot this sequence of increasingly accurate Maclaurin series, which hopefully, starting from a horizontal line at y equals 1, will line up with your expectations. Notice that outside of a region of fairly close to the point x equals 0, the approximation explodes off and becomes useless. By the time we get our 16th order approximation, we've pretty much nailed the region shown in our graph here, although just outside of these axes, the function would also be growing hugely positive. So you must always be careful when handling series approximations that you know the domain in which it's acceptable. In the second example, we're going to take a look at the function f of x equals 1 over x, which of course looks like this. It's a nice, simple function, but notice the discontinuity at x equals 0. This is absolutely not a well-behaved function. In fact, it's so badly behaved that when we even try and build the 0th order approximation, we immediately run into problems, because we have to perform the operation 1 divided by 0, which is not defined. And if you tried to ask your computer to do this, it may give you back the answer nan, which stands for not a number. So, we're going to need to try a different angle of attack. Clearly, we aren't going to have much luck at the point x equals 0, so why not try going somewhere else, anywhere else? Let's look at the point x equals 1. Certainly, it passes the first test of being able to evaluate the function at this point. However, moving away from x equals 0 means that we're now going to need to use the Taylor series instead of the Maclaurin series. So we now need to find a few derivatives of the function and see if we can spot a pattern. When we evaluate these functions at the point x equals 1, hopefully you'll recognize that we get a sequence of factorials emerging, just as we did when deriving the power series formula in the first place. So if we now substitute these values into our Taylor series formula, the factorial terms will cancel, and all we are left with is a sum of x minus 1 to the power of n terms with alternating signs, which we can simplify to this neat summation notation. So once again, let's now pass this formula to the computer and ask it to plot a sequence of improving approximations, starting as ever with a horizontal line, but this time starting at the height of the function at x equals 1. There are several really interesting features of this particular example which tell you interesting things about the power series more generally. Firstly, the approximations ignore the asymptote, going straight across it. And furthermore, the region of the function where x is less than 0 is not described at all by the approximations. Secondly, although the function is gradually improving for larger values of x, you can see the tail wildly flailing around as the sign of each additional term flips from positive to negative and back again. I hope these two examples have made it clear both how the Taylor series manages to reconstruct well-behaved functions like cosine x, but also why they can struggle to deal with something badly behaved like 1 over x. As we bring this video to a close, let's now watch an action replay of these two sequences of improving approximations. In the next video, we're going to talk briefly about what it means to linearize a function and see how this relates to the Taylor series analysis that we've seen so far. See you then. In this session, we're just going to take what we've learned about Taylor series so far and reframe it to a form that will help us understand the expected error in an approximation. So, as we've already seen, we can build up a sequence of gradually improving approximations to functions by adding higher powered terms. All I'm going to do now is change the notation of some of the terms. So if we take our first order approximation as an example, what this expression is saying to us is starting from the height f of p, as you move away from p, your corresponding change in height is equal to your distance away from p times the gradient of your function at p. So in a sense, rather than using gradient equals rise over run, we are just rearranging to rise equals gradient times run. You are ultimately going to use your approximation to evaluate the function near p, as you must already know about it at p. So I'm now going to say that our distance from p, which we currently call x minus p, we will now call delta p, to signify that it represents a small step size away from p. And we can also recast x now in terms of p, saying that x is just p plus delta p. Finally, it actually is now time to say goodbye to p, as in our first order approximation, everything is actually in terms of p. So all I'm going to do is swap all the p's for x's, as this is the form that people would usually expect to see it in. I'm going to do it all at once to make it as painless as possible. I haven't changed anything conceptually, I've just written an x everywhere where we used to have a p. And we can now, of course, also rewrite our Taylor series expression in this new form, with just x and delta x. So we're in good shape to talk about approximations. What I now want to know is, when I use the first order approximation, instead of evaluating the base function, how big should I expect the error to be? You can see, for example, that the gap between the white and green lines grows as we move along the x-axis away from the point x. Well, one way to think about it is that we know our function can be exactly represented by this infinitely long series. So although we won't be able to evaluate all of the terms, we do know that the next term along, i.e. the first term that we ignore when we're using our first order approximation, has a delta x squared in it. This means that if we can say that delta x is a small number, then delta x squared must be a really small number, and similarly delta x cubed must be a ridiculously small number. So we can now rewrite our first order approximation to include an error term, which we just say is on the order of delta x squared, or equally, that it is second order accurate. This process of taking a function and ignoring the terms above delta x is referred to as linearization, and I hope it's now clear to you why that's the case. We've taken some potentially very nasty function and just approximated it with a straight line. The last idea that I'm going to share with you in this video is perhaps the most interesting, as it brings us right back to our rise over run approximation that we met at the beginning of the course. The green line is our first order Taylor series approximation to the function at the point x, which is of course also the tangent to the curve at x. But let's now add another line, which is the approximation to the gradient at x using our rise over run method with a second point delta x away. We use this forward difference method to help us build the definition of a derivative at the beginning of the course. And we noticed that as delta x goes to 0, the approximation becomes exact. However, what happens if delta x does not go to 0 and the second point remains some finite distance away from x? Well, your calculated gradient will now contain an error, and once again, we can rearrange the full Taylor series to work out how big we'd expect that error to be. With a bit of slightly fiddly algebra, we can rearrange this expression such that the gradient term f dash of x is isolated on the left-hand side. Because the series is infinite, this is still an exact expression for the gradient at x, but what we get on the right-hand side is something that looks suspiciously like the rise over run expression plus a collection of higher order terms. If we notice that the first of the higher order terms has a delta x in it, we know that we can now lump them all together and say that using the rise over run method between 2 points with a finite separation will give us an approximation to the gradient that contains an error proportional to delta x. Or, more simply put, the forward difference method is first order accurate. That's all for this video. It might seem a little odd to go to all that trouble just to get an idea of the error in an approximation, but it turns out to be a hugely important concept when, as is typical, we ask computers to solve numerically rather than analytically. See you next time. So far in this module, I've introduced you to the concept of power series and then shown you how we can use them to approximate functions. We've also seen how power series can then be used to give you some indication of the size of the error that results from using these approximations, which is very useful when applying numerical methods. The last idea that we're going to very briefly look at on this topic is upgrading the power series from the one-dimensional version that we've seen so far to its more general multivariate form. Just to recap on the notational options from the previous video, we saw that we can re-express the Taylor series from a form that emphasizes building the approximation of a function at a point P to a totally equivalent form that emphasizes using that function to evaluate other points that are at a small distance delta x away. Just to make sure you can see that they're the same, we can write out the first four terms one above the other to make the comparison clear. In this video, we are going to continue using the delta x notation as it's more compact, which will come in handy when we're in higher dimensions. We won't be working through the multivariate Taylor series derivation in any detail, as all I really want you to take away from this video is what a multidimensional power series will look like, both as an equation and in a graph. So keeping in mind our one-dimensional expression, let's start by looking at the two-dimensional case, where f is now a function of the two variables x and y. So our truncated Taylor series expressions will enable us to approximate the function at some nearby point x plus delta x, y plus delta y. Let's look at the simple two-dimensional Gaussian function, which many of you may be familiar with from studying the normal distribution in statistics. It's a nice, well-behaved function with a simple maximum at the point 0, 0. Now, in a one-dimensional analysis, our power series would give us an expression for a one-dimensional function. However, in a two-dimensional case, our power series would of course now give us a two-dimensional function, which we would more intuitively refer to as a surface. Just as with the one-dimensional case, our zeroth order approximation are simply the value of the function at that point applied everywhere, which means in 2D, this would just be a flat surface. So a zeroth order approximation at the peak would look like this. And a zeroth order approximation somewhere on the side of the bell would look a bit more like this. This is fairly straightforward, but now let's think about the first order approximation. Drawing the analogy from the 1D case again, the first order approximation should have a height and a gradient. So we're still expecting a straight surface, but this time it can be at an angle. Now, if we are calculating it at the peak, it wouldn't be a very exciting case, as it's a turning point, and so the gradient is 0. However, let's look again at the point on the side of the slope. Taking the first order approximation here gives us a surface with the same height and gradient at the point. Finally, let's look at the second order approximation for these 2 points. We're now expecting some kind of parabolic surface. However, if I calculate it at the peak, nothing seems to appear. But that's just because we've created a parabola inside our bell curve. So we need to look from underneath to even see it. Finally, if we plot the second order approximation at the point on the side of the bell curve, you can see that we end up with some kind of interesting saddle function. But it's still fairly clear, even by eye, that the gradient and the curvature are matching up nicely at that point. Although this approximation is evidently not useful outside of a fairly small region around the point. We're now going to take a look at how we would write expressions for these functions. So, if we wanted to build a Taylor series expansion of the two-dimensional function f at the point x, y, and then use it to evaluate the function at the point x plus delta x, y, delta y, our zeroth order approximation is just a flat surface with the same height as the function at our expansion point. The first order approximation incorporates the gradient information in the two directions. And once again, we are thinking about how rise equals the gradient times the run. Notice here, for compactness, I'm using the partial symbol with a subscript to signify a derivative with respect to a certain variable. If we look now at the second order approximation, we can see that the coefficient of 1/2 still remains as per the one-dimensional case, but now we have 3 terms, all of which are second derivatives. The first has been differentiated with respect to x twice, the last with respect to y twice, and the middle term has been differentiated with respect to each of x and y. Now, There are, of course, higher order terms, but we've already got more than enough to play with here. So, let's look again at the first order term. It's the sum of the product of the first derivatives with the step sizes. But hopefully, this will remind you of our discussion of the Jacobian. So we can actually re-express this as just the Jacobian multiplied by a vector containing delta x and delta y, which we can write as delta bold x, where the bold x signifies a vector containing those two terms. Finally, if we look at the second order term in the same way and notice that these second derivatives can be collected into a matrix, which we've previously defined as our Hessian, then to make the sum we need, we now have to multiply our delta x vector by the Hessian, and then again by the transpose of the delta x vector. And that's it. So, we now have a nice, compact expression for the second order multivariate Taylor series expansion, which brings together so much of our calculus and linear algebra skills and makes use of the Jacobian and Hessian concepts which we defined earlier in the course. And of course, although we've been talking about the two-dimensional case in this video so far, we could actually have any number of dimensions contained in our j, h, and delta x terms. So this immediately generalizes from 2D to multi-dimensional hypersurfaces, which is pretty cool. See you in the next one. This brings us to the end of the fourth module of this calculus course. You now have all the tools in place to do something really useful. And in the next two lectures, David is going to walk you through a method for fitting functions to data, which will make use of a lot of the calculus, including all the 4 time-saving rules in their multivariate form, as well as putting the Jacobian into action. Good luck, and I'll talk to you again at the end of the course.
Hi there, I'm David Dye, and I'll be taking you through the last few modules of this course. In this module, we'll start to use the calculus we've done and put it together with vectors in order to start solving equations. In this first video, we'll look at a nice simple case where we just need to find the gradient, the derivative, in order to solve an equation using what's called the Newton-Raphson method. Now, say we've got that distribution of heights again with a mean, an average, mu, and a width, sigma, and we want to fit an equation to that distribution that so we don't have to, after we've fitted it, bother about carrying around all the data points. We just have a model with 2 parameters, a mean and a width, and we can do everything using just the model. And that would be loads faster and simpler and would let us make predictions and so on. So it would be much, much nicer. But how do we find the right parameters for the model? How do we find the best mu and sigma we can? Well, what we're going to do is we're going to find some expression for how well the model fits the data, and then look at how that goodness of fit varies as the fitting parameters mu and sigma vary. So we're trying to solve an equation where the fitting parameters are the variables in the equation. But in order to get there, in the next module actually, we're first going to need to do a bit more calculus. So first, let's look at the equation of a line. Say here, y equals x cubed minus 2x plus 2. If we differentiate this equation, we get the quadratic 3x squared minus 2. And that quadratic will have 2 solutions, and therefore 2 turning points will exist, one a maximum, one a minimum, just as we see here. Now, say that I don't know what the equation looks like, I'm blind, and I haven't got enough computer resources to graph out the values at every point. Or more likely, in reality, say the function exists in so many dimensions that I can't visualize it at all. But say I only need to find the solution to the equation where y equals 0, so where x cubed minus 2x plus 2 is equal to 0. We can see that there's actually only one solution here on this graph, but there could be more depending on the exact form of the equation I was trying to solve. Now, say that I have an idea that I want to hunt for a solution somewhere near some initial guess, the red dot here. For instance, the constant's pretty small and positive, so I might guess that I need a slightly negative value of x, say minus 2 might be somewhere near a solution. Now, if I can evaluate the value of the function at my guess of x equals minus 2, I find that the function has a value of minus 2. And if I ask what the gradient is at that value of x equals minus 2, I find that the gradient is positive and it's 10. Now I can extrapolate the gradient to the intercept with the y-axis, which is would be my first guess of the solution of the equation. So I'm trying to solve where it finds that intercept with the y-axis. So I can use that value of x at the intercept as a new estimate for what the solution to the equation is. Effectively, I'm guessing that the function is a straight line, and then I'm using the gradient to extrapolate to find the solution. It isn't really a straight line, of course, but the first order approximation would be that it's a straight line, and we'll use that to update our guess and then go again and evaluate. So I can write down an equation for my new guess, xi plus 1, based on my previous guess at attempt xi, as being my original guess minus the value of the function divided by its gradient. So let's see how it plays out. We can make a table starting with our initial guess at I equals 0, and then we can find the gradient and the intercept. And then use that to generate a new guess. In this case, minus 2 minus minus 2 divided by 10 gives us minus 2 plus 0.2, which is minus 1.8. Then we can evaluate the result for that guess and find that it's just a little less than 0, minus 0.23, and the gradient is 7.7. So we've gone from being out by 2 on y to being out by just 0.23. So in some sense, we've got like 10 times better in our estimate, just in our first go. If we carry on, then we get the next guess for x2 is minus 1.77, and that's just 0.005 away from the axis. It's really close. Then if we have another go, after just 3 iterations, we get an answer of x equals minus 1.769, which is just 2.3 times 10 to the minus 6 from the axis. So in just 3 iterations, we've pretty much solved the problem, which is pretty cool. This method is called the Newton-Raphson method, and it's really pretty neat. To solve an equation, all we need to be able to do is evaluate it and differentiate it. We don't need to graph and visualize it everywhere, calculating it lots and lots of times. We don't need to be able to solve it algebraically either. Which if we have lots of dimensions to a data set, say, and a big multi-variable function we're trying to fit to that data, it's going to be much too expensive to try and solve it analytically, or even plot it out for all the possible values of the variables. This sort of method where we try a solution and evaluate it, and then generate a new guess, and then evaluate that, and again and again and again, is called iteration. And it's a very fundamental computational approach. Now, there are some things that can go wrong sometimes with this method, so let's briefly look at those. Say I started off with a guess of x equals 0, which evaluates to y equals 2. When I find the gradient for that and extrapolate it, that takes me away from the solution to the other side of the turning point. It gives me a new guess that x equals 1. When I evaluate that, then I get a value for y at x equals 1 of 1. When I find the gradient and extrapolate back, then my new estimate lands me back at x equals 0, which is where I begun. So I have a problem. I seem to have magically landed in a closed loop where my estimates just cycle back between x equals 0 and x equals 1. And I never get close. I never even go anywhere near to the solution at x equals minus 1.769. There's another problem, which is that if I'm close to a turning point, this bottom here, to a minima or a maxima, then because my gradient will be very small, when I divide by the gradient in the Newton-Raphson equation here, my next estimate will take me zapping off to some crazy value. And therefore it won't converge easily, it'll dive off somewhere. Those are the problems. So that's the Newton-Raphson method. We iterate to a solution to an equation by each time making a new estimate for the solution, using the gradient to extrapolate towards the solution, then going again and again and again. And most of the time, this works really well as a means to step towards the solution. So, what we've done in this video is look at a method for using just the gradient to step our way towards solving a problem. This method is called the Newton-Raphson method, and it's a really powerful way to solve an equation just by evaluating it and its gradient a few times. It's as if you're standing on a hill in the fog, and you can know your height and you can know locally what's going on around you. You can know how steep the hill is, but you can't see the whole landscape around you. You don't know what it looks like. You don't know how to get down the mountain, if you like, down to a nice safe place that doesn't have cliffs. So what you do is you guess based on how steep the hill is locally around you which way to go. That you want to go down to sea level, so you go down the hill. Then you take that step blindfolded, and when you get there, you ask again what height you're at and how steep it is, and then you keep making more steps down the hill until either something goes wrong and you need to go back down the other way, or you get home to where you want it to be. The point is you don't need to know what the landscape looks like, the function. You just need an altimeter, the value of the function, and to be able to feel with your toe what the gradient is like locally around you. What we'll do in the next video is look at how to apply this where we've got multiple variables, not just x. And that will involve finding the gradient vector, how to go down a hill on a contour plot. Okay, so now we've looked at the Newton-Raphson method, which uses the gradient to iteratively solve a 1D function of x, say. Now we'll generalize that to figure out how to do something similar with a multidimensional function, a function of multiple variables, and how to use the gradient to find the maxima and minima of such a function. Later on, this will let us optimize, find the best fit for the parameters of a function that we're trying to fit. Say I've got a function like f equals x squared y here. This function looks like this. And what I've got here is a function that gets big and positive when x is big and y is positive, and it gets negative when y is negative. So if I look down the y-axis, I get a projection of a straight line. And if I spin to look down the x-axis, I get an upright parabola for y positive, and one going down for y negative. And the function is equal to 0 along both the axes. Now at the bottom here in MATLAB, I've used the surf-c function to plot contours when the function has a constant value, just like the contours of constant height on a topographical map. So the question we want to answer in this video is, how do I find the fastest or steepest way to get down this graph? Now, previously you found out what the gradient of a function is with respect to each of its axes. So you can find df dx just by differentiating the function f, treating all the other variables as constants. So in this case, we've got a function f of x, y is equal to x squared y. And so df dx is equal to differentiate that, treating y as a constant. So that's just 2x times y. And df dy is equal to, well, the x squared we treat as a constant, and y differentiates just to 1. So it's just x squared. Now, we can write down these two gradients in a vector, which we call the grad of f. So this guy we call grad. And this vector is just the vector where we write them down as the components of a vector. So we say that grad is that. It's just the vector found by writing down df by dx and df by dy in the x and y locations of the vector. And grad is like the most awesome vector ever. Grad is the little vector that combines linear algebra and calculus together. So grad's a lot of fun. So if we run along a little vector r is equal to dx 0, then if we dotted that with grad f, then we get df dx times dx plus 0. So we'd move the amount dx along the x-axis. So this is doing the right sort of thing, right? A dot product of grad f with a vector is going to take, it looks like, some amounts of df dx along the x bit of that vector and some amounts of df dy along the y bits of that vector. So it's going to tell us how much we've gone down. That's sort of how grad works. And the important thing is to remember this is evaluated at f has some values in the space, a, b. So it's evaluated at a location. So then if we want to know how much the function will change when we move along some unit vector in an arbitrary direction, so we'll call that unit vector r hat, and we'll give it components c and d. So c squared plus d squared is equal to 1. So df is going to be df dx times c plus df dy times d. So what we're doing here is we're doing grad of f dotted with r hat. And we call this thing the directional gradient. So another question we can ask is, what's the maximum value this directional gradient can take? So we've got grad f as a vector, and we're dotting it with r hat. And our question is, what's the maximum value they can take, given that r hat is a unit vector? Well, the only thing then left when we dot them together is going to be the cos theta term, because it's a, b, cos theta. And that's going to be maximised when cos theta is 1, which means theta is 0, which means r hat is parallel to grad f. So in order to find the maximum value of the directional gradient, we want an r hat that's actually the normalised version of grad. So we can write that down, we can do that calculation. So we'll have grad f dotted with the normalised version of itself, so grad f divided by its modulus. But grad f dotted with itself is just equal to the size of grad f squared. Got to divide by the size. So the maximum value the directional gradient can take is just the size of grad f, and that's therefore the steepest gradient we can possibly have. The size of the steepest gradient we can possibly have is just the size of grad f, the sum of the squares of the components of grad. So that's really fun. The other question to ask is, which way does grad point? This is less easy to see, but grad points up the direction of steepest descent, perpendicular to the contour lines. So think, if you're on a mountain and it's foggy and you can only see locally around you and you want to go down the hill, you don't walk around the contour, you go down the hill. So if the contour's like this and I'm staring down the hill is at 90 degrees to the contour line. And think about the way it's defined, is it up or down? df dx is positive if you're going up. So actually grad f points up the hill in the steepest way, and minus grad points down the hill the steepest way. So grad points up the direction of steepest descent. Now, if we have some data science problem where we want to minimise the difference between our data values and our model fit, then what we want to do is find the lowest point in the function. The function is kind of the badness, we want to find the best, so we want to find the point where the badness is minimised. And like Newton-Raphson, we can use the gradient to go from some trial point down towards the solution. But in Newton-Raphson, we're trying to find the 0 point. Here we don't know what the minimum value of the function is, so we don't know how far down we need to go. It's as if we're somewhere on our mountain, but we don't know the altitude of the valley. So what we do in what's called the gradient descent method is we take a series of little steps down the hill. That is, if we started at some position Sn, then our next position, Sn plus 1, is given by Sn plus some little step down the hill, and that little step is given by minus some amount times grad. And grad evaluated at the previous position Sn. On the graph, that's going to look like taking a little step, the little blue one, down the hill, and then we reevaluate, make another Sn plus 1, and make another step, and take a series of steps down the hill. If we overshoot, that's okay, because grad will just take us back to the minimum. And notice that as the gradient gets shallower, as we come towards the turning point, then the steps automatically get smaller, because grad gets smaller. So this is quite a nice method. There are lots of ways to enhance it, but that's the main idea. It's very powerful and simple. The other thing to notice is that there are multiple local minima in the landscape, then we might get stuck in one of them. And of course, which one we find depends on our starting point. We won't find the others, we'll only find one at a time. So in the general case, there are some problems, but nevertheless, this is quite a neat method. This just following little steps down the hill. And this is probably the main way in which most numerical optimizers work that people use in the real world. So, what we've done in this video is we've introduced ourselves to grad, the gradient vector, and merged calculus and vectors together to take our first steps in vector calculus. And that's allowed us to find a method for just using the gradient to step our way towards solving a problem for multivariable cases. And that method's called gradient descent. So we found out about grad, and that led us on to sketch out a neat method for finding the minima and maxima of multivariable functions, which we call gradient descent. In this video, we'll look at what happens if we want to find the minima or maxima subject to some constraint, that we want to find the maximum somewhere along a line or something like that. And this is called the method using Lagrange multipliers. So what we did in the last video is we looked at a function like this one, f here. This function f is x times the exponential of minus x squared plus y squared, and it's one of the standard MATLAB examples. and I've plotted below it here a contour map of the values. If I now plot just the contour map, I can plot out the vectors of grad f. As we said, these vectors are perpendicular to the contour lines and they point up the steepest gradient. Now let's return to the function we were looking at last time, f equals x squared y, which is the Khan Academy standard example for this problem. Last time we plotted grad f on both the 3D version and then dropped that down onto the corresponding contour map. Actually, it's going to be easier if we now just work with the contour map itself. So here's the contour map, and what I've done is I've used the gradient function in MATLAB to just plot out the gradient perpendicular to the contours everywhere in the space. So the low sides are at negative y down here and the high sides are at positive y up here. Now what happens if I want the maximum value for this function, f equals x squared y, but constrain it to lie on a circle? Where's the highest point anywhere on that circle? Say I have a circle of radius a squared and I want to find the minimum maxima on that path as I go around that circle. Now you can imagine that describing an equation for how x squared y varies as I go around a circular path is going to be a complete nightmare. But that's not the question we were actually asked. What we wanted to know was, what's the maximum along that circle, not what's the value everywhere on the circle. Now Lagrange was one of those French mathematicians whose name is inscribed around the Eiffel Tower. And what Lagrange noticed was that when the contours just touch the path, then you'll have found the maximal minimum point. That is, when f is a little bit smaller, it won't quite touch the path, see it here in 3D, and when it's a bit bigger, it might cross a couple of times, see here in 2D on the contours. But when the contour just touches, then we'll have found the minima and maxima of the function f as we go around the path, our circle in this case. And what Lagrange noticed was that when the contour touches the path, then the vector perpendicular to the contour is in the same direction, up to a minus sign, as the vector of the path itself that's perpendicular to the path. So if we can find grad, we can find the minimum maximum points and solve the problem. If we can find grad perpendicular to the contour on both the path and the function, we're away. So we want to maximize the function f of x, y, which is equal to x squared y, subject to some constraint, which we're going to call the constraint equation g of x, y. And that's the equation of a circle x squared plus y squared. And it has some value, some particular value to the problem we want to solve of a squared. So what we're saying is, if we've got the function doing something like this, and it has its grad that way, and the circle has some path that's doing that, and it's got its grad that way, what we're doing is we're solving grad f is equal to lambda, some number, times grad g, where lambda is Lagrange's multiplier, or the Lagrange multiplier. And that's all we really need to do. So we just need to set up this set of equations and then solve them. So if I take grad f is equal to the grad of x squared y, well, that's equal to, if I differentiate for the df dx, I've got 2xy. And if I take df dy, the y just goes and I've got x squared. And I'm saying that that's equal to lambda times grad g, which is equal to lambda times, if I differentiate g, x squared plus y squared with respect to x, I've got 2x. And if I differentiate it with respect to y, I've got 2y. And that's giving me two equations with two unknowns. And I've got a third equation, which is the constraint equation itself that brings in the actual value of the circle I'm particularly interested in. So I've just got to solve that. So if I take the first line, I've got 2xy is equal to lambda times 2x. I cancel the two x's, and therefore I've got y is equal to lambda, straight out. If I take the second row, the y row if you like, I've got x squared is equal to lambda times 2y. But lambda is itself y, so that's equal to 2y squared. So I can say that x is equal to the square root of 2 times y. And because I've done the square root, I've got a plus minus here. And now if I take the constraint equation itself, the third one, I've got x squared plus y squared is equal to a squared, but x squared is equal to 2y squared, so that's equal to 3y squared. So then if I square root that, I can say that y is equal to a divided by the square root of 3, and again, because I've done the square root, I've got a plus minus. So those are my solutions. So I can write those out, and I've got the solutions are going to be a over the square root of 3 times, if I take y as 1, then x is root 2 times that, so root 2, 1. And I've got a over root 3 times root 2 minus 1 for y. And I've got all the possibilities, a over root 3 minus root 2 and 1. And I've got a over the square root of 3 minus root 2 and minus 1. Now, if I find the values of the function, f of x, y, as I go take all of those, so I've got to find x squared y for that. So that's a cubed over 3 root 3, because I'm cubing that bit in effect, because they're both in x and y. And I've got x squared is 2 plus y is times y is 1, so that's 2. Here I've got the same thing, but I've got what y is negative. So now I've got a cubed over 3 root 3 times minus 2. This one's y is plus, and when this squares, the minus sign is going to disappear. So this is going to give me another plus solution, 2 over 3 root 3 a cubed. And I've got here y is negative, so I'm going to get a minus here. A cubed over 3 root 3. So I've got a max, I've got a min, I've got a max, the way I've written it out, and another min. So I've got two positive solutions, and I wanted to find the maximums, so those are there, and I've got the minima as well for free. So let's look at what that looks like now on the graph. So two of our solutions are here and two here. When we switch to the 3D view, we can see that the two with positive y are maxima and the two with negative y are the minima. So that's really neat. What we've done here is we've used our understanding of gradients to find the minima or maxima subject to some constraint equation, like a straight line or a circle. And very often we will want to make it that some of the variables in a function that we want to fit are fixed in relation to each other. They have some fixed relationship, like they're around a circle. So this is a very handy thing to be able to do. It's really useful. So hopefully that was good fun. This week, you've taken all the multivariable calculus you've done so far and looked at how to put that together with vectors and linear algebra to do vector calculus. We've been looking at optimization problems together, how to solve equations and optimize functions, for example, to optimize the fit of a function to some data. We started off with the Newton-Raphson method, where we used the gradient to estimate how far we should step to get from a current guess to a solution to our next guess. And then we kept doing that until our estimate for the solution converged to an answer we were happy with. We then moved on to look at how to find the gradient in the multivariable case. We defined the gradient vector grad, which is perpendicular to the contour lines and has elements equal to the differential of the function along each of the axes, df, dx, df, dy, and so on. And it has magnitude given by the size of grad, the sum of the squares of the elements. We then figured out that we could use grad to go down a hill to find the minimum values of a function by taking little steps down the hill at a time. And that's really neat, because it means we don't need to evaluate the function everywhere and then find the minimum, or solve the function using algebra. As long as we can find the gradient, an initial estimate, we can just take steps down the hill until we find ourselves in the bottom of the valley. And this gradient descent method is probably the most powerful method for finding minima that exists. Finally, we looked at how to solve a problem subject to a constraint. We found that this reduced to equating the gradient of the function to the tangent of the constraint, taking two grads and then solving the simultaneous equations resulting from equating those two vectors. That was the Lagrange multipliers method. So this is really neat. The big picture is we've learned how to optimize functions, and we've taken ourselves from the realm of doing algebra to the realm of solving problems with computers. In the next module, what we'll do is we'll move on to look at how to fit functions to data using what's called the least squares method. So, this week we're finally going to apply all this multivariate calculus to help us fit functions to data. This is really handy. It allows us to make sense of our data, to start doing statistics testing, and to start to really apply all of this stuff we've been doing into the real world. If you have some big bundle of data, the first thing you need to do is to clean it up. There are other courses on this, but the first thing you need to do is clean it up to get it into shape to start doing the maths with. That means figuring out what the sensible thing to do is with things like partially empty data entries, zeros, those sorts of things, to figure out if you can do any dimensionality reduction by binning or grouping the data together, eliminating duplicates, garbage data, all those sorts of things. Often the easiest thing to do is to tag all of your data so that you can reorder them and put them back in where you've changed the order, then sort them and look for funny values and then figure out what to do with those, to get rid of them altogether or to replace them with something sensible. And then once you've cleaned it up, you can start graphing it. Take averages, look at standard deviations and all those sorts of things. Of course, in doing this, it really helps if you're interested in the data. You need it to be kind of like a person that you want to figure out and understand until it becomes an old friend. If over time as you collect more data and it starts to change, you want to get to the point where you're going to notice those changes, actually. So you really want to get it intimate and friendly with your data. Once you've graphed it in a sensible way, you'll often get a plot like this guy here, which is a simple XY plot of some data. This data seems to plot like a straight line. If you know something physically about the processes involved in generating the data, or if you have some hypothesis as to how the variables are related, then you can try and fit that model to the data. Alternatively, you can just try fitting something sensible based on how it looks, like a straight line to this data here, for example. Now, I can model my straight line y here as being a function of the I observations xi and a vector a of the fitting parameters. In the case of a straight line equals y equals mx plus c, then the parameters in the vector a would be the gradient m and the intercept c of the straight line. So here I've plotted the optimal straight line for this data. It happens to have a gradient of 215 gigapascals GPa and an intercept of 0.3 GPa for c. I can also find the mean of x, x bar, and the mean of y, y bar, which are at the geometric centre of mass of that data set. Now, in order to find the optimal value of m and c, let's first define a residual r, which we define as the difference between the data items, yi, and the predicted location of those on the line at y, which would be mx plus c. So r is yi minus mxi minus c. Then I can take a measure of the overall quality of the fit, being a quantity I'll call chi-squared, which is the sum of the squares of the residuals r. I do this so that I penalise both data that are above and data that are below the line. I don't want the pluses and minuses to net off against each other. Also, I really want to badly penalise data items that are a long way away from the line. And then I'm going to try and find the best chi-squared possible, the one that's lowest. I'm doing a minimisation. So now, it's worth plotting out what chi-squared is going to look like for lots of different possible values of m and c, which is what I've done on this contour plot here. In the middle at about 215 and near an intercept of 0, I find my minimum, and the further I get away from those, the worse it is. And note that in terms of chi-squared, it's slanted. There seems to be some kind of trade-off. The bigger c gets, the lower the optimum value of the gradient m, and vice versa. And if I look on this plot, that's kind of sort of obvious. If I make the line steeper on the original fit, then in order for it to fit well, the intercept's going to have to get smaller. Actually, I'm pivoting about the centre of mass. And also this shallow trough here in the chi-squared value is going to be really quite shallow. So this is actually going to be quite a tricky problem for a steepest descent algorithm. It's going to be easy to get down the sides, but it's going to be difficult to get down the bottom of the valley to find the actual minimum. But nevertheless, it looks like it's going to be quite an okay problem to solve. It has one easy to spot minimum, and therefore we can find it. And note that to do this with any precision, if I do it simply by doing lots of computations here, like I've done, for different m's and c's and finding the minimum that way, plotting it all out, finding the minimum on this graph. To do this, I have to do a lot of maths. In MATLAB, this contour plot took about 200,000 computations to make. So even for a simple problem like this, we really do want to find an algorithm that's going to let us get there a bit more efficiently. Now, the minimum is going to be found when the gradient of chi-squared is 0. So if we just take the grad of chi-squared with respect to the fitting parameters and set it to 0, that's going to be our solution. Now, the neat thing is that in this particular case, we can actually solve this problem explicitly. So that's what we're going to do in this video. But then we'll go on to see how to do it by linear descent, and then we'll find a better algorithm, and then we'll explore how to do this sort of problem where it's not so easy to do explicitly. So if we differentiate the first row with respect to m, then the first thing to worry about is all these sums over the data items I. But actually it turns out that we don't need to worry about these sums because we're not differentiating the xi or the yi themselves. So they'll just sit benignly in the sum. You know, mx1 plus mx2 plus mx3 is the same as if we differentiate that with respect to m, it's we just get x1 plus x2 plus x3. So we don't have to worry about those sums. And then it's easy, right? We differentiate a square, that drops in power by 1, and we multiply by 2. And then we take the differential of the inside of the bracket, which with respect to m is minus xi. We can then take that minus 2 outside of the sum altogether, in fact. For the second row, it's easier because the differential of the inside of the bracket with respect to c is just minus 1. So we just get the 2 down from the power and the minus sign, and so it all looks quite easy. Keeping on looking at the second row, then the sum of c times the number of data items we can take out of the sum altogether. And then we've just got the sum of the yi's and the sum of m times the xi's. And if we divide that through by the number of data items, we get our result that c is going to be y bar minus m times x bar, y bar and x bar being the average. We can carry on in that way and generate an answer to m, which I'm just going to leave here. I don't think there's any point in showing all the maths to you blow by blow. It's a bit trickier to see, and I'm not going to go through actually the maths and the derivation, but you can also find estimates for the uncertainties in c and m, which I've put up here, which I'll call sigma c and sigma m. And it's very important actually when you're doing a fit to get an idea of the uncertainties in those fitting parameters and to quote those in your fit. So I'm just going to leave those here in case you need to use them. So coming back to our fitted data, we can plot it out again here. Now the amazing thing here is just how accurate this sort of fitting really is. It's really cool. You know, we've got quite noisy data, and a gradient of 215, but the uncertainty is only 9. It's about 5%. It's really amazing. Now you should always plot your fit and visually compare it, just as a sanity check. And we can see why this is a good idea here. This is Anscombe's famous quartet. You can find the graph on Wikipedia. All these 4 data sets have the same chi-squared, means, best fit lines, and uncertainties in the fitting parameters. But they're obviously very different data. In the right-hand 2 cases, probably fitting a straight line is just the wrong thing to do. The bottom left, if you remove the flyer data point, the gradient's different, and the intercept. It's only the top left where the fit's actually doing the right thing altogether. And there's another subtlety actually, which is if we go back and look at C, the intercept, we can see that the intercept depends on the gradient m, which is what we said earlier when we looked at our plot of chi-squared. Now there's a way to recast the problem, which is to look at the deviations from the centre of the mass of the data at x bar instead, and then the intercept, b now, rather than c, is the location of the centre of mass in y at y bar. And then the constant term in the fit b, that constant b, doesn't depend on the gradient anymore, and neither, therefore, does its uncertainty include a term from the uncertainty in m. In fact, if I plot out the contour plot for chi-squared, when I do that, I find that it then isn't slanted. It's a nice sort of circular looking thing. Because I've removed the interaction between m and the constant term. So it's a mathematically much more reasonable, well-postulated problem. So that's the essence of regression, of how to fit a line to some data. And this is a totally, really useful life skill, almost whatever your professional job. What we'll do in the next couple of videos is look at how to do this in more complicated cases with more complicated functions and how to extend the idea of regression to those cases. The main thing really that we've defined here that's important to remember is this goodness of fit estimator, chi-squared, the sum of the squares of the deviations of the fit from the data. And chi-squared is going to be really useful to us going forward. In this video, we're going to look at how to finally learn how to fit our distribution of heights data. Then in the following exercise, you'll actually do that for yourself. And then in the next video, we'll wrap up with looking at how to do this practically in MATLAB or Python. So we're looking at how to fit a function that's arbitrarily complicated compared to the simplest case of linear regression, y equals mx plus c, that we looked at last time. Of course, there's intermediate possibilities between very complicated and the simplest possible, but this gives you the general case before we move on to look at how to do this in the computer using tools instead of writing our own. So let's say we have a function y of some variable x, and that function has parameters in it, a, k, where k goes from 1 all the way up to m. So there's m of these a's. So for example, we could have x minus a1 squared plus a2. That would be an example of some function y. This function isn't linear in a1, notice. If I double a1, I don't double the function. So it's a non-linear least squares we're going to do. Now, say I want to fit the parameters a, k to some data. So I've got some data observations. I've got I equals 1 to n of them. And I've got pairs of data, yi and xi. So for every x, I've got a y. And I have an associated uncertainty, sigma I. That is, the more uncertain I am about the data point yi, the bigger the uncertainty sigma is going to be. So I can sketch that out. Something like this, for instance, as an example of my yi's and my xi's are there. So I've got an xi, yi, and each one's got an uncertainty sigma I there. Then I'm going to define a goodness of fit parameter chi-squared there, as being the sum over all the data points I of the difference between the yi and the model of xi with its parameters ak. And I'm going to divide all of those by sigma squared, and I'm going to take the squares of the differences. So what I'm doing here is I'm penalising each of these differences by an uncertainty sigma squared. When I make chi-squared, so that uncertain data points have a low weight in my sum of chi-squared, so that they don't affect the fit too much. If we don't know what the sigmas are, we could assign them all to be 1, right? This will just drop out. But if we have an idea of the measurement uncertainties, this gives us a way to include it. And my minima for chi-squared is, of course, going to be when the grad of chi-squared is equal to 0. Now, in the general case, I might be able to write down an expression for grad here, but I might not be able to solve it algebraically. So instead, I'm going to look to solve grad chi-squared equals 0 by steepest descent, going down the contours, simply by updating the vector of fitting parameters a. So I've got my vector a. I'm going to say that my next iteration is going to be my current iteration minus some constant times the grad of chi-squared. So I'm going to go down the gradient here by an amount given by the constant, which is sort of a pull handle for how aggressive I want to be in going down the steepest descent. And that I'm going to use to make my next guess for what the fitting parameters should be. And I'm going to write them down as a vector. And I'll keep doing that until I reach this criteria, that the grad of chi-squared is 0, or which means I've found the minima. Or failing that until chi-squared stops changing, which should be the same thing, right? Or I just give up because it's been so many iterations and I get bored and I decide that something's gone wrong. So to do this grad, I've got to differentiate chi-squared. So I've got to do d chi-squared by dak for each of the k's in turn. And when I do that, well, the sum has nothing to do with k, because it's to do with I. And I'm going to get a 2 down. And and I'm going to get the sigma squared has nothing to do with k. When I differentiate this, I'll get the 2 down, and then I'll have the bracket itself, yi minus y of xi and the ak's. And then I'm going to get the differential of the bracket. I get a minus sign out of that, and I get dy dak. So I get dy dak. So that's going to be my differential there. The minus 2 I can just take out. So when I come to update here, if I wrap the minus 2 into the constant, I can just make that a plus, ignore the 2. So I'm then going to get a current plus this thing, the sum from I equals 1 to n, because the minus signs will go, I'll wrap the 2 into the constant, then I'll just get this, yi minus y of xi and the ak's divided by sigma squared times the differential evaluated at a current, because I don't know a next yet. So the steepest descent formula here is just going to be that a next is equal to a current plus this sum, and I've got to be able to differentiate y with respect to ak. And this is one of these formulae that look really intimidating, but really isn't when you actually try to use it. For our example here, when you take this example here, if we differentiate that with respect to a1, then we'll get that dy by a1 is equal to minus 2x minus a1. I take the 2 down and I get a minus sign when I differentiate the stuff in the bracket. And when I do dy by dA2, I'm just going to get 1. So it's actually really easy when we come to finally use it, but the expression looks intimidating. So that's the steepest descent formula for the case of fitting a nonlinear function, where we're trying to minimize the sum of the squares of the residuals, and this is therefore called nonlinear least squares fitting. There are lots of more complicated methods than steepest descent for solving these sorts of problems, which we'll look at a little bit next time. But first I want you to try and give this a go and code it up and see how it looks for the sandpit problem that you were doing before. So that's the simplest version of how to do a general fitting, a finding of the minimum or least value of the sum of the squares of the residuals, for a model that's nonlinear in both the functions and the fitting parameters. So it's called generalized nonlinear least squares fitting. In this video, we're going to make some final comments on the least squares regression fitting of data, and we're going to look at how we really do this in anger in the world using computational tools like MATLAB or Python or R. So you've made a gradient descent least squares minimizer and then used that to solve the sandpit problem already. There are a few comments to make before we move on. In reality, there are a huge number of solvers for nonlinear least squares problems. We can observe that if we do a Taylor series expansion of chi-squared, then the second term, the second derivative, is the Hessian, which gives us information about the curvature or the gradient of the gradient of the Jacobian. And therefore we can shoot directly for where the Jacobian is 0, just as in Newton-Raphson, using that second derivative. Now, using the Hessian would be faster than simply taking steps along a steepest descent algorithm. Effectively, we'd be using the Hessian to give us a guess as to the size of the step we should take in gradient descent. The problem is that often the Hessian isn't very stable, especially far from the minimum. So the Levenberg-Marquardt method uses steepest descent far from the minimum and then switches to using the Hessian as it gets close to the minimum, based on a criteria as to whether chi-squared is getting better or not. If it's getting better, it uses the Hessian, and if it's in trouble, it uses steepest descent. There's also the Gauss-Newton method and the BFGS method, amongst many others, that either use the Hessian directly or build up information about the Hessian over successive iterations. And depending on the convergence, then different methods may be better than others. Robust fitting is another topic you should be aware of in case you need to look it up later. If we come back to Anscombe's quartet here, we see that the bottom left data set in our problem has just that one flyer data point. A truly robust fitting method would be unbothered by such a data point. One approach to robust fitting minimises, instead of the least squares, the absolute unsquared deviations. So it doesn't weight the points that are far away from the line as strongly. And that means it fits a little bit what visually looks a bit better. Now, let's turn to look at how you do this in the real world. In MATLAB, it's easy. You simply import your data using the Import Data tab at the top of the screen, and then flick over to the Apps tab and start up Curve Fitting, the Curve Fitting app. There you can even symbolically define your own algorithm. You have to pick a starting guess and it will fit your function for you. Or you can use a pre-built function that already knows its Jacobians and will therefore be faster and more efficient. In Python, it's very nearly as simple. In the scientific Python SciP set of modules, the optimizer module includes a least squares curve fitting minimizer, curve fit, which is at the link below this video. Accompanying this video, we've left you one of the SciP examples for fitting some data so you can see how to use it. This is it. And it's amazing. The fitting really works very well, produces this nice graph here of this apparently noisy data with this crazy function. And the fitting only takes 3 lines, the 3 bold ones here, 2 lines to define the function and 1 line to do the fit. The rest of that code is all about plotting it and importing the data and everything else. Well, generating it in this case, actually. Effectively, this set of routines in SciP is the modern implementation of what's called MinPack, which was a Fortran set of routines published by Georges Moret in 1980 and described in the book Numerical Recipes. And it's absolutely astonishing how easy it is to do this stuff now. You know, when I was a student, you were reduced to reading this long, difficult textbook. Now you just effectively write 1 line in Python. Just as in Python, in the R statistical programming language, there's also a minimizer for doing nonlinear least squares fitting of models to data. So if you like R for looking at data, you can also do all this stuff just as easily in R. So what I want you to do now is write a Python code block to fit the Gaussian distribution shown here. You'll need to give it a starting guess, and we give you the input data for the height distribution in the population. This is the final height distribution data set that we've been talking about schematically all the way through these 2 courses. And what you'll find is that the mean height, B here, is about 178 centimetres, and the characteristic width of this distribution is about 11 centimetres. That's parameter C in the equation here. Now it's useful at this point to think about why we need to have the starting guess. If we started with a guess here for the mean of 100 centimetres, the model curve wouldn't overlap with the data at all. So when we did a little move to B, we get no change, and therefore the gradient of chi-squared with respect to the mean B would be 0. So the algorithm wouldn't know what direction to go in. We wouldn't get a sensible answer for the Jacobian or for grad, and therefore our algorithm wouldn't know where to go to find the minimum. So in doing any of this data fitting, it's vital to come up with a good means for generating a starting guess. Here it's easy, you pick the biggest value, for instance. Not coincidentally, it's also equally important to compare the fit to the data and ask if you believe the final fit. So, what we've done in this video is we've finished our little discussion of using vectors and multivariate calculus together to help us do optimizations of functions and to fit data to functions. And it's turned out in the end to be really easy computationally. We can fit functions in just a few lines of code in Python or MATLAB or R. But now, after all this work, you understand something of how those algorithms work under the hood. And that means that hopefully you'll be much better off at figuring out how to fix them when they go wrong. For instance, where the Jacobian doesn't make any sense. And also, you've got all the maths you need to access the next course in this specialization on machine learning.
That brings us to the end of this introductory course on multivariate calculus for machine learning. Congratulations to you all for sticking with the course, and thank you for your contributions to the forums. We've moved very quickly, starting right at the beginning with the definition of the derivative, then exploring multidimensional mountain ranges, training neural networks, and finally finishing up by seeing regression in action. Although we certainly didn't cover all of the details of a traditional calculus course, what I hope is that you come away with an understanding of the fundamentals and language of calculus, as well as some intuition as to where it might be usefully applied in machine learning. It's been such a pleasure to teach you, and best of luck with the next course on the Mathematics for Machine Learning specialization.
Hi, I'm Mark. I'm a lecturer in statistical machine learning at Imperial College. In this course, we will be going through the mathematical foundations that we need in order to do dimensionality reduction with principal component analysis. Data in real life is often high-dimensional. For example, if we want to estimate the price of our house in a year's time, we can use data that helps us to do this. The type of the house, the size, the number of bedrooms and bathrooms, the value of houses in the neighborhood, when they were bought, the distance to the next train station and park, the number of crimes committed in the neighborhood, the economic climate, and so on and so forth. There are many things that influence the house price, and we collect this information in a data set that we can use to estimate the price of our house. Another example is the 640 by 480 pixels color image, which is a data point in a one-dimensional space, where every pixel corresponds to 3 dimensions, one for each color channel, red, green, and blue. Working with high-dimensional data comes with some difficulties. It is hard to analyze, interpretation is difficult, visualization is nearly impossible, and from a practical point of view, storage can be quite expensive. However, high-dimensional data also has some nice properties. For example, high-dimensional data is often overcomplete. That means many dimensions are redundant and can be explained by a combination of other dimensions. For example, if we took a color image with 4 channels, red, green, blue, and a grayscale channel, then the grayscale channel can be explained by a combination of the other 3 channels, and the image could equally be represented by red, green, and blue alone, as we can reconstruct the grayscale channel just using that information. Dimensionality reduction exploits structure and correlation and allows us to work with a more compact representation of the data, ideally without losing information. We can think of dimensionality reduction as a compression technique similar to JPEG or MP3, which are compression algorithms for images and music. Let's take a small binary image of the handwritten digit 8. We're looking at 28 by 28 pixels, each of which can be either black or white. Therefore, this image can be represented as a 784-dimensional vector. However, in this example, the pixels are not randomly black or white, there's structure. They often have the same value as the neighboring pixels. In this dataset, there are many examples of an 8. They differ a little bit, but they look sufficiently similar that we can identify them as 8. We can use dimensionality reduction now to find a lower dimensional representation of all 8s that is easier to work with than a 784-dimensional vector. The lower dimensional representation of a high-dimensional data point is often called a feature or a code. In this course, we will look at a classical algorithm for linear dimensionality reduction, principal component analysis, or PCA. The purpose of this course is to go through the necessary mathematical details to derive PCA. In the first module, we will look at statistical representations of data, for example using means and variances. And we also describe how means and variances change if we linearly transform our dataset. In the second module, we will look at the geometry in vector spaces and define how to compute distances and angles between vectors. In the third module, we'll use these results to project data onto lower dimensional subspaces, and in the fourth module, we'll derive PCA as a way to reduce dimensionality of data using orthogonal projections. When we work with data, we often need to find compact ways to describe some of its properties. It wouldn't be particularly handy or useful to give somebody the entire dataset. Instead, we can use some statistical properties to describe the data. For example, we can say something about the center or the average of the data, or the spread or orientation. In the following videos, we will be looking at exactly these kind of statistical properties and discuss mean values to describe average data points, variances that make statements about the spread, and covariances which characterize orientation and correlations. Data is often compactly described by some of its statistical properties, such as the mean and the variance. In this video, we'll explain how to compute means of datasets. The mean of a dataset describes the average data point. The mean does not have to be a typical data point, and it also does not need to be part of the dataset itself. For example, if we look at a set of images of the digit 8, the average image looks like this. It has properties of all images in the dataset, but it is not part of the dataset itself. we obtain the average 8 as follows. Remember that an image can be represented as a long vector in a high-dimensional vector space by stacking all pixels together. After transforming all images into these vectors, we take all image vectors in our dataset, add them together, and divide by the number of images in the dataset. This gives us the average image vector. If we then reshape that vector into an image again, we get the average digit in the dataset. Here's an example with 4 8s. The mean of the first one is just the image itself, but when we add the second image, we see that the average image now contains properties from both images. When we add the third image, the mean image is all 3 images on top of each other divided by 3. After the fourth image, we can still see characteristics of all 4 images in the average image. When we add more images to our dataset, the average digit becomes a bit more blurry. And if we take all 8s in our dataset, we get this 8 as the average image. Generally, if we have a dataset x1 to xn, let's say D consists of data points x1 to xn, we get the mean value or the expected value of this dataset as follows. We write, well, the expected value of D is 1 over the number of data points, so this is n, times the sum n equals 1 to capital N of xn. So we sum up all data points in our dataset and divide by the number of data points that we have. Let's look at an example. I create a dataset consisting of the 5 numbers that I get when I roll 5 dice. We got 1, 2, 4, 6, and 6. So let's write this down. So we're going to call this D prime is 1, 2, 4, 6, and 6. And now the expected value, or the average, of this data set is the sum of all elements in this data set. So this is 1 plus 2 plus 4 plus 6 plus 6 divided by the number of elements in our data set, and that is 5. So if we sum these things together and divide by 5, we get 19 over 5, or 3.8. We can clearly see that 3.8 is not part of the dataset and cannot even be achieved by rolling a dice. Therefore, it is also worthwhile keeping in mind that although the mean is the average of the dataset, it does not have to be a typical instance. In this video, we computed the mean value of datasets as the average data point. The mean value doesn't have to be part of the dataset. In the next video, we'll introduce variances to describe the spread of the data around the mean value. In the last video, we discussed mean values of datasets which represent an average data point. In this video, we will look at variances to describe other properties of a dataset. Let us have a look at 2 different datasets, D1 and D2. D1 is represented by the blue dots located at 1, 2, 4, and 5, and D2 is represented by the red squares at -1, 3, and 7. D1 and D2 have the same mean, which is 3, but the data points in D2 are less concentrated around the mean than the data points in D1. Remember, the mean value is the data point we would expect on average, but to describe the concentration of data points around the mean value, we can use the concept of the variance. The variance is used to characterize the variability or spread of data points in a dataset. In one dimension, we can look at the average squared distance of a data point from the mean value of this dataset. Okay, let's do this for D1 and D2. So D1 was 1, 2, 4, and 5, and the mean value or expected value of D1 was 3, and D2 was -1, 3, and 7 with exactly the same mean value. So now we want to compute the average squared distance of D1 from the mean and from D2 from the same mean. So let's do this for D1 first. So we get 1 minus 3 squared plus 2 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared. So these are the sum of the average of the squared distances, and to get the average we divide by 4, which is the number of data points in D1. So if we do the computation, we get 4 plus 1 plus 1 plus 4 divided by 4, which is 10 over 4. So now we do the same for D2. And for D2 we get minus 1 minus 3 squared plus 3 minus 3 squared plus 7 minus 3 squared. And we divide by the number of data points in D2, which is 3. And we get 16 plus 0 plus 16 divided by 3, which is 32 over 3. So now this number is now bigger than this number, which means that the average squared distance of D2 from the mean value is bigger than the average squared distance of D1 from the mean value, which indicates that the spread of the data is higher in D2 than in D1. So what we have done can be formalized. So assuming we have a data set consisting of n data points x1 to xn, then we can define the average squared distance as the following. So we have x1 up to xn, and then we define this to be our data set x, and we define now the variance of this data set to be 1 over n times the sum of small n equals 1 to big N of xn minus mu squared, where mu is the mean value of the data set x. Yeah, so what we have done here is exactly the same as what we did before with D1 and D2. We computed an average squared distance of the data points in the data set from the mean value of the data set. And now we can also make some statements about this. First, the variance as defined here can never be negative because we just sum up squared values. And that also means we can take the square root of the variance, and this is called the standard deviation. The standard deviation is expressed in the same units as the mean value, whereas the variance, unfortunately, is expressed in squared units, so comparing them is quite difficult. Therefore, when we talk about spread of the data, we usually look at standard deviations. So in this video, we looked at variances of one-dimensional data sets, and in the next video, we will generalize this to higher dimensions. In the last video, we looked at variances for one-dimensional data sets. And in this video, we were looking at variances for high-dimensional data sets. The intuition and definition of the variance we had earlier does not really work in the same way in high dimensions, and squaring vectors is not really defined. Assuming we have a two-dimensional data set, we can now compute variances in the x direction and the y direction. But these variances are insufficient to fully describe what is going on in the data set. In particular, we only have the variation of the data in either direction, independent of the other direction, but we may also be interested in the relationship between the x and y variables. And this is where the concept of the covariance between these components comes into play. Let's have a look at an example in two dimensions. For this data set, we can compute the variances in the y direction and the variances in the x direction, which are indicated by these vertical and horizontal bars. But this can be insufficient, because we can look at other examples where the variances in the x and y directions are the same, but the data set look very different. If we look at this particular example, we have a different shape of the data set, but the variances in the x direction and the variance in the y direction are exactly the same, and the mean values of these data sets are also identical. And I can look at different sets like this one here and this one. These four data sets look very different. We've seen four different examples with four different properties or shapes of the data sets, but the variances in x and the variances in y and the mean values are identical. If we exclusively focus on the horizontal and vertical spread of the data, we can't explain any correlation between x and y. In this last figure, we can clearly see that on average, if the x value of a data point increases, then on average, the y value decreases, so that x and y are negatively correlated. This correlation can be captured by extending the notion of the variance to what is called the covariance of the data. The covariance between x and y is defined as follows. So covariance between x and y is defined as the expected value of x minus the mean in the x direction times y minus the mean in the y direction. Just write mu x is the expected value in the x direction and mu y is the expected value of the y coordinates. For the 2D data, we can therefore obtain 4 quantities of interest. We obtain the variance of x. We get the variance of y. And we also have the covariance terms, the covariance between x and y and the covariance between y and x. So we summarize these values in this matrix called the covariance matrix with 4 entries. And in the top left corner, we have the variance in the x direction. Then we get the covariance term between x and y in the top right corner, the covariance between y and x in the bottom left corner, and the variance of y in the bottom right corner. If the covariance between x and y is positive, then on average the y value increases if we increase x, and if the covariance between x and y is negative, then the y value decreases if we increase x on average. If the covariance between x and y is 0, then x and y have nothing to do with each other. They are uncorrelated. The covariance matrix is always a symmetric, positive, definite matrix with the variances on the diagonal and the cross covariances or covariances on the off diagonals. If we now look at d-dimensional data sets, let's say we have a data set consisting of n vectors, x1 to xn, and every xi is in Rd, then we can compute the variance of this data set as 1 over n times the sum I equals 1 to capital N of xi minus mu times xi minus mu transpose, where mu is the mean of the data set, and this is called the covariance matrix of the data, and this is a d by d matrix. So previously we looked at means and variances to describe statistical properties of data sets. In this video we'll discuss what happens to means and variances when we linearly transform the data set. That means we shift it around or stretch it. So let's look at a data set D, which is given by these blue dots over here. So we have a data set D, which is -1, 2, and 3. Now let's compute the mean value of this data set to start with. So the expected value of D is -1 plus 2 plus 3 divided by 3, which is 4 over 3. So I'm indicating the mean value of this data set by this blue star. So now the question is, what happens to this data set when we shift it? So let's have a look at a shift by 2 to the right. So we end up with these red dots now. What happens to the mean value of this data set if we shift the data set, the original data set, to the right? Well, the answer is the mean also shifts by 2. So let's define D prime to be the data set 1 plus, 1, 4, and 5, which is d plus 2 for every individual component in D, then the expected value of d prime is 1 plus 4 plus 5 divided by 3, which is 10 over 3. And in particular, we can write this in a slightly different way. We can write this as 4 over 3, which comes from here, plus 2, which is the shift or the offset of the original data set. So we can generalize this now to general shifts. And we can write an expected value of d plus a, where a is a constant factor, is a plus the expected value of d. So up to this point, we know what happens to the mean of the data set when we shift the data set. But what happens if we stretch the data set? Let's say we also stretch by a factor 2, and that means we multiply every individual component in the data set D by 2. So then we end up with this data set on the indicated by the red dots here, and we define D double prime to be -2, 4, and 6. And if we now compute the mean of D double prime, then we end up with -2 plus 4 plus 6 divided by 3, which is 8 over 3. And we can rewrite that again in a convenient way, which is 4 over 3, which again comes from here, plus, times 2, which is the scaling factor. So in general, we can write that the expected value of alpha times d is alpha times the expected value of d. Putting everything together, we can shift and scale our original data set, and the new mean of this linear transformation is given as follows. So if we compute the expected value of alpha times d plus a, we get alpha times the expected value of d plus a, where alpha is the scaling factor and a is the shift. In this video, we looked at the effect of linear transformations on the mean value of a data set. In the next video, we will look at exactly the same for the variances. We've seen what shifting and scaling a data set does to the mean. Now let's have a look at the effects on the variance. Remember that the variance is a measure of the spread of the data. What do we expect when a data set is shifted? Let's have a look at this data set over here. We have 3 data points given at -1, +2, and +3. And now we are shifting the data set towards the right. The variance of the data set is indicated by the blue bar at the bottom. The shifted data set is now given by the red dots, and we shift every individual data point by 2. So the question is now, what happens to the variance? Well, the shift of the data does not really affect the relation of the data points among themselves. Therefore, the variance does not change. The variance is identical. So the variance of the blue data set is identical to the variance of the red data set. Therefore, a general result is that if we have the variance of D, that is exactly the same as the variance of our data set D plus A, where A is an offset applied to every individual element of D. Let's now scale the data set and see what effect that has on the variance of the data. So we're going to take exactly the same data set as before. The variance is indicated by the blue bar. And we're going to scale every individual data point by 2. So the question is, what is the variance of 2 times D? So new data set is indicated by these red dots. Remember that the variance is the average squared distance of the data points from the mean. If we scale the dataset by a factor of 2, the distance of every data point to the mean is scaled by 2. But the squared distance is scaled by 4. And the variance is therefore 4 times as big as it used to be. And our next result is that the variance of alpha times d is alpha squared times the variance of d, where alpha is a real number that scales every individual element in the dataset d. Now let's have a look at high-dimensional problems. Assume we have a dataset d, which is a collection of data points x1 to xn, and the xi live in Rp. Remember, the variance of this dataset is given by a covariance matrix. If we perform a linear transformation of every data point, say axi plus b, for a given matrix A and an offset vector b, the question is, what happens to our dataset if we do this to every single data point? Well, we get the covariance matrix of the transformed dataset as follows. We're getting the variance of A times D plus B is A times the variance of D times A transpose. In this video, we saw what effects a linear transformation of a dataset has on the mean and the variance. In particular, we saw that shifting data has only an effect on the mean, but not the variance, where scaling the data affects both the mean and the variance. We've already come to the end of this module. We looked at statistics to summarize and characterize datasets, means, variances, and covariances. We looked at how these statistics change when we shift or scale the dataset. We'll use means and covariances in Module 4 when we discuss the PCA algorithm for dimensionality reduction. Well done. It is often necessary to measure similarity between data points. In the context of dimensionality reduction, we are interested in finding compact representations of data that live in a lower dimensional space, but which are similar to the original data. One of the key concepts we will be looking at in this course is orthogonality. We'll use orthogonal projections of data points as a way to compress data while minimizing the loss of information. Thinking of data points as vectors in a vector space will allow us to look at two types of similarity between data points: distances of data points from each other and the angle between these two data points. Let's have a look at an example. Assume we're living in a two-dimensional world and we have two vectors, x and y. Things that we will be discussing in this course are how to compute the length of individual vectors. So that means for x, that means the length of this line here. We will be looking at angles between two vectors, and we would be looking at distances between individual data points or vectors in this vector space. So in this case, we would be interested in the distance between x and y. In order to measure angles and compute lengths and distances, we need to equip the vector space with an inner product, which allows us to talk about geometric properties in this vector space. In the next videos, we will be looking at computing lengths, distances between vectors, and angles between vectors. In order to measure angles, lengths, and distances, we need to equip the vector space with an inner product which allows us to talk about geometric properties in a vector space. An example of an inner product that we may know already is the dot product between two vectors x and y. If x and y are two vectors in Rn, then the dot product is defined as x transpose y is the sum I equals 1 to n of xi times yi, where x and y are n-dimensional vectors. The length of x is then defined as the square root of the dot product of x with itself. So the length of x is the square root of x transpose x, which we can also write as the square root of the sum of I equals 1 to n of xi squared. Let's have a look at an example. We take a vector x as 1, 2 and a vector y as 2, 1 in a two-dimensional plane. Then we can compute the length of the vector of x as the square root of 1 squared plus 2 squared, which is the square root of 5, and the length of y similarly is the square root of 5 as well. If we're interested in the distance between two vectors x and y, we simply compute the length of the difference vector. So we generally define then the distance between x and y to be the length or the norm of x minus y, which is the square root of x minus y transpose times x minus y. So now let's compute the distance between our two vectors over here. So the distance between these two vectors is effectively just the length of this difference. So we can write this as the norm of 1, 2 minus 2, 1. So this is our difference vector, and that is the norm of minus 1 and 1. And this is the square root of 1 plus 1, which is the square root of 2. So the length of this yellow segment is square root 2. So the last thing we are still interested in is the angle between two vectors, and we can compute the angle also using the dot product. The cosine of the angle, let's call this angle alpha. So the cosine of alpha is given by x transpose y divided by the length of x times the length of y. And in our example over here, we'll get that the cosine of the angle between x and y is x transpose times y, which is 4, divided by the length of x times the length of y. But we've done these computations already, which come from here. So it's square root 5 in any case. So therefore, we get the cosine alpha is 4 over 5, which corresponds to approximately 0.64 radians. And that is our angle alpha between these two vectors. In this video, we looked at dot products as special cases of inner products to compute lengths of vectors, to compute distances between vectors, and angles between two vectors. And in part 2 of this video, we will be looking at general inner products to compute exactly the same quantities. Previously, we looked at the dot product to compute angles, lengths, and distances. In this video, we will be looking at generalizations of the dot product in order to compute angles, lengths, and distances. Sometimes it is necessary to use an unconventional way to measure these geometric properties, and the inner product allows us to do exactly this kind of thing. An inner product is a generalization of the dot product, but with the same idea in mind. We want to express geometric properties such as lengths and angles between vectors. Let's define what an inner product actually is. So let's write the definition. We're looking at two vectors for any vectors x and y in a vector space V. An inner product is defined as a symmetric, positive, definite bilinear mapping. So let's see what that means. We take a mapping that takes two inputs out of this vector space. It's a mapping from V times V to the real numbers. and we say this function is symmetric, positive definite, and bilinear. So let's unpack this a little bit. Let's start with bilinearity. Bilinear means that for vectors x, y, and z in this vector space and real numbers lambda, we get that lambda times x plus z and y, so the scalar, the inner product between lambda x plus z and y can be written as lambda times the inner product between x and y plus the inner product between z and y. So this is linearity only in the first argument of this function, and we require to have linearity also for the second argument of this function. So similarly, we will then require that the inner product between x and lambda y plus z is lambda times the inner product between x and y plus the inner product between x and z. So this means linearity also in the second argument, and that's the reason why this is called bilinear. It means linearity in both arguments of this function. So positive definite means that the inner product of x with itself is greater or equal to 0, and equality holds if and only if x is the 0 vector. And the last component that we need is symmetry, and symmetric means that the inner product of x and y is the same as the inner product of y and x. So the order does not matter. Let's have a look at an example in R2. If we define our inner product to be x transpose times the identity matrix times y, then we get exactly the dot product that we are very familiar with. But now let's have a look at a different example where we define our inner product to be x transpose times A times y, where A is the matrix 2, 1, 1, 2. Then we can also write our inner product to be 2 times x1, y1 plus x2, y1 plus x1, y2 plus 2 times x2, y2, and this inner product is different from the dot product. Any symmetric positive definite matrix in this equation defines a valid inner product. In this video, we introduce the concept of an inner product, which we will use in the next videos to discuss geometric properties of vectors, such as lengths and angles. In the last video, we defined inner products. Now we will use inner products to compute the lengths of vectors and distances between vectors. The length of a vector is defined via the inner product using the following equation. So the length of a vector x is defined as the square root of the inner product of x with itself. Remember that the inner product is positive definite. That means this expression is greater or equal than 0. Therefore, we can take this square root. We can now also see that the length of a vector depends on the inner product, and depending on the choice of the inner product, the length of a vector can be quite different. Similarly, the geometry in the vector space can be very different. The length of x is also called the norm of x. So let's have a look at an example. Assume we're interested in computing the length of a vector in 2 dimensions, and x is given as the vector 1, 1. So in a diagram, we have 1 here and approximately here. Then our vector x would be here. And now we're interested in computing the length of this vector. So in order to compute the length of the vector, we need to define an inner product. So why don't we start with the standard dot product? So if we define xy to be x transpose y, so the inner product of x and y to be x transpose times y, then the length of x is the square root of 2. So it's 1 squared plus 1 squared, and we take the square root of this. Now let's have a look at a different inner product. Let's define xy to be x transpose times 1 minus a half 1 times y, which we can also write as x1 times y1 minus a half x1 y2 plus x2 y1 plus x2 y2. Using the definition of this inner product, then the length of a vector is the square root of x1 squared minus a half x1 x2 plus x2 x1 plus x2 squared. And this is identical to the square root of x1 squared minus x1 x2 plus x2 squared. And we'll get smaller values than the dot product definition up here if this expression is positive. If we now use the definition of this inner product to compute the length of our vector up here, we will get that the squared norm, or the inner product of x with itself, is 1 plus 1 minus 1, which is 1, and therefore the norm of x is just 1. And 1 in this case would be the length of the vector using this unusual definition of an inner product, whereas the same vector would be longer had we used the dot product up here. The norm that we just looked at also has some nice properties. Let me write a few of those down. So in particular, one of the properties is that if we take a vector and stretch it by a scalar lambda, then the norm of this stretched version is the absolute value of lambda times the norm of x. The second property is the triangle inequality. Which says that the norm of x plus y is smaller or equal to than the norm of x plus the norm of y. Let's have a look at an illustration. So let's assume we have our coordinate system in 2 dimensions, and we use the standard vectors x equals 1, 0. So x would be sitting exactly here. So this is x, and y is 0, 1. Then x plus y is sitting here. If we use the dot product as our inner product, then the norm of x is 1, which is the same as the norm of y. And the norm of x plus y is square root 2. So what the triangle inequality says that x plus y norm is smaller or equal than the norm of x plus the norm of y, and that is also true in our case because square root of 2 is smaller or equal than 2. And there's another inequality I would like to mention, which is the Cauchy-Schwarz inequality. And that one says that the absolute value of the inner product of x with y is smaller or equal than the product of the individual norms of the two vectors. In this video, we looked at lengths of vectors using the definition of inner products. And now we're going to use this to compute distances between vectors in the next video. Now that we know how to compute the length of a vector, we can also compute distances between any two vectors x and y. The distance between two vectors is defined as the length of the difference vector. So we can write the distance between x and y to be the norm of x minus y. And as we know, this depends on the definition of our inner product. If we use a dot product, then the distance is called the Euclidean distance. Let's have a look at an example. We're going to look at two vectors, x and y. We're going to say x is 2, 3, and y is 4, 1. So let's draw this. So this is x, and y is over here. In order to compute the distance between these two vectors, the first thing we actually need to do is let's have a look at this difference vector. So x minus y is 2 minus 4 in the first component and 3 minus 1 in the second component. That means we get minus 2 and plus 2 as the difference vector. So now we can define inner products. And let's now use the dot product as our first example. If we use the dot product to compute the length of this difference vector, we will get the square root of the first component squared plus the second component squared, which is 4 plus 4, and that's the square root of 8. And if we use a different inner product, let's say we define the inner product between x and y to be x transpose times 1 minus half minus a half and 1 times y, then if we now use the difference vector here, the result will be the square root of 12. So we can see that depending on the choice of our inner product, we will get different answers of what the distance between x and y actually is. In this video, we computed distances between two vectors using inner products. And we saw that depending on the inner product, the distance between these two vectors can differ. Previously, we have looked at lengths of vectors and distances between vectors. In this video, we'll introduce angles as a second important geometric concept that will allow us to define orthogonality. Orthogonality is central to projections and dimensionality reduction. Similar to lengths and distances, the angle between two vectors is defined through the inner product. If we have two vectors, x and y, and we want to determine the angle between them, we can use the following relationship. The cosine of this angle between the two vectors is given by the inner product between the two vectors divided by the norm of x times the norm of y. Let us have a look at an example. And let's compute an angle between two vectors x, which is 1, 1, and y, which is 1, 2. And let's quickly draw this. This is x. And this is y. And we're interested in the angle omega between those. If we use a dot product as the inner product, we get that the cosine of omega is x transpose y divided by the square root of x transpose x times y transpose y, which is 3 divided by the square root of 10. This means the angle is approximately 0.32 radians or 18 degrees. Intuitively, the angle between two vectors tells us how similar their orientations are. Let's look at another example in 2D, again with the dot product as the inner product. We're going to look at the same vector x that we used to have before, so x equals 1, 1, which is this vector over here. And now we choose y to be -1 and +1, and this is this vector. Now we're going to compute the angle between these two vectors, and we see that the cosine of this angle between x and y is, with the dot product, x transpose times y divided by the norm of x times the norm of y. And this evaluates to 0. This means that omega is pi over 2 in radians, or if we want to say this in degrees, we have 90 degrees. This is an example where two vectors are orthogonal. Generally, the inner product allows us to characterize orthogonality. Two vectors x and y, where x and y are non-zero vectors, are orthogonal if and only if their inner product is 0. This also means that orthogonality is defined with respect to an inner product, and vectors that are orthogonal with respect to one inner product do not have to be orthogonal with respect to another inner product. Let's take these two vectors that we just had, where the dot product between them gave that they are orthogonal, but now we're going to choose a different inner product. In particular, we're going to choose the inner product between x and y to be x transpose times the matrix 2, 0, 0, 1 times y. And if we choose this inner product, it follows that the inner product between x and y is -1. This means that the two vectors are not orthogonal with respect to this particular inner product. From a geometric point of view, we can think of two orthogonal vectors as two vectors that are most dissimilar and have nothing in common besides the origin. We can also find a basis of a vector space such that the basis vectors are all orthogonal to each other. That means we get the inner product between bi and bj is 0 if I is not the same index as j. And we can also use the inner product to normalize these basis vectors. That means we can make sure that every bi has length 1. Then we call this an orthonormal basis. In this video, we discussed how to compute angles between vectors using inner products. We also introduced the concept of orthogonality and saw that vectors may be orthogonal with respect to one inner product, but not necessarily if we change the inner product. We will be exploiting orthogonality later on in the course. If we have a vector and we want to compute the smallest difference vector to any point on a line that does not contain the vector, then we will end up finding a point on the line such that the segment between the point and the original vector is orthogonal to that line. In the previous videos, we looked at properties of inner products to compute lengths, angles, and distances. We focused on inner products of finite dimensional vector spaces. In this video, we will look at two examples of inner products of other types of vectors, inner products of functions and inner products of random variables. The inner products we discussed so far were defined for vectors with a finite number of entries, and we can think of these vectors as discrete functions with a finite number of function values. The concept of an inner product can be generalized to continuous valued functions as well. And then the sum over individual components of vectors turns into an integral. Then the inner product between two functions is defined as follows. We can write that the inner product between two functions u and v is the integral of an interval from a to b of u of x times v of x dx. And as with our normal inner product, we can define norms and orthogonality by looking at this inner product. If that integral evaluates to 0, the functions u and v are orthogonal. Let's have a look at an example. If we choose u of x equals sine x and v of x is cosine of x, and we define f of x to be u of x times v of x, which is sine x times cosine x, then we're going to end up with this function. This function is sine x times cosine x. We see that this function is odd, which means that f of minus x equals minus f of x. If we choose the integral limit to be minus pi and plus pi, then the integral of this product sine of x times cosine of x evaluates to 0. And that means that sine and cosine are orthogonal. And it actually holds that if we look at a set of functions, say 1 cosine x, cosine of 2x, cosine 3x, and so on, that all of these functions are orthogonal to each other if we integrate from minus pi to plus pi. Another example for defining an inner product between unusual types are random variables or random vectors. If we have two random variables which are uncorrelated, then we know the following relationship. We know that the variance of x plus y is the variance of x plus the variance of y, where x and y are random variables. If you remember that variances are measured in squared units, this looks very much like the Pythagorean theorem for right triangles. That one states that c squared equals a squared plus b squared. If we look at triangles of this form, where this is a, b, and this is c. Let's see whether we can find a geometric interpretation of the variance relation of uncorrelated random variables. Random variables can be considered vectors in a vector space, and we can define inner products to obtain geometric properties of these random variables. If we define the inner product between two random variables, so between x and y, to be the covariance between x and y, we see that the covariance is symmetric, positive definite, and linear. So linearity would mean that the covariance of lambda times x plus y and z, where x, y, and z are random variables, and lambda is a real number, is lambda times the covariance between x and z plus the covariance between y and z. And if the length of a random variable is the square root of the covariance between of x with itself, which is the square root of the variance of x, then this is the standard deviation of the random variable x. So this is the length of a random variable. Therefore, the zero vector is a vector that has no uncertainty. That means standard deviation is 0. If we now look at the angle between two random variables, we get the following relationship. We get the cosine of theta, which is the angle between two random variables, is by definition the inner product between the two random variables divided by the length of the first random variable times the length of the second random variable. And if we now write this out using the definition of our inner product, we get the covariance between x and y divided by the square root of the variance of x times the variance of y. And this evaluates to 0 if and only if the covariance between x and y is 0, and that is the case when x and y are uncorrelated. Coming back now to our geometric interpretation, we would now replace a with the standard deviation of x, b is the standard deviation of y, and c is the square root of the variance of x plus the variance of y. And this is how we get our geometric interpretation of random variables. In this video, we looked at inner products of rather unusual objects, functions and random variables. However, even with functions and random variables, the inner product allows us to think about lengths and angles between these objects. In the case of random variables, we saw that the variance of the sum of two uncorrelated random variables can be geometrically interpreted using the Pythagorean theorem. This is the end of this module. Congratulations! In this module, we introduced the concept of an inner product, a generalization of the dot product. The inner product allows us to talk about geometric concepts such as lengths, distances, and angles between vectors. One special case we discussed was orthogonality. In the next modules, we will use orthogonality heavily for projections of high-dimensional data onto lower-dimensional subspaces, an integral part of principal component analysis. High-dimensional data is often hard to analyze or visualize. However, high-dimensional data quite often possesses the property that only a few dimensions contain most information, and most other dimensions are not essential to describe key properties of the data. When we compress or visualize high-dimensional data, we lose information. Ideally, we find the most informative dimensions in the data and keep them when we compress the data and ignore the irrelevant dimensions. In this course, we will have a close look at orthogonal projections, which play a central role in algorithms for dimensionality reduction. In this video, we'll look at orthogonal projections of vectors onto one-dimensional subspaces. Let's look at an illustration. We're given vector x in 2 dimensions, and x can be represented as a linear combination of the basis vectors of R2. We also have a one-dimensional subspace U with a basis vector b. That means all vectors in U can be represented as lambda times b for some lambda. Now we're interested in finding a vector in U that is closest to x. Let's have a look at this. When I compute the length of the difference of all vectors in U and the vector x, I'm getting the graph on the right. It turns out that we can find the vector in U that is closest to x by an orthogonal projection of x onto U. That means the difference vector of x and its projection is orthogonal to u. Overall, we are looking for the orthogonal projection of x onto u, and we will denote this projection by pi u of x. The projection has two important properties. First, since pi u of x is in u, it follows that there exists a lambda in R such that pi u of x can be written as lambda times b, a multiple of the basis vector that spans u. Then lambda is the coordinate of the projection with respect to the basis b of the subspace u. The second property is that the difference vector of x and its projection onto u is orthogonal to u. That means it's orthogonal to the basis vector that spans u. So the second property is that the inner product between b and the difference between pi u of x and x is 0. So that's the orthogonality condition. These properties generally hold for any x in Rd and one-dimensional subspaces U. Now let's exploit these two properties to find pi u of x. I've drawn the setting once more over here. We have a two-dimensional vector x. We have a one-dimensional subspace U, which is spanned by the vector b. And we're interested in finding the orthogonal projection of x onto u, which we call pi u of x. And we have two conditions for pi u of x. The first thing is that since pi u of x is an element of u, we can write it as a scaled version of the vector b. So there must be a lambda in R such that pi u of x is lambda times b. And the second condition is the orthogonality condition, that the difference vector between x and pi u of x is orthogonal to u, which means it's orthogonal to the spanning vector b. And now let's exploit these two properties to find pi u of x. So first, we start writing, we use the condition that b and pi u of x minus x inner product is 0, which is equivalent to that the inner product of b and pi u of x minus the inner product of b and x is 0, where we exploited now the linearity of the inner product. Now we're going to rewrite pi u of x as lambda times b. So this is equivalent to b times lambda b, or inner product with lambda b minus the inner product of b and x. That must be 0. Now we can move the lambda out again because of the linearity of the inner product, which is then lambda times the squared norm of b minus the inner product of b and x must be 0. And that is equivalent to lambda is the inner product of b with x divided by the squared norm of b. So now we found lambda, which is the coordinate of our projection with respect to the basis b. And that means that our projection using the first condition is lambda times b, which is now the inner product of b with x divided by the square norm of b times b. If we choose the dot product as the inner product, we can rewrite this in a slightly different way. So we would get b transpose times x times b divided by the squared norm of b. So now, given that this one is a scalar, we can just move it over here. So this is equivalent then to saying b times b transpose divided by the squared norm of b times x. is our projected point. And if we look at this, this is a matrix, and this matrix is a projection matrix that projects any point in 2 dimensions onto the one-dimensional subspace. So now if we look at the special case of B having norm 1, then we get a much simpler result, and we would get, so if the norm of B equals 1, then we will get that lambda is B transpose times x, and pi u of x is B times B transpose times x. So we would get the coordinate of the projected point with respect to the basis B just by looking at the dot product of B with x. And the projection matrix is simply given by B times B transpose. Let me make a comment at the end. Our projection pi u of x is still a vector in Rd. However, we no longer require d coordinates to represent it, but we only need a single one, which is the lambda. In this video, we discussed orthogonal projections of vectors onto one-dimensional subspaces. We arrived at the solution by making 2 observations. We must be able to represent the projected point using a multiple of the basis vector that spans the subspace, and the difference vector between the original vector and its projection is orthogonal to the subspace. In the next video, we will look at an example. In the last video, we derived the formula for projections of vectors onto a one-dimensional subspace. In particular, we arrived at this equation if we choose the dot product as the inner product. Here, x is a d-dimensional vector, and b is the basis vector that spans that one-dimensional subspace that we want to project x onto. In this video, we are going to look at an example. Assume our vector b that spans our one-dimensional subspace is the vector 2, 1, and the vector x we want to project onto that subspace is given by 1, 2. Let's quickly draw this. So x is the vector 1, 2. So x is living over here. And the vector b is going to be the vector 2, 1. And so this is b. And b spanning our subspace means that our subspace U is going to extend along this line. So now we're interested in computing the orthogonal projection of x onto U. So using now this equation here, we get, so x transpose times b is 2 plus 2. And now we divide by the squared norm of b. So the length of b is 2 squared plus 1 squared square root. So overall, we get the squared norm to be 5. And then times b will get us to 2, 1. So overall, 4 over 5 times the vector 2, 1. This means that our orthogonal projection is 4 over 5 times the vector b. That means if we take 4/5 of this vector, then we will get to our orthogonal projection. So this point here is now pi u of x, so the orthogonal projection of x onto u. And the length of this segment is 4/5 times the length of B. We've gone through orthogonal projections onto one-dimensional subspaces. In the next video, we're going to look at orthogonal projections onto higher dimensional subspaces. In the last video, we learned about orthogonal projections onto one-dimensional subspaces. In this video, we look at the general case of orthogonal projections onto n-dimensional subspaces. For this, we'll exploit the same concepts that worked in the one-dimensional case. Let's start with an illustration. We're going to look at a case where we have a vector x that is living in a three-dimensional space, and we define a subspace, a two-dimensional subspace U, which has basis vectors b1 and b2, which are, for example, this vector, and b2 is this vector. So we write U is spanned by b1 and b2. So U in this case would be the plane down here. So this is U. So now we are looking at the orthogonal projection of x onto U, and we're going to denote this by pi u of x. So that projection is going to look something like this. That's the projection point. So this is the orthogonal projection of x onto the subspace U. So we can already make two observations. The first thing is that because pi u of x is an element of U, it can be represented as a linear combination of the basis vectors of U. So that means we can write pi u of x is lambda 1 times b1 plus lambda 2 times b2 for appropriate values of lambda 1 and lambda 2. And the second property is that the difference vector of x minus pi u of x, so this vector over here, is orthogonal to U, which means it's orthogonal to all basis vectors of U. And we can now use the inner product for this, and we can write that x minus pi u of x inner product with b1 must be 0, and the same is true for b2. But now let's formulate our intuition for the general case where x is a d-dimensional vector, and we're going to look at an m-dimensional subspace U. Okay, let's derive this result. I copied our two insights up here, and I have defined two quantities. A lambda vector, which consists of all these lambda I here, and a B matrix, where we just concatenate all basis vectors of our subspace U. Now, with this definition, we can also write pi u of x equals b times lambda. Let's assume we use the dot product as our inner product. Now, if we use our second property, we'll get that so pi u of x minus x inner product with bi is now equivalently written as the inner product of b lambda minus x and bi, and this needs to be 0, where I just used the definition of p u of x in here. So now we can simplify this by exploiting the linearity of the inner product, and we'll get b lambda times, or inner product with bi minus the inner product of x with bi needs to be 0. And this holds for I equals 1 to m. With the inner product, we can now write this in the following way. We can write this as lambda transpose times b transpose times bi minus x transpose times bi equals 0 for I equals 1 to m. And now we can write this as a set of conditions. And if we summarize this, we would get lambda transpose times B transpose times B minus X transpose times B must be 0. Now we need to talk here about an m-dimensional 0 vector. What we would like to do now is we would like to identify lambda. For this, we are going to right multiply the inverse of B transpose times B onto the entire equation. And then we get lambda transpose equals X transpose times B times B transpose B inverse, which then also means we can write lambda as the transpose of this entire expression. We get B transpose B inverse, so this matrix is symmetric, so its transpose is the same as the original matrix, times B transpose X. So now we have identified lambda to be this, but we also know that our projection point can be written as B times lambda. So this means we will get pi u of x as B times lambda, which is B times B transpose B inverse times B transpose X. We can now identify this expression as the projection matrix, similar to the one-dimensional case. And in the special case of an orthonormal basis, B transpose times B is the identity matrix. So we would get pi u of x is B times B transpose times x. The projected vector pi u of x is still a vector in Rd, but we only require m coordinates, the lambda vector over here, to represent it as a linear combination of the basis vectors of the subspace U. We also effectively got the same result as in the one-dimensional case. Remember, in 1D we got lambda equals B transpose x divided by B transpose B, and we got a projection point pi u of x, which was B transpose x divided by B transpose B times B. Now, B transpose B is now expressed as matrix B transpose times matrix B, but we now have the inverse matrix sitting here instead of dividing by a scalar. That's the only difference between these two results. In this video, we looked at orthogonal projections of a vector onto a subspace of dimension m. We arrived at the solution by exploiting two properties. We must be able to represent the projection using a linear combination of the bases of the subspace, and the difference vector between the original vector and its projection is orthogonal to the subspace. In the next video, we're going to look at a concrete example. In the last video, we derived orthogonal projections of vectors onto m-dimensional subspaces. In this video, we'll run through a simple example. We're going to define x to be a three-dimensional vector given by 2, 1, 1, which is over here, and we define two basis vectors for our two-dimensional subspace, b1 to be 1, 2, 0, and b2 to be 1, 1, 0. So that means U, which is spanned by b1 and b2, is going to be effectively the plane and its extension. So this all is U. The orthogonal projection was given as pi u of x is B times lambda, and we define B now to be B1 and B2 concatenated, which is 1, 2, 0, 1, 1, 0. And lambda was given as B transpose B inverse times B transpose X. B transpose times X is given as 4, 3 vector. B transpose B is a 2 by 2 matrix, which is 5, 3, 3, 2. Now we solve for lambda as B transpose B inverse times B transpose X, which means we find lambda such that B transpose B lambda equals B transpose X. Using Gaussian elimination, we arrive at lambda equals minus 1, 3. And this implies our projection of X onto the space spanned by the two B vectors is minus 1 times B1 plus 3 times B2, which is 2, 1, 0. In our diagram over here, this would correspond to this vector here. This is pi u of x. This result makes sense because our projected point has as a third component the 0, and our subspace requires that a third component is always 0. Our projected vector is still a three-dimensional vector, but we can represent it using two coordinates if we use the basis defined by B1 and B2. Therefore, that is the compact representation of the projection of X onto this lower dimensional subspace. In this video, we looked at a concrete example of the orthogonal projection of a three-dimensional vector onto a two-dimensional subspace. In the next video, we're going to exploit orthogonal projections and derive a dimensionality reduction algorithm called principal component analysis. In this module, we discussed orthogonal projections of vectors onto subspaces. We exploited two things to get to the solution. The projected vector can be represented as a linear combination of the basis of the subspace, and the vector that connects the data point and its projection must be orthogonal to the subspace. We will use orthogonal projections in the next module when we introduce the PCA algorithm. This was a tricky module, but we made it through. Well done! In this course, we will introduce principal component analysis, or PCA, an algorithm for linear dimensionality reduction. PCA has been around for about 100 years and is still one of the most commonly used techniques for data compression and visualization. High-dimensional data, for example images, often has the property that it lies on a low-dimensional subspace and that many dimensions are highly correlated. Here's an illustration in 2 dimensions. Although the data does not quite lie on a straight line, the data does not vary much in 1 dimension, so that we can express it as if it was on a line with nearly no loss. A key idea behind PCA is to use orthogonal projections to find lower dimensional representations of data that retain as much information as possible, similar to the example that we just looked at. In the following videos, we will derive PCA as an algorithm that minimizes average reconstruction errors by orthogonal projections. In this video, we will introduce the setting of PCA and the high-level idea. Assume we have a data set X in Rd consisting of n vectors. So X is a data set, and we have n vectors x1 to xn, where the xi are d-dimensional vectors. Our objective is to find a low-dimensional representation of the data that is as similar to X as possible. Before we start, let's briefly review three important concepts. The first one is that every vector in Rd can be represented as a linear combination of the basis vectors. So let's write this down. So we write xn can be written as the sum of I equals 1 to d of beta in times bi, where in the following we will assume that the bi are an orthonormal basis of Rd. If we assume that we use the dot product as our inner product and b1 to bd are an orthonormal basis, we can also write the beta in as xn transpose times bi, which means we can interpret beta in to be the orthogonal projection of xn onto the one-dimensional subspace spanned by the ith basis vector. The third property is that if we have an orthonormal basis b1 to bm of Rd, and we define B to be the matrix that consists of these orthonormal basis vectors, then the projection of x onto this subspace we can write as x tilde is B times B transpose times x. That means x tilde is the orthogonal projection of x onto the subspace spanned by the m basis vectors. And B transpose times x are the coordinates of x tilde with respect to the basis vectors collected in the matrix B. This is also called the code. So coordinates or code. Now let's have a look at PCA. The key idea in PCA is to find a lower dimensional representation xn tilde of xn that can be expressed using fewer basis vectors, let's say m. We assume the data is centered, that means the dataset has mean 0, and we also assume that b1 to bd are an orthonormal basis of Rd. Generally, we can write any xn tilde in the following way. Xn tilde can be written as a sum I equals 1 to m of beta in times bi plus the sum of I equals m plus 1 to d of beta in times bi. So we took this entire thing is still living in Rd. So we took our general way of writing any vector in Rd, which comes from property 1, and we split the sum in property 1 into two sums. One is living in a m-dimensional subspace, and the other one is living in a d minus m-dimensional subspace, which is an orthogonal complement to this particular subspace. In PCA, we ignore the second term, so we get rid of this part. And then we call the subspace that is spanned by the basis vectors b1 to bm the principal subspace. So b1 to bm span the principal subspace. Although xn tilde is still a d-dimensional vector, it lives in an m-dimensional subspace of Rd, and only m coordinates, beta n1 to beta nm, are necessary to represent it. So these ones are the coordinate of this xn tilde vector. The betas are then also called the code or the coordinates of tilde xn with respect to the basis vectors b1 to bm. And the setting now is as follows. Assuming we have data x1 to xn, we want to find parameters beta in and orthonormal basis vectors bi such that the average squared reconstruction error is minimized. And we can write the average squared reconstruction error as follows. We can write j, that's the average squared reconstruction error, is going to be 1 over n times the sum n equals 1 to n. And then we write xn minus xn tilde squared. Let's have a look at an example. We have data living in 2 dimensions, and now we want to find a good one-dimensional subspace such that the squared or average squared reconstruction error of the original data points and their corresponding projections is minimized. Here I'm plotting the original data set with their corresponding projections onto one-dimensional subspaces, and I'm cycling through a couple of options of subspaces, and you can see that some of these projections are significantly more informative than others, and in PCA we are going to find the best one. Our approach is to compute the partial derivatives of J with respect to the parameters. The parameters are the beta in and the bi's. We set the partial derivatives of J with respect to these parameters to 0 and solve for the optimal parameters. But one observation we can already make, and that observation is that the parameters only enter this loss function through xn tilde. This means that in order to get our partial derivatives, we need to apply the chain rule. So we can write dj by d either beta in or bi can be written as dj by dxn tilde times dxn tilde by d either beta in or bi. And the first part we can already compute, and we get dj by dxn tilde is minus 2 over n times xn minus xn tilde transpose. And the other derivatives we compute in the next videos. In the last video we set up the PCA objective, and in this video we will determine our first set of optimal parameters. We make 2 general assumptions in the beginning. The first thing is that we have centered data. That means that the expected value of our data set is 0. And the second one is that the basis vectors form an orthonormal basis. From the previous video, we carry over the following results. First, we can write our projected data point xn tilde as a linear combination bjn times bj, where bj form the orthonormal basis of our subspace. Our loss function is the average squared reconstruction error between our original data point and the projection. And the partial derivative of our loss function with respect to xn tilde is given by this expression. And now we are ready to compute the partial derivative of J with respect to the beta in parameters as follows. So dj with respect to dbin is the derivative of J with respect to xn tilde times the derivative of xn tilde with respect to beta in. So now we're going to have a closer look at this one here. So d xn tilde by d beta in is simply given by bi for I equals 1 to m. And the reason for this is that if we take the derivative with respect to one fixed beta in, then only the ith component of this sum will play a role, and that's the reason why we end up simply with bi. But that also means that our derivative of J with respect to d beta in is now given as dj by d beta in is minus 2 over n times xn minus xn tilde transpose times bi, where here we used equation C to get the first part and we plugged in this bi over here. And what we're going to do now is we are going to replace xn tilde using equation A. So we end up with minus 2 over n times xn minus the sum of j equals 1 to m bjn times, so beta jn times bj transpose times bi. And this is given as minus 2 over n times xn transpose times bi minus beta in times bi transpose times bi, where we exploited that the bi form an orthonormal basis. If we multiply bi onto both components here, we end up with the sum of bjn times bj transpose times bi. And since bj transpose times bi is 1 if and only if I equals j and otherwise 0, we end up with only one term, which will be 1. So we end up with minus 2n times xn transpose bi minus beta in. So now we need to set this to 0 in order to find our beta in parameters, and this is 0 if and only if the beta in parameters are given by xn transpose times bi, which we're going to define as equation D. What this means is that the optimal coordinates of xn tilde with respect to our bases are the orthogonal projections of the coordinates of our original data point onto the ith basis vector that spans our principal subspace. In this video, we determined the coordinates of the lower dimensional data as the orthogonal projection of the original data onto the basis vectors that span the principal subspace. In the next videos, we will determine the orthonormal basis that spans that principal subspace. In the last video, we determined the coordinates of the optimal projection with respect to the orthonormal basis that spans our principal subspace. Before we go on and determine the optimal basis vectors, let's rephrase our loss function first. I have copied over the results that we have so far, so the description of our projected data point, our loss function, the partial derivative of our loss function with respect to our projected data point, and the optimal coordinates that we found in the last video. Before we go on and determine the optimal basis vectors, let's rephrase our loss function. This will make it much easier to find our basis vectors. For this, let's have a closer look at the difference vector between our original data point and our projected data point. So you can write, so xn tilde is given by equation A, which is the sum over j equals 1 to m beta jn times bj. If we now use the results for our optimal beta jn parameters from here, we get this is j equals 1 to m xn transpose times bj times bj, where we used d. Now we rewrite this in the following way. This is just a scalar, or dot product in this particular case. Dot products are symmetric, so we can swap the order. And we can also move the scalar over here. So what we end up with is bj times bj transpose times xn. And this one we can write generally as j equals 1 to m times bj transpose xn, where we moved the xn out of the sum. And if we look at this, this is a projection matrix. So this means that xn tilde is the orthogonal projection of xn onto the subspace spanned by the m basis vectors bj, where j equals 1 to m. Similarly, we can write xn as the sum j equals 1 to m of bj times bj transpose times xn plus a term that runs from m plus 1 to d bj times bj transpose times xn. So we write xn as a projection onto the principal subspace plus a projection onto the orthogonal complement. And this term is the one that is missing over here. And that's the reason why xn tilde is the approximation to xn. So if we now look at the difference vector between xn tilde and xn, what remains is exactly this term. So xn minus xn tilde is the sum j equals m plus 1 to d of bj times bj transpose times xn. So now we can look at this displacement vector, so the difference between xn and its projection, and we can see that the displacement vector lies exclusively in the subspace that we ignore. That means the orthogonal complement to the principal subspace. Let's look at an example in 2 dimensions. We have a data set in 2 dimensions represented by these dots, and now we are interested in projecting them onto the U1 subspace. When we do this and then look at the difference vector between the original data and the projected data, we get these vertical lines. That means they have no x component or no variation in x. That means they only have a component that lives in the subspace U2, which is the orthogonal complement to U1, which is the subspace that we projected onto. So with this illustration, let's quickly rewrite this in a slightly different way. I'm going to write this as sum of j equals m plus 1 to d of bj transpose xn times bj, and we're going to call this now equation E. We looked at the displacement vector between xn and its orthogonal projection onto the principal subspace xn tilde. And now we're going to use this to reformulate our loss function. So from equation B, we get that our loss function is 1 over n times the sum n equals 1 to n of xn minus xn tilde squared. So this is the average squared reconstruction error. And now we're going to use equation E for the displacement vector here. So we rewrite this now using equation E as 1 over n times the sum n equals 1 to capital N. And now we're going to use inside that squared norm this expression here. So we get the sum j equals m plus 1 to d of bj transpose times xn times bj squared. And now we're going to use the fact that the bj's form an orthonormal basis, and this will greatly simplify this expression, and we will get 1 over n times the sum n equals 1 to capital N times the sum j equals m plus 1 to d of bj transpose times xn squared. And now we're going to multiply this out explicitly, and we get 1 over n times the sum over n times the sum over j times bj transpose times xn times xn transpose times bj. So this part is now identical to this part. And now I'm going to rearrange the sums. So I'm going to move the sum over j outside. So I'll have sum over j equals m plus 1 to d times bj transpose, so this is independent of n, times 1 over n, the sum n equals 1 to capital N of xn times xn transpose, and there's a bj from here missing, times bj. So I'm going to bracket it now in this way. And what we can see now is that if we look very carefully, we can identify this expression as the data covariance matrix S, because we assumed we have centered data. So the mean of the data is 0. This means now we can rewrite our loss function using the data covariance matrix, and we get that our loss is the sum over j equals m plus 1 to d of bj transpose times S times bj. And we can also use a slightly different interpretation by rearranging a few terms and using the trace operator. So we can now also write this as the trace of the sum of j equals m plus 1 to d of bj times bj transpose times S. And we can now also interpret this matrix as a projection matrix. This projection matrix takes our data covariance matrix and projects it onto the orthogonal complement of the principal subspace. That means we can reformulate the loss function as the variance of the data projected onto the subspace that we ignore. Therefore, minimizing this loss is equivalent to minimizing the variance of the data that lies in the subspace that is orthogonal to the principal subspace. In other words, we're interested in retaining as much variance after projection as possible. The reformulation of the average squared reconstruction error in terms of the data covariance gives us an easy way to find the basis vector of the principal subspace, which we'll do in the next video. In the last video, we found that minimizing the average squared reconstruction error is equivalent to minimizing the projection of the variance of the data when projected onto the subspace that we'll ignore in PCA. In this video, we will exploit this insight and determine an orthonormal basis of the m-dimensional principal subspace. Using the results from earlier, over here, we can write our loss function as the sum j equals m plus 1 to d of bj transpose S times bj, where S is the data covariance matrix. Minimizing this objective requires us to find the orthonormal basis that spans the subspace that we will ignore. And when we have that basis, we take its orthogonal complement as the basis of the principal subspace. Remember that the orthogonal complement of a subspace U consists of all vectors in the original vector space that are orthogonal to every vector in U. Let us start with an example to determine the B vectors. And let's start in 2 dimensions, where we wish to find a one-dimensional subspace such that the variance of the data when projected onto that subspace is minimized. So we're looking at 2 basis vectors, B1 and B2 in R2. So B1 and B2. And B1 will be spanning the principal subspace and B2 its orthogonal complement. That means the subspace that we will ignore. We also have the constraint that B1 and B2 are orthonormal, which means that Bi transpose times Bj is delta Ij, meaning that this dot product is 1 if I equals j and 0 otherwise. In our example with our two vectors, our loss function is j is B2 transpose times S times B2, with the constraint that B2 transpose times B2 is 1. To solve this optimization problem, we write down the Lagrangian, and the Lagrangian is B2 transpose S B2 plus lambda times 1 minus B2 transpose times B2, where lambda is the Lagrange multiplier. So now we compute the gradients of the Lagrangian with respect to B2 and with respect to lambda and set them to 0. So dl d lambda is 1 minus B2 transpose times B2, and this is 0 if and only if B2 transpose times B2 is 1. So we recover our constraint. So now let's have a look at the partial derivative of L with respect to B2. So we get 2B2 transpose times S from the first term and minus 2 lambda B2 transpose from the second term. And this needs to be 0, and that is 0 if and only if S times B2 is lambda times B2. Here we end up with an eigenvalue problem. B2 is an eigenvector of the data covariance matrix, and the Lagrange multiplier plays the role of the corresponding eigenvalue. If we now go back to our loss function, we can use this expression. We can write J, which was B2 transpose times S times B2. Now we know that S times B2 can be written as lambda times B2. So we get B2 transpose times B2 times lambda, and because we have an orthonormal basis, we end up with lambda as our loss function. Therefore, the average squared reconstruction error is minimized if lambda is the smallest eigenvalue of the data covariance matrix. And that means we need to choose B2 as the corresponding eigenvector, and that one will span the subspace that we will ignore. B1, which spans the principal subspace, is then the eigenvector that belongs to the largest eigenvalue of the data covariance matrix. Keep in mind that the eigenvectors of the covariance matrix are already orthogonal to each other because of the symmetry of the covariance matrix. So if we look at a two-dimensional example, if this is our data, then the best projection that we can get that retains most information is the one that projects onto the subspace that is spanned by the eigenvector of the data covariance matrix, which belongs to the largest eigenvalue. And that is indicated by this long arrow over here. Now let's go to the general case. If we want to find the m-dimensional principal subspace of a d-dimensional data set, and we solve for the basis vectors bj, where j equals m plus 1 to d, we optimize these ones, we end up with the same kind of eigenvalue problems that we had earlier with a simple example. We end up with S times bj equals lambda j times bj for j equals m plus 1 to d. And the loss function is given by the sum of the corresponding eigenvalues. So we can write j is the sum from m plus 1 to d of all lambda j. Also in the general case, the average reconstruction error is minimized if we choose the basis vectors that span the ignored subspace to be the eigenvectors of the data covariance matrix that belong to the smallest eigenvalues. This equivalently means that the principal subspace is spanned by the eigenvectors belonging to the m largest eigenvalues of the data covariance matrix. This nicely aligns with properties of the covariance matrix. The eigenvectors of the covariance matrix are orthogonal to each other because of symmetry, and the eigenvector belonging to the largest eigenvalue points in the direction of the data with the largest variance, and the variance in that direction is given by the corresponding eigenvalue. Similarly, the eigenvector belonging to the second largest eigenvalue points in the direction of the second largest variance of the data, and so on. In this video, we identified the orthonormal basis of the principal subspace as the eigenvectors of the data covariance matrix that are associated with the largest eigenvalues. In the next video, we will put all the pieces together and run through the PCA algorithm in detail. In this video, we'll go through the individual steps of PCA. But before we do this, let me make two comments. When we derived PCA, we made the assumption that our data is centered. That means it has mean 0. This assumption is not necessary to derive PCA, and we would have come to the same result, but subtracting the mean from the data can avoid numerical difficulties. Assume the values of our data are centered around 10 to the 8. Then computing the data covariance matrix requires us to multiply huge numbers, which results in numerical instabilities. An additional second step that is normally recommended after subtracting the mean is to divide every dimension of the centered data by the corresponding standard deviation. This makes the data unit-free and guarantees that the variance of the data in every dimension is 1, but it leaves the correlations intact. Let's have a look at an example. Clearly, this data spreads much more in one dimension than the other dimension, and the best projection of PCA is clear. However, there's a problem with this data set. The two dimensions of the data set are both distances, but one is measured in centimeters and the other one in meters. The one measured in centimeters naturally varies much more than the other one. When we divide each dimension of the data set by the corresponding standard deviation, we get rid of the units and make sure that the variance in each dimension is 1. When we look at the principal subspace of this normalized data set, we can now see that there is actually quite a strong correlation between these two dimensions, and the principal axes have changed. But now let's go through PCA step by step, and we'll have a running example. We're given a two-dimensional data set, and we want to use PCA to project it onto a one-dimensional subspace. The first thing that we do is to subtract the mean. The data is now centered. Next, we divide by the standard deviation. Now the data is unit-free and it has variance 1 along each axis, which is indicated by these two arrows. But keep in mind that the correlations are still intact. Third, we compute the data covariance matrix and its eigenvalues and corresponding eigenvectors. The eigenvectors are scaled by the magnitude of the corresponding eigenvalue in this picture. The longer vector spans the principal subspace, let's call it U. And in the last step, we can project any data point x star onto the principal subspace. To get this right, we need to normalize x star using the mean and standard deviation of the dataset that we use to compute the data covariance matrix. So we are going to have a new x star, and the new x star is going to be the old x star minus the mean of the dataset divided by the standard deviation, and we do this for every dimension in x star. Now we can get the projection of x star as x star tilde, or the projection of x star onto the principal subspace U as B times B transpose times x star, where B is the matrix that contains the eigenvectors that belong to the largest eigenvalues as columns, and B transpose times x star are the coordinates of the projection with respect to the basis of the principal subspace. In this video, we went through the steps of PCA. First, we subtract the mean from the data and send it at 0 to avoid numerical problems. Second, we divide by the standard deviation to make the data unit-free. Third, we compute the eigenvalues and eigenvectors of the data covariance matrix. And finally, we can project any data point onto the principal subspace that is spanned by the eigenvectors that belong to the largest eigenvalues. In the last video, we've gone through the steps of the PCA algorithm. In order to do PCA, we need to compute the data covariance matrix. In d dimensions, a data covariance matrix is a d by d matrix. If d is very high, so in very high dimensions, then computing the eigenvalues and eigenvectors of this matrix can be quite expensive. It scales cubically in the number of rows and columns, in this case, the number of dimensions. In this video, we provide a solution to this problem for the case that we have substantially fewer data points than dimensions. Assume we have a data set given as x1 up to xn in Rd, and we assume that the data is centered, so it has mean 0, then the data covariance matrix is given as S equals 1 over n times x transpose times x, where we define x to be the matrix that consists of x1 transpose up to xn transpose, and that is an n by d matrix. We now assume that n is significantly smaller than d. That means the number of data points is significantly smaller than the dimensionality of the data. And then the rank of the covariance matrix is n. So rank of S equals n. And that also means it has d minus n plus 1 many eigenvalues, which are 0. That means that the matrix is not full rank, and the rows and columns are linearly dependent. In other words, there are some redundancies. In the next few minutes, we'll exploit this and turn the d by d covariance matrix S into a full rank n by n covariance matrix without eigenvalues 0. I've just moved the covariance definition up here to have a bit more space on the board. In PCA, we ended up with the following eigenvalue eigenvector equation. We had S times bi equals lambda I times bi, where bi is a basis vector of the orthogonal complement of the principal subspace. Now let's rewrite this equation a little bit. We're now going to replace S with the definition up here. So we'll get 1 over n times x transpose x, this is S, times bi equals lambda I times bi. And now we multiply x from the left-hand side. So we will get x times x transpose x bi times 1 over n equals lambda I times x times bi. And now we have a new eigenvector eigenvalue equation. So lambda I is still an eigenvalue, and now we have eigenvectors x times bi, which we call ci, of the matrix 1 over n times x transpose. This means that 1 over n times x transpose has the same non-zero eigenvalues as the data covariance matrix, but this is now an n by n matrix, so that we can compute the eigenvalues and eigenvectors much quicker than for the original data covariance matrix. All right, so this is an n by n matrix, whereas S used to be a d by d matrix. So now we can compute the eigenvectors of this matrix 1 over n times x transpose. And we use this to recover the original eigenvectors, which we still need to do PCA. Currently, we know the eigenvectors of 1 over n times x transpose. And we want to recover the eigenvectors of S. If we left multiply our eigenvalue eigenvector equation with x transpose, we get the following. So you get 1 over n times x transpose times x transpose times ci equals lambda I times X transpose times Ci. And now we find our S matrix again. This is S. And this also means that we recover X transpose times Ci as an eigenvector of S that belongs to the eigenvalue lambda I. In this video, we reformulated PCA such that we can efficiently run PCA on datasets where the dimensionality of the data is substantially bigger than the number of data points. We derived PCA from the perspective of minimizing the average squared reconstruction error. However, PCA can also be interpreted from different perspectives. In this video, we'll have a brief look at some of these interpretations. Let's start with a recap what we have done so far. We took a high-dimensional vector x and we projected it onto a lower dimensional representation z using the matrix B transpose. The columns of this matrix B are the eigenvectors of the data covariance matrix that are associated with the largest eigenvalues. The z values are the coordinates of our data point with respect to the basis vectors which span the principal subspace, and that is also called the code of our data point. Once we have that low dimensional representation z, we can get a higher dimensional version of it by using the matrix B again, so multiplying B onto z to get a higher dimensional version of the z in the original data space. We found the PCA parameters such that the reconstruction error between x and the reconstruction x tilde is minimized. We can also think of PCA as a linear autoencoder. An autoencoder encodes a data point x and tries to decode it to something similar to the same data point. The mapping from the data to the code is called an encoder. Let's write this down. So this part here is called an encoder. The mapping from the code to the original data space is called the decoder. If the encoder and decoder are linear mappings, then we get the PCA solution when we minimize the squared autoencoding loss. If we replace the linear mapping of PCA with a nonlinear mapping, we get a nonlinear autoencoder. A prominent example of this is a deep autoencoder where the linear functions of the encoder and decoder are replaced with deep neural networks. Another interpretation of PCA is related to information theory. We can think of the code as a smaller compressed version of the original data point. When we reconstruct our original data using the code, we don't get the exact data point back, but a slightly distorted or noisy version of it. This means that our compression is lossy. Intuitively, we want to maximize the correlation between the original data and the lower dimensional code. More formally, this would be related to the mutual information. We would then get the same solution to PCA we discussed earlier in this course by maximizing the mutual information, a core concept in information theory. When we derived PCA using projections, we reformulated the average reconstruction error loss as minimizing the variance of the data that is projected onto the orthogonal complement of the principal subspace. Minimizing that variance is equivalent to maximizing the variance of the data when projected onto the principal subspace. If we think of variance in the data as information contained in the data, this means that PCA can also be interpreted as a method that retains as much information as possible. We can also look at PCA from the perspective of a latent variable model. We assume that an unknown lower dimensional code Z generates data X, and we assume that we have a linear relationship between Z and X. So generally we can then write that X is b times z plus mu, and maybe some noise. We assume that the noise is isotropic with mean 0 and covariance matrix sigma squared times I. We further assume that the distribution of this z is a standard normal. So P of z is Gaussian with mean 0 and covariance matrix, the identity matrix. We can now write down the likelihood of this model. So the likelihood is P of x given z, and that is a Gaussian distribution in x with mean bz plus mu and covariance matrix sigma squared I. And we can also compute the marginal likelihood as P of x is the integral of P of x given z, so that is the likelihood times the distribution on z dz, and that turns out to be a Gaussian distribution in x with mean mu and with covariance matrix b times b transpose plus sigma squared I. The parameters of this model are mu, b, and sigma squared, and we can write them explicitly down in our model up here. So model parameters are b and mu and sigma squared. We can now determine the parameters of this model using maximum likelihood estimation. And we will find that mu is the mean of the data, and B is a matrix that contains the eigenvectors that correspond to the largest eigenvalues. To get the low-dimensional code of a data point, we can apply Bayes' theorem to invert the linear relationship between z and x. In particular, we are going to get P of z given x as P of x given z. So that is the likelihood, which comes from here, times P of z. So that's our distribution that we have here, divided by the marginal likelihood, P of x, which comes from here. In this video, we looked at 5 different perspectives of PCA that lead to different objectives: minimizing the squared reconstruction error, minimizing the autoencoder loss, maximizing the mutual information, maximizing the variance of the projected data, and maximizing the likelihood in a latent variable model. All these different perspectives give us the same solution to the PCA problem. The strengths and weaknesses of individual perspectives become more clear and important when we consider properties of real data. In this module, we derived PCA and looked at some of its properties. By minimizing the average squared error between a data point and its projection onto the principal subspace, we found that the best thing to do is to project onto the subspace that is spanned by the eigenvectors that belong to the largest eigenvalues. PCA has a lot of similarities to other machine learning algorithms, so it's good that we had a closer look at it. This module was very hard, but I hope you gained some new and interesting insights, either through the detailed derivation or through the practical exercises. Well done completing this module. In this course, we looked at PCA, a practical machine learning algorithm for dimensionality reduction and data compression. We covered a lot of material to get to the point where we could derive and understand how PCA works. We started off with some summary statistics of data, means and variances, which we later used to compute the data covariance matrix in PCA. Then we looked at inner products, which allowed us to compute lengths, distances, and angles between vectors. We used these inner products for orthogonal projections of data onto lower dimensional subspaces. And in the end, we put everything together for the PCA algorithm. I'm aware that this course was challenging at times, but I hope you enjoyed it nevertheless. A big thanks to everyone who made it this far and completed the course. Very well done.